everyone. I'm hoping that people online can hear me. So if you can check whether my mic is. Maybe this is on now.
Okay. Good morning, everyone. So welcome to our knowledge sharing session for our Arena project. As you probably know, we've got a hybrid event, and we are hoping that everything will go well. Typically, in these hybrid events, there are so many different things that we need to make sure are taken care of. But let's see how we go today. We are in a beautiful venue on our Clayton campus, learning and teaching building. People are still coming in, and we're hoping that everybody can find their way to this venue, given the other events going on today here in this building. So, good morning, everyone. I'm Dr. Behrooz Bahrani, a senior lecturer in the Electrical and Computer System Engineering Department within Monash Engineering Faculty of Engineering. Before we begin, some housekeeping about where we are for people who are here in the building. We've got restrooms next to the elevator. We came to the second floor. There's also a kitchenette next to the restroom if you need, but the catering is just outside. You probably can find everything that you need during the day. It's going to be a day-long event, so we'll be starting now, and if everything goes well, we'll be finishing around 5 p.m. So I guess everybody who came to the room knows where the catering is. Now, it's my pleasure to chair this knowledge sharing session with you today. Before we start, I would like to acknowledge the people of the Kulin Nation, the traditional owners and custodians of the land where I'm hosting this session today. I pay my respects to their elders, past and present. It is now my pleasure to invite to this stage Professor Tony Markson to say a few words before I start the presentation. Tony.
Thanks, Behrooz. Is that audio all right, Larissa?
I believe so.
Okay. Well, today's a bit of an exciting day for us in the Grid Innovation Hub. This was the first major research project that the Hub succeeded in defining and getting both industry and Monash support for and ARENA funding. So in the last 2.5 years, the project has produced a significant amount of research results. I should just say a bit about the Grid Innovation Hub for those who are not familiar with it. It is a joint industry Monash vehicle for defining and facilitating and arranging funding for research that's of value to Australia, specifically energy markets and the national grid. All links in the chain of energy production and delivery and consumption, and everything from precinct scale up to national scale. And this project is a classic of what we want to produce. I think the only thing that is missing is it's very much power grid engineering, and we are moving slowly but steadily towards interdisciplinary studies. And we have another project underway in the business and economics area on the market treatment of storage and the dispatch engine that is required if you're going to properly represent storage on the grid, and the industry competition policy required with the change in the grid from a traditional coal, hydro, gas powered grid to a renewables grid. So the challenge that we've set ourselves to tackle is huge. It's not going to go away anytime soon. It's just going to get more so. And Monash is, as you can see, or you will see today with this project, is well positioned and to bring a lot of very expert and talented resources to bear to help Australia meet those challenges. We see the sort of research that you see presented today is just the first step. You know, most of you, many of you would be fully aware of the process of research. You start with academic papers that explain ideas and test them on simulations and so on. And then you migrate up to actually trying them on a real grid in a real market. And if they work as well as the simulations say they will, then they get adopted as an industry market and grid standard for the future. So what you're going to hear today is the presentation of the ideas and the simulation results, which indicate the value of those ideas to Australia in meeting this challenge. So welcome everyone, and I think it's going to be a fascinating day. Back to you, Behrooz.
Thank you so much, Tony. I would like to give a very brief overview of the project before we go and hear about our partners in the project. A few words. I believe most of you are already familiar with the, at least the title of the project, Stability Enhancement of Utility Scale Renewable Energy Farms in Weak Grids. It looks like that my thing is not working. Or should I turn it on? Yes. So yes, turn it on first before you use it. Okay. So, okay. Still not working. Okay, mouse is better. Okay, good. I believe everybody in the room and online knows about the system strength issues that we've got in Australia and all the challenges that comes with that. You probably have seen this before many times in many different places, and you'll probably see it a few times today in our presentations, that system strength in Australia is not really so good. We've got a lot of these red dots which represent very weak parts of the network, and these weak parts of the network, they lead into so many different problems: control interactions, failure to ride through disturbances, low frequency stability issues, islanding issues, inability of farms to maintain their stability. And what we are hoping to do in this project, we're hoping to come up with solutions that can help us navigate through this energy transition and add more and more renewables to these weak parts of the grid, or strengthen these weak parts of the grid in order to be able to integrate more renewables. And you know, the bigger challenge that we are facing in future years is that most of the good renewable energy zones that we've got in the NEM are located in weaker parts. So that's a very big challenge. And what we wanted to do in this project, we wanted to tackle all these issues. So we were funded this project back in 2020. We started 2020, and we defined 3 tasks in the project. First one was to define weak grids and develop a nice test bed to do all the studies. And second, and most probably important, was grid strengthening solutions that we're hoping to come up with to assist more and more grid integration into these weak areas. And finally, to understand better the interactions of these controllers on each other and how these controllers might actually affect each other. We had 3 partners in the project: AusNet Services as part of our Grid Innovation Hub, AEMO and Hitachi Energy. They were supporting us in the project, and we'll hear from them soon. The aims of the project, well, I'm not going to go through all the details here, and you'll see more from our fantastic presenters today. But particularly wanted to understand, classify and describe the stability issues in the grid, and identify and develop tools to come up with controllers that can actually strengthen the grid, particularly syncons and grid forming inverters, and enhance control of grid following inverters, which are the flavor of all the presentations that you will be seeing today. So the outcomes obviously will be increased penetration, maximized generation, and increased reliability and security and stability. For the project, we developed a website, and this website I very much encourage you to have a look at. It's a pretty well-developed website, including all the papers that we have developed, publication, and a lot of information about the project. It is hosted on Monash Energy website. So if you search for the name of the project and Monash Grid Innovation Hub or Monash Energy Institute, this will come up. And we have a section in this which is hosting all of the publications. So if you go to that website, you will see. And today we will try to give you as much as we can in terms of the details of these concepts that we've developed, which are all presented in these publications in detail, of course. We have uploaded the PDF version of all of these things. Some of them are open access, so you can have access to the publisher's version. Some of them are not. We have uploaded the latest version that we have submitted to the publisher, which we can in terms of licensing and copyrights. So the project started back in 2020 with this team. Ms. Jackie Bridge back then was at AusNet. Dr. Zhou was back then at AEMO, and Dr. Zabi, Hitachi, Dr. Razvari, and Professor Markson from Monash. I think at some point, so Jackie left, and Sorel was the point of contact. And Nilesh, Dr. Nilesh Modi from AEMO was the point of contact for us at AEMO. Now, like I said, what we were focusing on in the project was around syncons, grid following inverters, and grid forming inverters. So that's the flavor of all of the publication and the work that we've done. So we're focused on providing and proposing grid strengthening solutions in all these different technologies. And you'll see a lot from our researchers today that how and what we've done all these concepts. But it goes without saying that this project wouldn't be successful with the fantastic team that I had. I had the pleasure of supervising and leading a fantastic team. We had three researchers, postdoctoral researchers, Dr. Ravanji, Dr. Mohammed, and Dr. Zhou. Brilliant researchers, and you'll be hearing from them today. And our superstars, PhD students that I'm very much proud of, Dr. Zarif Mansour, Dr. Hadavi, Dr. Rathnayake, and Mr. Si Phu Me. You will meet them, you will hear from them. Dr. Zarif Mansour is currently at Oricon. Dr. Hadavi at Gridwise, and Dr. Rathnayake, well, he will be soon, doctor, at AEMO. And Si Phu is still with us as a PhD student, continuing his brilliant work on grid forming inverters and interaction of grid forming inverters with grid following inverters. So thank you, team. And I guess that's the end of my brief presentation. So I think before we start the technical presentation, I would like to hand over to our partners to hear a few words, and we can start with Sorel. Sorel, please.
All right, thanks very much. Hi, everyone. I'm Sorel Grogan. I'm an engineer at AusNet Services. And I first of all want to start off with a big thank you to the team at Monash for the outstanding effort, our friends at AEMO and Hitachi ABB for all of the invaluable contributions and guidance that was given to the team. And of course, ARENA for chipping in a sizable amount of the funding to actually make it happen. Look, I could get up here and make the usual cliched statement about our energy industry is in a once-in-a-lifetime transition. I'm increasingly thinking that's not quite accurate. I think it's ongoing. I think it's more nuanced than that. And I think there's already been multiple iterations, at least, of a transition in this industry. And there's many, many more on the horizon. Where I see it, and as I look around the room, I realise this analogy might not hit home given how young everyone looks, but what I see where we're at the moment is very much akin to the late 90s internet, right? Where it's internet version 1.0. There's been incredible progress and change. There's an exciting new future available to anyone with their eyes open. Everyone knows about what's happening, but not everyone's really engaged with it. They've just heard about it. And also, like the 90s internet, we're really unrefined at the moment. So there are plenty of bugs. There are plenty of mishaps. Is South Australia reconnected yet? No. Not yet, no. I did, yeah, okay, great. That's important. We're very much coasting on old world technology and infrastructure. So in many ways, it's still a bit like the Wild West in what we're trying to do as part of this transition. So there have been some really admirable and important efforts to steer development. A special shout out to the AEMO team and some of the ISP work that's been done there. But there are still many conflicting interests, and some people will just naturally have a distrust of centralized coordination. And as a result of all of that, our energy systems are not only decentralized, but they're democratized as well. And when we have a democratized system, that brings incredible opportunity, but it also can bring some chaos along with it. What that means, from a financial perspective, there are some people who, are having trouble making money. There are others who the conditions could not be better. Technically, though, we're still very much figuring it out as we go. We're hoping stuff holds together. So in terms of an analogy with the early internet, this is where the analogy actually needs to end. While the early internet could suffer outages with only a few mild inconveniences to a subset of the population, electricity is way too critical of an infrastructure to have such failures. It's the most, in my opinion, it's the most critical of all critical infrastructures. Everything takes electricity as an input nowadays. Telecommunications, gas systems, water systems, everything, right? It all uses electricity. And this is where this Monash Grid Innovation Hub work comes in. What's been delivered as part of this work are critical inputs to developing the next iteration of renewable enabling and decentralized generation technology. In particular, the work completed here in this program can look at how a robust system can be developed and coexist with the already first generation of new renewable energy fleet that's connected, and also how it can evolve with the changes that are on the horizon as well to make sure that we have a stable and secure system. Look, the work done includes important inputs into not only new manufacturing designs, but as well as inputs into a lot of the planning and operational efforts that need to be done as we transition to a new system. So look, rather than me standing up here and attempting to, summarize it all, I'm going to leave it to the team with far more skill to actually go through it. I want to thank again everyone for all the amazing work that was being done. And on a personal level, I also want to thank you for bringing me along on this intellectual journey. It's been really illuminating. Thank you all.
Thank you so much, Sorel. Very much appreciated. Now I would like to invite our next guest. So it would be from AEMO, and I believe Nilesh, you are, Nilesh is not, okay, Jay is there, but okay, the name is Nilesh. So Jay, if you could please, say a few words on AEMO's behalf, and I'm hoping that we can hear Jay in the room.
Yeah, sure. Can you hear me all right?
We cannot hear you, Jay.
Oh, okay. I think the people on the call.
I can hear you, Jay. Yeah.
Oh, it looks like that people online can hear, but in the room, we don't have the voice. Can you try again, Jay, please?
Hello.
Oh, looks like that we have some issues with the speakers in the room. So the speakers.
Can you hear me, Behrooz?
Here.
Or maybe not, John.
Can't hear either of us. Okay. I know we were getting an echo at the start, so maybe Larissa
speaker here.
Turned something off. That was giving that feedback, maybe.
This one. Okay, I think we can hear you now.
Hello.
Yes, fantastic.
Okay.
Fantastic.
Okay, good.
Yes. Okay. Sorry for that.
Yeah, thank you, Behrooz. And as Behrooz mentioned, Nilesh is an apology. So I have to introduce myself. I'm Jay. I'm with AEMO Operational Analysis and Engineering. I'm a principal engineer here. I'm at the moment quite involved in the system strength studies and quite a few different operational analysis and engineering studies here at AEMO. I would be remiss in my introduction if I did not mention that I spent more than 15 years in the United States before I moved here to Australia. So I get to see two different standards in two different parts of the world. I would definitely say that Australia is definitely on the forefront when it comes to renewables, and definitely a world leader that we have to learn collectively together of the challenges and what we can make of this energy transition. Secondly, I want to thank the team at Monash for giving AEMO an opportunity to be part of this project. I've been provided from input from Nilesh that this has been a very involved project, and we really look forward to the publications and how we can leverage some of these findings from an academic perspective to the industry perspective. So on that note, I would say what the topic that, as you all know, there is a lot of challenges with this low system strength, and as Behrooz mentioned, it arises from two issues. One is remoteness to the synchronous generation, and the other is really the high penetration of IBR. Classic example is West Murray Zone, and if you go to the AEMO website, you can see some recent publications as well on this topic. But I think the challenge is looking forward from an operations perspective, really, the challenge really comes down to two things. Like if you talk about, say, the subsynchronous oscillation, say, for example, one is how do you predict that in a control room environment? And secondly, what thresholds are acceptable? Is it just a power quality issue that you can just brush away, or is it 2% acceptable, 5% acceptable? So those are real challenges that as an industry, as we move further, we have to improve our understanding on. And as Sorel gave a classic example of the internet of the 1990s and how we are fixing little bugs here and there, and how we evolve the industry, but doing that, evolving it in a very careful manner. And as you know, it's as Sorel rightly pointed, it's electricity is a very critical infrastructure, and the solutions have to be thoroughly tested. If we come up with small signal analysis tools in the research front, how do we take that? How do we evolve those tools? How do we look at this? Performing those open loop analysis of Y converter multiply with the impedance of the grid, and how you can predict those interactions. And those are all, I think, challenges that we have to address. And as you know, these small signal analysis tools are well evolved for synchronous machines, but still we are all learning as an industry and how we can apply these understanding to the control room. So that's my 2 cents on this introduction, and I'd like to convey from Nilesh that we are excited to be part of this project and look forward to collaborating even further with Monash. Thank you.
Thank you so much. I would like also to thank AEMO for their fantastic contributions. They've been very much involved and engaged in the project. They've been assisting us significantly. They have also provided us with a lot of information and data and models that enabled us to do a lot of the work. So thank you so much. Now I would like to introduce John from ARENA. John Girardello, if you could please give us a few introduction to the work and ARENA's perspective.
Thank you, Behrooz, and good morning all. Sorry I can't be with you there today, but John Girardello, the client manager on this project over the last 2.5 years from ARENA. So I would firstly just like to reiterate what the other two speakers have said and thank Behrooz, Tony, Larissa and the team for their collective efforts on this project over the last 2.5 years. So as an observer, I've been on the steering committee for the project, and I've always been impressed with the volume and quality of outputs that have flowed from the project, and we'll see a lot of that today. Always been impressed with the engagement and response to stakeholders, and importantly the network operator who have been involved with this project, because I think what ARENA's always tried to do is encourage research to link with practical change for renewables, and this project has definitely done that, is doing that, and and we'll obviously get to evidence that today. Grid stability sits at front and centre with our priority one at ARENA, and that is to optimise the transition to renewable energy. So ARENA is, when this project comes to an end, we're hopeful that there's potential further engagement with Monash and the team on this theme of grid stability beyond the end date further into next year. So a message from our business development team out of Sydney on this important work, and I quote that ARENA is sure that advanced inverters are expected to play a big role in aiding the power system to 100% instantaneous renewables. So, of course, that's most to people in this room. And just finally, from me, a big congratulations to the team. I mean, navigating the COVID years, it began only a couple of months into the COVID lockdown, so the border closures, the closure of labs and access to the university. I know Behrooz is smiling there as the challenge of managing a significant sized team on this project hasn't been missed by ourselves, and I really appreciate. I looked through the records this morning. There's only been 2 or 3 variations on this project compared to some that I've worked with over the last 3 years. It's a very small amount by comparison, and I know this project ends in the number 007, so I just thought that maybe that's apt with Behrooz's ability to navigate his team over these 2.5 years, and perhaps he is Monash's own version of James Bond. So a big congratulations. Looking forward to the day, and good luck to the fellows and PhD students who are presenting today. So back to you.
Thank you so much. And we would like to acknowledge again the fantastic support from ARENA. Of course, without your support, this work wouldn't be possible. So thank you again. So last but not least, I would like to invite Dr. Zabi from, well, back then it was, I guess, when we first started, it was ABB and then became ABB Hitachi, or Hitachi ABB, and now Hitachi Energy. So to say a few words about the project, Hasan.
Hey, good morning all. Glad to be here among you. And yeah, thank you, Behrooz. Thank you, everyone who's been playing a good role throughout this fantastic journey. When we started this like 2.5 years ago, we knew the issue, but the challenges around it was not specified. The origins of the issues that we are well aware of these days, it's well recognized, but it was not recognized at that point, and basically we owe this to the team who worked on different aspects of this project and the solutions. So I have to thanks for the opportunity that's provided to the team here, and to the contributors and to the members of this project who played a significant role in succeeding through, as I said, recognizing and specifying the issues and the challenges, and then exploring the solutions as much as we could, and coming up with significant outcome, I would say, throughout this journey. So yeah, probably I'll just limit my words to the appreciation that I'd like to show to everyone who was engaged in this project.
Thank you, Hasan.
Thank you.
So I guess it's about time to go to the technical presentations, and our first presenter for the day is Dr. Sajjad Hadavi. Dr. Hadavi received a BS and MS degrees in electrical engineering from Amir Kabir University of Technology, Tehran, Iran in 2013 and 15, and the PhD degree from Monash University, Australia. He is currently working as a senior power system engineer at Gridwise Energy Solutions. He has been involved in ARENA project on the stability enhancement of utility scale renewable energy farms in Grid and several large scale renewable energy connections across the NEM over the past few years. His research interests include control of power electronic systems, power electronics in power systems, and grid integration of renewables. Please welcome Sajjad to the stage. Well, you
Hello, everyone. Thanks, Behrooz, for his kind word and support during that project. So I'm Sajjad Hadavi, Senior Engineer at Gatewise Energy Solution. I'm here to present my research during my PhD at Monash University, alongside with this AEMO project, which was stability enhancement and interaction of the synchronous condenser and renewable energies in weak grids. First, sorry for. Okay, so first, briefly, I'm going through the introduction, then I will explain about the research aim and the question that we answered with our project, and also the three output of the this project. As you know, the renewables are booming and the penetration of the renewables are increasing in power system, and the traditional fossil fuel-based generation will be replaced by renewable. For example, by 2040, 54 gigawatt of renewable will be placed in the system and replace around 60 gigawatt of fossil fuel-based generation. The fossil fuel-based generation provide you inertia, provide you system strength in the system. And because of that Australian power system, as Behrooz showed you that figure previously, I'm not going through that one in detail, but you can see the red point. And this situation will be catastrophic by 2038, 2039, with that pace of the renewable integration to the system. So this low system strength issue and different point of the NEM will be in weak grid situation. So first of all, I want to explain what are the problems that introduced in a system with high penetration of renewable, with a low system strength, and what are the dynamic challenges that we have. One of them is the failure to ride through the disturbances. As you can see, for by high penetration of renewable, they cannot meet, may not ride through the disturbances such as what happened at 2016 in South Australia. And also we can have some subsynchronous oscillation in the system. The West Murray region that you know the issue here. And also they can have, because all of these renewable have their own control strategy or control structure. They can interact with each other. The nearby generator can interact with each other, and they can cause some instability in the system. These are some real problems that I already mentioned that it happens in the system, that we are aware of them. So what are the solutions to these issues, these low system strength issues? One of them is to improve the transmission line, which is a costly solution. And the other one is to improve the control structure of our renewable, which my colleagues will present later, that there is another approach to improve the performance of the renewables in a weak grid. And also the third one is to add some system strengthening assets, such as synchronous condenser or grid forming inverter. In this project, we are aiming to use synchronous condenser as a system strengthening asset to a weak grid with high penetration of renewables. And we are aiming to reach these 2 points. First of all, we want to utilize syncons in a system with high penetration of renewable and see the impact of that, the dynamic impact of the syncon in the system, and how we should utilize them, where we should install them, and what should be the size of the syncon based on the problem and issues that we have in the system. And also, we want to introduce a framework to analyze the stability of the system with high penetration renewables and also with this asset that we have. So these are the aims that we are going to answer during that project. First of all, we want to find how we can allocate size a syncon in the system to tackle the issues that we have in the system and things. All of you know the synchronous condenser are a well-known technology. It's a synchronous machine without a prime mover. They can contribute to the fault current. You know, S5255, they want an IQ contribution for all of this renewable energy system, but as you know, they can just provide 1 per unit current during the fault. But synchronous machine can provide you 5 or 6 times of their normal current. Also, this synchronous machine can provide you inertia. The conventional renewable system based on the IBR doesn't provide you any inertia in the system. Yes, grid forming, they can, with a battery, they can provide you virtual inertia. But if you want the inertia, you need to have a synchronous condenser. Also, they can provide you voltage support in the system. And if you want to look at the power quality issues, yes, the sync of some harmonics are synchronous machine, not only that capacitors are synchronous machine. By removing synchronous machine from the system, you will lose the sync of the harmonics in the system as well. So you may need synchronous condenser on that purpose as well. But they are not a silver bullet point. They have some drawbacks. The cost is a real matter for the syncons. And also the lead time, the time that you can install a syncon in the system. So we want to present an approach to optimally allocate and size a syncon in a system that make you sure that all of the point of connection have a SCR greater than some desirable value, and also the cost of the installation, operation, and maintenance of the syncon will be minimized. We had 2 approaches. One is a meta-heuristic one. The other one is a convex optimization approach. With meta-heuristic one, as this flow chart shows you, you can find a subset of the solution. They are not globally optimized solution, but you can find a solution that makes sure that the point of connection has some SCR greater than desired values, and also the cost will be locally minimized, not globally minimized solution. The objective function can be a cost, or you can add a voltage deviation in the system as well. Different objective function you can add in a meta-heuristic approach. The output of that one will be the location, size, and the number of the syncon. The constraint that we have, the SCR at each point of connection will be greater than desired value. As you know, by installing the syncon, the subtransient reactance will be different in the system, and it will impact the short circuit current at the different point of connection. So these are the impact of the syncon. The other approach is to formulate all of those equations in a convex approach, which is a little bit complex, but we did it. And based on that, you can find and guarantee that the set of the result that you find, they are a globally optimized result, the best result that you can find. The equation is a little bit messy, but the concept is similar to that previous one. The constraint is the SCR greater than some value. And we have just some other constraint to make the equation convex. And the problem set is that the cost will be decreased and minimized in the system. We implemented that method on IEEE 39 bus. We make it a big grid connection, and also we replace some a synchronous machine with renewables, 2 wind farm and 1 solar farm at different points. And when we apply that method with meta-heuristic one and with the convex one, we find the size, number, and the location that the syncons should be connected. We have published 2 papers based on those approach, one with meta-heuristic one with the convex one on IEEE. So you can, I just mentioned them here. But we just evaluate that result also in AMT simulation environment. We model all of these ITRP39 bus and this asset in the system in PSCAD, and we run some tests such as FRT and MFRT to see the performance of the optimized solution. This is a system when we apply fault after at the point of connections, and the three-phase fault is applied, and after fault clearance, you can see that the system is not stable, and we have a constant oscillation, or sustained oscillation on the voltage and active power. So now you can see that this is the result when you have optimized synchron with a meta-heuristic method, and this is a result when you have a synchron in a system with convex optimized solution. You can see that after fault clearance, the system is stable. But you can say that we know that by installing synchron, we will improve the result. But here I show you that if you do not allocate them optimally, in this scenario with optimized size, we just randomly allocate the synchron in the system, and you can see the result. It will not resolve the issue. And also, in the other scenario, we use optimal locations that we got, but with a random sizing, a size less than that minimized, the size that we find with the optimal size. And you can see again, the system has that oscillation, is not recover or right through the disturbance. So if I want to talk about the industrial impact, is that the installation of synchron, based on this study that we did, it should be based on the NSP or renewable energy zones or NEM point of view, not each specific project point of view. Because you can have a different project, you can install synchron, but it is not the right answer for the whole system, for the impact on the whole system. It just, yes, it's okay for that specific project, but how about the whole system or whole renewable energy zone point of view? And we should consider the committed and also upcoming project alongside with the existing project to allocate those synchrons, not only at this stage. We should look at the future as well. So this is the other point that we should consider. And the other thing is that considering the pre-FIA for each project, do in the EMT simulation system. For example, if you want to connect a solar farm or wind farm to the grid, do a pre-FIA before the full GPS package submission. Then you can know that if you need any amendment or system strengthening in the system, it will help the project sooner. Now, in the second one, we want to look at the different thing in the synchrons. Yes, we know that we can install synchron in the system, and there are different well-known or conventional synchrons with the exciter. But we want to look at different in this project. We want to change that exciter controller, and I will explain it. The only controller that synchrons have, they don't have any prime movers or governor and this stuff, but they have exciter to control the voltage at the terminal. Yes, we can use the conventional AC exciter or a static exciter. But in this research, we want to design an exciter which not only make you good and a stable operation of the synchron with that project, but also help the system to remove subsynchronous oscillations, to damp subsynchronous oscillations. For example, if you consider that this conventional ACA1C exciter, we want to replace that part of the controller. I don't know, I cannot zoom it or not. But here, I just put here. Yeah, here we want to replace that main controller with our design controller. For that purpose, we did a data-driven method to first identify a system from the sync exciter point of view. From this point of view, we want to identify the system from this point. So we perturb this point with some pseudo-random binary sequence, and we measure the output here. And based on that, we can identify with some mathematical method, we can identify the system response of that. And you can find detail of that one in the paper that I will mention later. Here we have submitted one paper. When we identify the system, then we can design a controller, a robust controller based on the H infinity norm to satisfy the criteria that we have. So in here, we design a controller. Instead of this conventional controller that we have in AC1C, we replace it with this controller, which I will show you the impact of that controller in some dynamic simulations. And you can see with different orders here, you can see the result with order 4, then we can satisfy that criteria in the H infinity norm design process. You can see here, I had a system, the 400 megawatt solar farm in a very weak grid system, 1.016 was the system strength, the SCR at that point of connection. And we installed that Sync-on. First time we used that default AC1A, and the second time we used our design controller in the exciter of the Sync-on. And you can see this is the HPRT, I have a HPRT event, and this is the POC reactive power here. And also here you can see that we have a VREF step, 5% VREF step. You can see the difference between our design controller and the default AC1A. Yes, if I increase the size of Sync-on, this result will be better, but with some minimum or some small size of Sync-on, if you play with your exciter controller, it will impact your performance. And also we conduct some large signal tests as well. As you can see, after fault clearance with the default exciter and with our design exciter, you can see the response here. Again, the industrial impact of that research, again, I'm just emphasizing on the pre-FIA or full impact assessment of the study, which installation of the Sync-on, because it can interact with your system. And also collaborate with the OEMs that provide the Sync-ons or any other assets, for example, StatCom. We should not use only the conventional controller. We can design the controller based on the issues that we have in the renewable energy zones. So not only the conventional controller. We can think about it, okay, we want some controller to help us with these issues that we have in the system. And at the end, finally, I'm going to introduce an approach to introduce a framework to analyze the stability of the renewable assets and all of other assets in the grid. Normally, we have some index such as SCR and XR ratio to find that the system is the strength of the system. But here we want to introduce a new index to find the stability of the system based on that index. We use impedance-based stability analysis. And in that approach, we divided the system to a source and load from one point of connection that we want. And if you look at this equation, here, this VC considered as our asset, a renewable asset that we have, IBR. Here is a grid impedance, and here is the grid voltage. So if I consider this matrix, which is the impedance of the grid in DQ framework, ZDD, ZDQ, ZQD, ZQQ is a 2x2 matrix. And admittance of this asset, the IBR here, again in DQ framework. And if we have this matrix here, if this matrix satisfies Nyquist criteria, the system will be stable. This is the basic of the impedance-based stability analysis. So the gaps in the research about that approach is that normally for calculate this admittance of the IBR, you need a full detailed understanding of the model inside that one. But because of the IP of the OEM, you don't have any idea what's going on. It's a black box in your system, in your model. You don't have information inside that model. And also, usually they consider just a simple VSC in the studies. And also the other thing, they just only consider the grid as an R and L, which is not the case. Sometimes you have a Sync-on, sometimes you have a StatCom, SVC, which they are not a simple R and L. They have a different impedance there. So our approach is that to, for a black box system, identify this impedance. It's not necessary to know what's inside that black box. You identify the impedance matrix of that one. And then based on that, you conduct that stability analysis and introduce a new index for that. For that approach, for example, consider this is the black box. This is the grid. We perturb here in D and Q axis voltage, and also measure the D and Q current here. And based on that, we can calculate the impedance of that black box method. These are the 4 elements of that matrix. And based on some genome criteria, which is output of the Nyquist criteria for the stability, if G norm of that ZG, the grid impedance, and multiplied by G norm of the admittance of the IBR satisfy this criteria, then for every single frequency, you can show that the system is stable. For instance, if I want to show you some graph here, left side, you can see this SI index that we have, the new index that we have. And this value is less than 25% for each frequency. It means that if in each frequency we excite the system in different frequencies based on some disturbances, the system will be stable. And we just did some tests also. It's a very strong grid here. The SCR is high, and you can see we expect to have that. For that a generic solar farm that we have, 400 megawatt solar farm, we did that study. We changed the SCR and calculated index. You can see by increasing the SCR, this index will be reduced. And also in some SCR, you can see that this index for different frequency greater than 25%, which means that the system will not be stable for that cases if it's excited on that specific frequency. Also, we did some study on the XR ratio impact on that index. With a constant SCR of 2, you can see that in some specific XR ratio, this index will be less than 25%. And in that scenario, the system will be stable. I did that study in here. You can see with a constant SCR of 2, if we don't change the gain of the system and anything in our IBR, by change of the XR ratio, you can see the result here, the impact on reactive power and active power. The SCR are constant, but change of the XR ratio. Also in here, we look at the impact of the synchron on that SI index. We install synchron at the point of connection. Then we identify synchron impedance as well and include it in the grid impedance. And you can see by different size of synchron, without synchron, with a very small synchron, and by increasing the synchron size, you can see that index will be reduced. And in the right-hand side, also I show you something that when the solar farm want to connect, without the synchron, you cannot go to the 400, which is its nominal power, and you have a very bad result here. And then by increasing the size of the synchron, then you can see the IBR response here. Again, I'm just to emphasize about the pre-FIS study that we should do that. We should see the impact on interaction of this IBR with existing project, and in the EMT simulation, not only in RMS simulations. And we can consider this impedance-based stability analysis instead of just saying the SCR as some index for strength or a strong or weak grid. And also, we should consider the XR ratio on the stability issues. We should study the impact of if we change XR ratio. XR ratio will be changed by changing the load, or in different operating point of the system from the point of connection. XR ratio will be changed from that point of connection. So it will impact the stability of system. You can tune your IBR for a specific SCR and XR ratios, but this XR ratio and this SCR will be changed in the system. So it will be good if we consider the impedance-based stability analysis. Thanks, everyone. I'm just happy to answer your question if is there any.
Thank you so much, Sajjad. So as you just saw in Sajjad's presentation, he's been focused quite a lot on syncons and using syncon as a grid strengthening asset. He worked, his work had two separate areas. One was allocation of syncons, where you would install them and what would be the size. You can find two publications on that again on the website that we've got, and also on IEEE Explorer. You can find them out on the website. If you go to our website, you can download those two publications. And the other work was around designing a new exciter system for syncons to provide better performance out of an existing syncon. And finally, the index that he talked about. I believe we've got around 10 minutes before we go to a short break. So I guess we are happy to take questions either from the floor. Yes, Sorel.
Thanks very much for that. A question about the design of the excitation system. Oh, that's going to feed. On the excitation system for the sequence condenser. Did that excitation system that you're looking at, did that include a traditional power system stabilizer? And are you able to see performance better than a traditional power system stabilizer with that excitation system?
No, we didn't consider PSS, but yes, I agree with you. With PSS also, that result will be better with PSS. Yes, yes. I did some study there, but yeah, not. Yeah.
What input did you use? PSS primarily? Is it the standard output power?
Yeah. But you can change that one. You're based on because of that, I said that based on the issues, we can design that controller based on that issues that we have. If you want to stabilize, for example, active or reactive power voltage, you can just change that input for that one. So yeah.
So essentially, the same control approach that we've taken for that exciter can be applied to the PSS. I mean, PSS that we use are fairly, I would call them simplistic controllers, that they're not very sophisticated or high order controllers, but taking such an approach and looking into the frequency response of the whole system at the point that you would like to act potentially can help you to design even better PSSs. And that is potentially an area for us to look into now that we've got this knowledge of designing controllers with this approach. Probably that's a good concept for us to work on in the future. Yeah. No, that's a very interesting problem to look into, and I'm pretty sure that such approaches will have a big impact on improving the performance there and taking more out of your PSS.
Hi.
Yes, Weihua.
Hi, Sajjad. Thanks very much for your presentation. In your last part, you performed the impedance method. So I'm wondering what's the impedance of the syncon like? For example, for the 2x2 matrix, what's the impedance look like?
It's not some symmetrical matrix as well. There are different impact, and in different operating point as well, you will have a different impedance for that syncon as well. So we should consider that one. In one paper that it's my bad, I have not submitted yet, but if I submitted is in that one, I also use some mathematical method to calculate that impedance for each element of that syncon. And also we use the identification method to identify the impedance of that syncon as well.
Okay, thanks.
Quick one, simple one.
I mean that before the full impact assessment at the end of the project, for example, we do conduct some chapter of the NER rules, not all of them for the GPS, full GPS, not full GPS, basic tuning for S554 and fault studies, then give it to the NSP. They can do the PRFI, such as the work I believe the PowerLink now they are going to do. They will see the impact of your proponent in the system with the EMT simulation. And then they found if there is any issues in that system, and you should have some, for example, some assets syncon for your proponent as well in some point. Then you will do the full study after that point. They will find the problem with your proponent sooner before that, for example, going to one after R0 stage, for example.
Is there on the mic as well, so online attendees will, yeah.
So what you're suggesting is in the connection process,
Yeah.
we give an NSP a half completed package and get them to work and find the issue
Yeah.
and get that issue back
Yes,
and
yes.
apply your method and develop the solution. Is it?
Not only my method. For example, they can provide some solution based because they have something. Yeah. For example, you have your project. You will tune it for some purposes, some studies. I believe the PowerLink has a very good document now. They do that approach as well, not full GPS connection. Then they will give you will give them the package with the project, and they will run that study in their EMT environment with the impact of the nearby generation. And if there is an issue, they will provide you some answer. For example, you need some assets or something like that, and then or you may reduce the size of your project. You cannot go with that size, something like that. I'm not sure about that, but we can find the issues earlier. Then they will provide you an answer. Okay, you need that approach. Then you do the full impact. Then you submit your package.
Just one
Sure.
item, just to clarify. Is it because proponent doesn't have access to the wide area model?
Exactly.
All
Yes,
right.
yes.
Okay.
Which is another solution that AEMO is going to introduce, that in the cloud simulation.
Yeah. Thank you.
No.
Hey, one of your recommendations was for sync-on allocation to be more of a holistic approach, looking at the broader network rather than just a project-based response, which it is currently. Do you think that the current approach of project-based sync-ons has potential to introduce issues, or is it just the fact that it's not as optimized as it could be?
First, it's not optimized, but also it can introduce issues because you increase the number of the asset that, for example, in one location, you will have a different sync-ons for different project maybe, okay? And they will interact each other in the controlling the voltage at that point. So increasing the number of controller, nearby controller, increase the control interaction as well.
If I can just add into that, there was a new system strength rule change made recently, and it's now in 2025, it will be the TNSPs, the transmission network operators, whose job it is to get to optimize system strength provision for new connecting renewables. And it'll be the proponent who can choose to either self-remediate or choose to use the TNSP-led solution. So that's trying to overcome the issues, both of the optimization, but also of the potential interactions if you design a site-specific solution. So hopefully that'll improve things.
Yeah, we've got actually a question online. Nabil, would you please read the question for us?
I got a question from Eros. Why sync-ons are considered sync for harmonics?
Because of their structure and the subtransient impedances they have, they are a traditional sinks of some harmonic orders, for example, fifths and sevenths. Not only the capacitor in the system, they are also they can, because of their impedance in subtransient impedance that they have.
Okay, thanks.
No more questions now.
We still have a question, I think.
Yeah, but we'll take that. We'll take that later. Any other questions from our online audience? Please feel free to write questions in the chat. And also audience here in the room, no further questions for Sajjad? Okay, I guess you're right on time to have a short break. So we'll break for probably less than 10 minutes to be back exactly at 10:25. So we'll start the next presentation at 10:25, a very quick 8-minute break, and we'll be back. Okay, I guess it's about time to start our next presentation. Well, the first session was mainly, of course, dedicated to sync-ons, and we saw some interesting concepts about sync-ons. But I guess the rest of the presentations that we'll be having for the day, they'll be focused on inverters, IBRs, inverter-based resources, their control, the interactions, their modeling, small signal, large signal. And we'll be focusing on different types of inverters. We'll be seeing grid following inverters. We'll be seeing grid forming inverters. We'll be seeing a new concept, a new way of controlling inverters. So yeah, from now on, it's all about inverters. Okay, and our next presenter is Dr. Milad Zarif Mansour, and I believe also Dr. Mohammed Hasan Ravanji will be presenting in this one. So Dr. Milad Zarif Mansour did his bachelor and master and PhD all in electrical engineering at University of Tehran, Zarif University of Technology, both in Iran, and Monash University in Australia. He's currently a power system engineer at Oricon, Australasia. His field of expertise includes renewable energy resource integration, power converter control, and power system dynamics. Also, we'll be having Dr. Mohammed Hasan Ravanji presenting today in this session. He has received all of his degrees, BS, MS, and PhD in electrical power engineering from Zarif University of Technology, Tehran, Iran in 2012, 2014, and 2020, respectively. He was a visiting student with the University of Waterloo in Canada from October 2017 to April 2018. Further, he was with the Iranian Grid Management Company, Tehran, Iran, as a researcher in their System Planning and Dynamic Studies group, working on the detection of Iranians' electric power grid weaknesses from the small signal stability point of view. He is currently a postdoc fellow at Monash University, and during his postdoc career, Dr. Ravanji was involved in various tasks and projects, including a project on Australia's Global Power System Transformation Research Roadmap, which was published by CSIRO, and also within the ARENA project that he will be presenting today. So the floor is yours, and I guess Milad will be starting first, and yeah. Okay.
Thank you very much.
Can you? Yeah, it's good. So first of all, I would like to thank the Monash team and also Behrooz for their support throughout my PhD in the last 3 years and a half. I am Milad Zarif Mansour, and today I'm going to present my work on nonlinear stability analysis of grid following converters. I would like to acknowledge Monash University for the facilities and opportunity that provided during my PhD for doing this project. However, I am not affiliated with Monash anymore. I'm a power system engineer at Oricon at the moment. We are going to talk about the motivations and why we are basically doing this research first, and then we are going to a little bit explain what is system strength, grid following inverter control, motivations and outcomes, and also the takeaway messages of this project. So first, we're going to see if what basically we have defined as a project is a real world issue in power systems, or is a kind of fictitious thing that we just came up with 3 years ago in order to get the funding from ARENA. In a couple of seconds, you will see that it's a real issue that we have seen in multiple power systems, in particular in the NEM, and it has caused a lot of outages, system instabilities, islanding, and other things. I really hope that this is the last time that you are seeing this figure today. So this figure in the right shows the places that most IBRs and most renewable energy sources basically are connected to. It is seen that most of these IBRs are connected in remote areas, which are a little bit distant from the main grid. So the overlapping of this IBR places and also the system strengths is showing that this system strength map is for 2021 for last year. It is seen that most of these remote areas are located in the places that has lower system strength. Based on AEMO's ISP, we can see that in a couple of years, when we increase the penetration of renewable energy sources, these remote areas will have less system strength again, or red points are going to increase in the system. And again, we can see that these red points are mostly overlapping with the remote areas with which renewables are connected to. So it's worth mentioning that what do we have in the power system in the NEM at the moment mostly? So we have some solar farms, we have some wind farms. In the last couple of years, we are seeing more batteries being integrated into the system. And we know that most of these farms are connected to the power system with inverters. So there are two most common types of inverter control methods currently employed in real world projects. One of them is grid following inverters. The other one is grid forming inverters. So in grid following inverters, what is happening is that we already have a grid, we already have a voltage, and we are trying to get synchronized to that voltage. If the system strength is not in a very desirable amount, or if we are connected to, that the IBR is connected to a weak grid, it's really possible that we have a failed synchronization, and definitely the system that the IBR is going to be disconnected from the system. In grid forming inverters, however, we are creating the voltage ourselves. We are forming the grid, as it's clear from its name. So we really don't need a pre-existing grid, and as a result, low system strength is not going to impact negatively the synchronization of the inverter. And as a result, if we are connected to weaker part of the system and we are using a grid forming strategy, we are not going to see we are not going to see an unstable system or an unstable inverter. So in this presentation, we are going to focus on just grid following inverter as the most common type of control strategy. So we are seeing more grid forming inverters across the NEM at the moment, but again, I guess something around 80–90% of the inverters that currently we have in the NEM are grid following inverters. And even if we stop using grid following inverters exactly now, there are a very considerable number of inverters, grid following inverters, already in the system. So we need to know that how we can deal with them and how we can assess their stability, how we can improve their stability while connected to weak systems. So it's in this stage, we are going to talk about what is system strength. So we are just keep telling that the system strength is low. We need to enhance it. So what is the system strength? So the concept between behind system strength is that how sensitive the voltage in a certain point is toward changes, perturbations, the small changes in active or reactive power. So it means that if we perturb the active power or reactive power in a point a little bit, if it's going to lead to a huge oscillation or huge change in the voltage, then it means that our system strength is low, or we are connected to a weak part of the system. So this is the concept. So one famous way to characterize this system strength mathematically is using short circuit ratio, or SCR. So SCR is the very well-known index used for system strength. And so if we know the Thevenin impedance seen from a certain point, and if we calculate 1 over the magnitude of that Thevenin impedance in per units, it will give us SCR. So in transmission systems that usually the resistance is negligible, it can be approximated by 1 over the Thevenin reactance seen from that specific point. So we can see in SCR, we are just considering the magnitude of the impedance, and also we are just considering the grid itself. So it doesn't tell anything about the IBR itself, the control strategy, if the IBR is able to remain stable while connected to, for example, SCR to a system with SCR 2, 3. So we know that different IBRs can be different. So one IBR can be tuned for SCR 2, the other one can be tuned for SCR 5, and may not be able to work with SCR 2. So the SCR gives us an understanding of how weak or strong the system, the grid is, but it doesn't provide any information about the IBR and its stability. So a lower SCR means a weaker system, and the weaker. So if you say that the system is weak, it means that the impedance in from that point is large. So we're going to talk about this later in the next slide. So what is the impact? So we know that the harmonic generates, the inverters generate harmonics because they are switching devices. So a high grid impedance or low SCR means that the filter is going to be useless. So the POC, point of connection voltage, is going to be pretty similar to the terminal of the inverter, and that harmonics are going to be propagated to the PLL and other control systems that we are going to talk about shortly. So the distorted voltage is fed back to the control system. So the grid following inverter control. So in this part, we're going to see the control loops, different control loops used in a grid following inverter. This is an SMIP model of a grid following inverter. It has a current controller. It has a PLL, which is responsible for generating the angle used in current control. And also it has a PWM, it has the switch, filter, transformer, and the grid, which is shown as an infinite bus and an RNL. So this is an SMIP model. The PLL, which is probably the heart of the system, is responsible for generating theta, or the angle, is shown in the bottom figure. It's a very common type of PLL named SRF, synchronous reference frame PLL. So it gets the voltage from the POC. So if that point, that POC after the filter is distorted, that distortion is going to exactly be propagated to the PLL. So it extracts VQ, it's regulated to 0, and it generates theta, which is then used in the current control. So if the PLL fails, or if it means that the synchronization fails, and it means that the system cannot inject any active or reactive power, and the control is going to be unstable. So the motivations behind this project is that, so we know that the system, as we saw in the previous slide, this is a nonlinear control system. So it means that if we write the equations of the system, if we write the state spaces of the systems, we can see that it's a nonlinear system. So linear methods are not sufficient anymore. And as I mentioned earlier in the system strength part, we know that the only thing which impacts system strength is not the SCR, or the magnitude of the impedance in front of the IBR. Rather, system strength relies on both the grid and the inverter control, including the PLL. So also, we know that the PLL is one of the main sources of instability in the system. So the reason that that grid following inverters are prone to instability while connected to weak grids is that the PLL fails. So what we are going to do here is that first, we are going to, what we already have done actually, we are going to derive a nonlinear model for PLL-equipped grid following inverters. And then we are going to propose a nonlinear controller in the next stage. We are going to propose a nonlinear controller that expands the PLL's capabilities in order to enable the PLL to be synchronized, to remain synchronized in weaker grids. So starting from the PLL block diagram, we can derive the PLL model. And if we just mix the PLL model and the grid and the information that we have from the grid, like its impedance or the injected currents into the grid, we can derive a model combining grid and the PLL to each other. And then we are going to use this derived model, which is a nonlinear model, in order to assess the stability. In order to do that, the first stage would be linearizing the system model and using the state space modeling. And at the end is basically the stability analysis that I'm going to just talk about in a stage manner. So the first thing that we are supposed to do is finding if in a not so. Nonlinear systems and linear systems are two different types of systems, definitely. So the main difference between nonlinear and linear system is that in linear system, we always have one equilibrium point, and that is for certain that we always have one of them, and we cannot have more than one equilibrium point. But in nonlinear systems, the story is different. We may or may not have a linear, an equilibrium point, And the number of equilibrium points can vary. It means that it can be one or it can be more. So the first thing is that we find the equilibrium points to see if we have any, or if we have the equilibrium points, so what are the equilibrium points? In order to do that, the state space equations should be set to 0. We need to determine which equilibrium point is stable. So in order to, in probably this figure can explains what is an stable equilibrium point and unstable equilibrium point better. So as we can see in equilibrium point 1, so that's an equilibrium point. We know that if we put a ball exactly in that point, it's not really going to fall unless we just push it a little bit. So if we are in an unstable equilibrium point, if there is no external force or external disturbance, we are going to remain in that equilibrium point. But as soon as we just go outside of that exact equilibrium point, or if we just push the states outside of that equilibrium point a bit, we are going to end up somewhere else. So it means that point 1 is an unstable equilibrium point. Point 2 and point 3, however, are stable equilibrium points, because we can see that if we perturb the states, or in this figure, the balls, we are going to come back to the equilibrium point again. So in order to find if the equilibrium point is stable, we just linearize the system. And similar to linear systems that we assess the poles of the system, we just assess the eigenvalues of the system. And if they are negative, it means that the system is stable, that the equilibrium point is stable. But there is also one other important thing here, which is in nonlinear system, which is named domain of attraction. So in linear systems, if we have a stable point, it means if we start from any initial points in the plane, regardless of how far we are from the equilibrium point, we are going to end up in the equilibrium point. It means that the domain of attraction is the whole plane, but here it's different. So here, for example, in point 2 and point 3, you can see that if the force that we are actually applying to the ball is more than a certain amount, we are going to end up in another equilibrium point. So it means that basically the domain of attraction is not the whole plane anymore. So in other words, the domain of attraction is a neighborhood around the equilibrium point that we have, in which actually if the initial conditions are located, we end up and we converge to the equilibrium point. Otherwise, we are going to other equilibrium points or to infinity. So domain of attraction is another important thing that in nonlinear system we need to find. In order to do that, we need to utilize Lyapunov's second theorem. Also, using the domain of attraction, we have proposed a system strength index instead of SCR that includes both the grid and converter controls, named disturbance tolerance, and it's being defined by 2/pi multiplied by the radius of the domain of attraction that we have found using Lyapunov's second theorem. This paper here, published in IEEE, is discussing what I really briefly touched here. So we have done some experimental results and on this, let's say, on this theory. So we have created basically this inverter here in our lab, and we have done some simulations. So in the first simulation, we have increased the output current from 12 amps to 13 amps at t equal to 4, and the expectation is that since the zeta is going from 0.1 to 0, the system should become unstable. So we can see that when we change, so we have just cut the time here, but yeah, so when we increase the current from 12 to 13, the system starts oscillating, and the amplitude of the oscillations are increasing, meaning that the system is unstable. So in the second scenario, we are increasing the inductance of the grid from 7.5 millihenry to 15 millihenry at t equal to 0.08, and the expectation is that again the system becomes unstable because zeta is being changed from 0.1 to 0. So if zeta is greater than 0, and zeta is always less than 1, if zeta is greater than 0, the system must be stable. Otherwise, if it's 0 or negative, it should be unstable. So again, we see that because the zeta is becoming zero, the system becomes unstable after changing the grid impedance, or when we decrease the SCR by increasing the grid inductance. So in the second stage, we have developed.
Can I just add a very quick explanation here? So this zeta, the index that Milad has developed here, so as opposed to SCR, which is an index for system strength, this is again an index for system strength, this zeta. But this not only includes your impedance, but also it does include so many other parameters and variables in your system. And this zeta, when you calculate this zeta for a particular system, can tell you whether your system is stable or not. As soon as zeta goes to zero, it means that your system will become unstable. So just wanted to tell you that zeta is essentially a better replacement of SCR in the system and can very accurately predict whether your system will remain stable or not, because SCR alone cannot. SCR can only tell you, and it gives you an indication how weak your system might be or how strong it might be. But zeta can very accurately predict whether your system will remain stable or not. You can calculate it. There is, again, the paper that Milad showed. You can go through that. It has all the derivations and that zeta there. You can find the equation for that. And you can calculate for every operating point, for every controller in a grid following mode. And again, if it goes to zero, it means that you're unstable. If it is more than zero, you're stable.
Yeah, correct. Thank you very much, Behrooz. So in the second stage, we have developed a nonlinear controller that expands the domain of attraction of the PLL. So we have seen that the domain of attraction plays an important role in the stability of the system when we have large disturbances, actually. So it is very desirable to expand that domain of attraction by means of some nonlinear control methods. So we have, so we are going to again use the same nonlinear model that we derive for the PLL and the grid altogether. And after finding the state space modeling, which is the same state space that we found in the previous part of the presentation, we are going to use feedback linearization technique in order to modify the PLL. So the feedback linearization, in very simple words, what it does, as it's clear from its name, it's eliminating the nonlinearities within the nonlinear model that we have. So from the perspective of an external observer, what we are seeing is a linear model, although inside of the linear model, we have the main nonlinear model plus a nonlinear controller, which is named which is named feedback linearization controller. So the feedback linearization controller that we proposed has some shape like this. X1 and X2 are the states of the system. K1 and K2 are two degrees of freedom that we have, and using those we can specify the poles of the linearized system that we are seeing from outside of the model. And A, B, C, D, and alpha are basically depending on the inverter control and the grid, and also operating point. So we have proposed adding this orange, I would say, is it brown? Yeah, brown block here as our feedback linearization controller. So what we are doing, we are feedbacking IDIQ X1 and X2. So X1 should be estimated, but it's accessible in the paper. And after integrating that U, which is generated at the output of this, the middle brown block here, we are going to add it to the angular frequency. And so what is happening here is that brown blocks here are causing that instead of seeing a nonlinear model for the PLL, we observe a linear model, that the poles of which can be basically changed using that K1 and K2. So except for getting rid of the nonlinearities, we have the luxury of defining the exact dynamics of the PLL that we want to have. So as I mentioned, if we have a linear system, it means that if the equilibrium point is stable, it means that the whole plane is the domain of attraction. So we don't need to be worried about the domain of attraction anymore. And these two figures here are the phase portraits when we don't have this controller in the system, and it shows that the system is unstable. So phase portraits are basically showing the path of the system states for different initial conditions. So in the top one, we can see that if we start from any point, we are not ending up at 0 and 0 or the origin, which is the equilibrium point, because the system is unstable. However, in the bottom figure, we can see that after adding this controller to the system and linearizing it, because the domain of attraction is the whole plane. If you start from any arbitrary points in the system, we are ending up in the equilibrium point, which is the origin. So this is basically, if schematically, what this feedback linearization controller is doing to a nonlinear system, to an unstable nonlinear system. Also, this research has been published in IEEE again. So these are some experimental results. So in the left, we can see that a normal conventional grid following inverter without the proposed compensator has been added to a system with SCR2. We can see that after increasing the power to, or the current to its nominal value, the system starts to become unstable and starts showing oscillations which are not damped, and actually the magnitude is increasing. And in the right, we can see that the same system, while we have the compensator, we do not see those oscillations anymore. And we can observe that the system has been stabilized after adding that nonlinear controller to our system. So about the takeaways and the impacts. So what we did in this project was we derived a nonlinear control method for assessing the stability of the system. Then we proposed a new system strength index that, as Behrooz mentioned, it's comprising of both the grid and inverter control, and it can give you an accurate response whether your system is stable or not, contrary to SCR or GSCR or whatever else that we have basically in the different researches. So this system can tell you if if you ask this question, is the system stable, it can give you the answer of yes or no. So it's not something in the middle. Okay, the system is stable, it might be unstable, or so. No, it gives you an absolute answer. And finally, we derived a nonlinear controller that can expand the confined domain of attraction of conventional PLLs to the whole plane, and causing it much more robust toward different disturbances, and regardless of their magnitude, basically. And yeah, so we can use this stability analysis basically, and the index that we have derived to for the system planners and operators, and that is definitely gives a much better insight to them in terms of the stability of the system. And this developed nonlinear controller definitely is a very powerful tool for OEMs and developers if they are interested, in order to enhance the PLLs and the synchronization. So this research has been done for an SRF PLL. I understand that it's not probably the PLL that many OEMs and developers use, but it's just a kind of prototype, so they can adjust it based on their PLL and adjust it. So, but the idea is going to remain there. So thank you very much. I am more than happy to take any questions that you might have.
Yeah, I guess we were supposed to have two presentations, but let's take questions for this while it is relevant. If you please unmute yourself, hopefully there wouldn't be any feedback.
Thanks very much, Milad. A question just regarding your system strength index. What data does it take as inputs? For example, is it something that needs to know controller internal parameters, or is it something that, you know, is very much considering an arbitrarily large power system, is it something that can be derived from, say, the physical characteristics of the network and simple machine parameters, etc.?
Okay, so the key for finding that system strength is that we can put everything together in order to form that state spaces that we derive. So yeah, regardless of what we have in the grid network side, we can always find a Thevenin equivalent of the network. Or I know it might not be very accurate, but anyway, we can approximate the rest of the network from the POC of our inverter by its Thevenin equivalent. But what is more important here for us is having information about the PLL parameters. So it is it's crucial for us to know what is the structure of the PLL and what are the parameters. For example, in our case, SRF PLL, we must know what are KP and KIs used in that PLL. Probably this is a very good tool for developers because they know what is inside of their PLL, obviously. So it's a very powerful tool for developers because they can get a Thevenin model from the TNSP or whoever is responsible. And they can also employ the parameters that they have for their PLLs, and they can derive this zeta, which is actually a function of the radius of the domain of attraction.
Any other questions for Milad? And do we have any questions online?
Yeah, we do have one.
Can you please read it for us?
Can the proposed dominant of interaction-based stability index incorporate multi-IBR controllers that would interact across the network, or does its derivation necessitate representation of the rest of the network as a Thevenin equivalent impedance and the voltage source?
So basically, we have not done in our research, we have not considered two IBRs, but conceptually, it should be possible to do it. So the only thing that you need to do is, so because the equations that we have derived, the states equations that we have derived are written in the DQ frame of that specific IBR. So if we have two different IBRs, we will have two different DQ frames. So we need to choose one reference DQ frame and write all these state equations in that basically that general or that the frame that we are choosing as our reference. So instead of two states, which we have for one inverter here, we will have then 4 state equations, and we will have a 4x4 system, for example, if we are assessing 2 inverters plus the grid. And yeah, so so there is a concept in power systems and control named participation factors. We can use those participation factors to see what is the impact of each mode on the other modes. So for example, what is the impact of the theta in IBR1 on the frequency in IBR2? Yeah, so it's possible to do it, but it means more a mathematical burden, and it's definitely tougher to do.
That's right.
No other questions online?
No.
Any? Yes, go ahead.
So taking all of that into account, can you see this being turned into some kind of real-time operational stability index tool for the NEM?
So it depends. It depends on how probably powerful AEMO is in order to getting information from the developers and OEMs. Until now, they have done a great job. They could get many things from them, but it's really, I guess, necessary to. So the OEMs and developers really do not need to give the exact PLL model to anyone, but they can give an equivalent SRF PLL model, for example, to AEMO or any other party which is responsible for assessing this stability. But yeah, so if that information can be provided to anyone who is responsible for the network management and have information of the network, yeah, I would say it's really possible to use it even in a real-time manner too, because it's just 20 lines of code probably in order to find that zeta for each inverter, provided that we have information about the synchronization unit.
We do have a question online.
Yes, please go ahead.
How can we integrate system strength calculation with dispatch? As we know, a field in system strength can be passed if a synchronous unit is dispatched next to the inverter and vice versa.
So from the distribution, so what was that? So can you
he meant like focusing how we can integrate system strength calculation with the dispatch units.
Okay, so I would say that zeta that we found here is also a function of the operating points, or in other words, how on basically what is the output active and reactive power from the inverter. So it's a kind of the dispatching of that specific inverter. So if we change the injected active and reactive power, that zeta may change, as we saw in one of the experimental results. When we increase the current, zeta changed from 0.1 to 0 and caused instability in the system. So that in the dispatching part, we definitely can, if we have information about zeta, we can see what is the maximum amount of active power outputted from that IBR that does not lead to a 0 zeta in our system. So that is how we can use it in real time for stability assessment in the dispatch part. Yeah.
And if I can just add to that, I feel like the rules guy, but there's a new rule coming in, being made on the 1st of December, and it's called the operational security mechanism. And AEMO will need to do exactly that in real time. So there's pre-real time, there's going to be a second market that runs alongside the spot market, and it'll be a system security optimization. And it will need to work out exactly what is required to keep the system secure, and that will then feed into what units are required to be online. So I think it's a super good question, because it will need to be implemented in October 25.
Right.
So a bit of work to do before then.
Thank you.
Okay, maybe we can thank Milad for his beautiful presentation.
Thank you very much. Thanks.
And our next presenter, Dr. Ravanji, will talk about impact of PLL dynamics and grid strength on stability and output power capability of inverter-based resources.
Hello, everyone. I'm Mohammad Hasan Ravanji, and I'm very glad to be here to talk about some of our findings in this project, the Stability Enhancement Project. I have 2 presentations today. One is mainly relating to grid following inverters, the presentation right now I'm going to talk about, and also another presentation in the afternoon about providing grid forming capabilities for wind farms. So for the first one, I mainly want to talk about grid following inverters. And in some parts, since I'm going to say that one way to improvement is employing grid forming capability, grid forming modes, I will touch grid forming here a little bit. But the main concentration focus here is grid following mode. So as you can see, the title is to considering the PLL dynamics and also grid strengths, 2 factors on the stability, the same thing similar to what Milad talked about, but in another way of explanation. And also I will talk about the output capability curves of inverters and what's the relation between these limits and the OCC output capability curve for IBRs. So first of all, similar to what my colleagues explained, I start with the evolving power system. We have a transition from synchronous-based grid to IBR-based, inverter-based resources grid. And as you can see in the right-hand side of this slide, we are expecting an increase to 100% penetration. But the focus of my presentation here is not the final goal, but my focus is on the shaded areas here. As you can see, it says that we may have some constraints to reaching to that point. And my part here is to show that why we may have these constraints, what are the reasons, and how to address them. So we have different types of limitations and constraints when we are going to go to 100% IBRs. In this specific presentation, I mainly focus on synchronization issues. I want to categorize the issues in 2 different distinct groups. The first one, constraints caused by network, which is the grid strengths. My colleagues talked about it, but I want to formulate it and show it in another way. And also some constraints are caused by the IBR itself. I mean IBR control system, which is again the PLL impact. Why I'm really interested in this topic? Because if for very high penetrated levels of IBRs in our grid, First of all, if we have installed some farms, we may cannot even operate and at nominal power, which is not desirable at all. And also, it may limit us to integrate more farms while we want to go to 100% penetration. So in this study, first, we try to quantify these constraints and then propose some solutions. As I said, the tool I'm going to use in this study is OCC. The reason I'm going to use this tool is that in the study we have done, we had several of equations, which is not really good to explain them in such a session. Instead, I want to use graphical things to explain all of these equations. As I said, OCC is a tool showing the permitted operating region for any generating unit in a system. If we, for a very first step, if we assume, if we consider any type of generating unit, the first limit we always have is the thermal limit. If we formulate it as I showed in the slide, the region of operation, the OCC, would be such a circle, limited circle. Now, this is very simple. Now, what if we talk about a synchronous generator? For synchronous generator, we have several other limits rather than thermal limit. I've just plotted some more important of them. As you can see, we may have some limits from turbine itself, the energy resource, in fact. We may have some limits from the excitation system. We may have some limits from the armature and so on. So instead of that circle, we have a more limited area, which is well known in the industry. Now the plan is to find such a curve for an IBR. And the point is, for an IBR, the mode of operation, grid forming or grid following, has impact on this specific OCC curve. So let's start from this system. My friend started a SMIP case of an inverter connected to a grid, a very simple study case, which is enough for this type of study. Here, I'm gonna talk about the limits we should consider in the study. As I said, we have two categories. One, limits caused by the inverter itself. As you can see, we may have thermal limits, we have PLL stability limits, and also we may have energy resource limits. Also, we may have some limits caused by the grid. The main important ones are voltage limits and the static limit. We have provided equations for all of them. I'm not gonna go through these things at all, but I'm just gonna talk about two more important things here. First one is PLL limits. Milad talked about this in detail in the previous slide, so I'm just gonna show the outputs in my slide. But the other thing is the static limit. The static limit caused by the grid. If we look into the equations for a grid, a simple grid like this, assume that our grid following inverter just is in QRF0 mode. We've shown that the maximum power reachable for this IBR follows such an equation. This equation shows that if the grid is inductive, XR ratio is very high, then for SCR less than 2, we cannot even have the maximum, the nominal power, which is a limit. So for a very weak grid, when QRF is 0, grid following inverter cannot even transfer its nominal power. However, when we inject reactive current, we can increase this P with the equation provided in our paper. More details can be found in the manuscript I mentioned here. This manuscript is still under revision, but I can say that I'm very hopeful that this paper is will be published maybe in the next 1 or 2 weeks. And when it's published, we will put it in our website. Now, so we have 5 limits. If we plot the OCC based on those limits, we would reach to a OCC curve like this. You can see in the slide, we have a thermal limit, the circle one. We have limits comes from the PCC voltage. We have energy limits. These are similar to what we saw for the synchronous generators. However, we may have a limit for PLL, as you can see in the purple line. and also a limit as the static coming from the grid strength. For this specific scenario, you can see that those limits, if QRF is 0, are not activated, meaning that Pmax is not, P nominal is reachable, and you can reach to that point. However, assume a weaker grid. We can show that with equations that when the grid is weaker, that trace showing the static limit goes up, meaning that the OCC is more limited, and in some cases, CR less than 2 for inductive grid, for instance, Pmax at Q0 is less than P nominal. Also, if the PLL is purely tuned, for our case, the curve shown goes to left, and it also can limit the OCC. Now, let's have a look at the impact of control mode. For grid following, we usually control it as a constant Q generating unit. As you can see, if reference is 0 for the worst case I showed in the previous slide, the trajectory would be a straight line and is limited to powers less than nominal. However, as I said, when we increase reference for reactive power, we can go to higher active power. We can reach to the nominal value. However, if this Q is too much because of the thermal limit we have, we still cannot inject the nominal power. So we have a optimal value for reactive power to be injected for a specific case. We proposed a control system which can provide us the reference for Q and let us to maximize the static limit we may have for an IVR. In this figure, this box shows the conventional grid following, and this part is what we've proposed in the paper I discussed previously, which gives us how we can maximize our maximum static limit. As you can see here, we need to estimate the grid. For the grid estimation, there are several methods. I'm not going to talk about it in this presentation. We have some presentations later today, which will cover this topic. Then using the blocks shown here, we find the optimal value for reactive power reference, which I'm not going to talk about it now. I refer you again to the paper. Now, we want to talk about the solutions. The first one was a solution, how to resolve the issue of low SCR. Now, let's talk about solutions for PLL-induced operational limit. First of all, since we can see that when we change PLL gain, we may limit the OCC, one solution would be retuning the PLL. But retuning the PLL is not the best way because it would be dependent on the grid strength, and we usually don't do it every time. We just tune a PLL when we commission the system, and we won't change it anymore unless we use an adaptive way, which is not which wasn't in the scope of my study. The second way is going to use PLL-less structure. For PLL-less structure, I can talk about two things. The first one is using power synchronized grid following control. This is a new method. This is a proposed method by our team, and we would have some presentations today later about this specific structure. Milad, Behrooz, and Nabil will talk about this specific idea later. And also, the other way is using grid forming controller. I will show in this presentation that employing grid forming control also improves those limits. And there's another way of improvement is PLL passivation. This is a very specific way, which Weihua, one of our colleagues, will talk about it later after me when I finish. Now, I'm going to talk about grid forming mode. So right now, I provided grid following limits, OCC for the grid following. Now I want to show the grid forming limits as a solution. If we do again all the steps we've done for the grid following inverters, we again have two types of limits. Some limits comes from the inverter itself, but here we don't see any limits because of PLL, because we don't have any. But the equations here are different from what we had for grid following. For instance, if we look into the static limit for grid forming inverters, the equations is completely different. And the point here is that if the grid is again inductive, XR ratio is very high, you can see that that limit we had before for grid following, which was SCR less than 2 was problematic. Here is SCR less than 1, which means the situation is much better. For SCRs between 1 and 2, we don't see any limits for grid forming. If we plot OCC for grid forming again, we don't see any impact from PLL, and this is the OCC of a grid forming. Now, showing these concepts, I'm gonna just represent some validation results. But before that, sorry, for grid following, I showed that when we are in reactive control mode, the trajectory is straight lines. But for the grid forming, since we usually control grid forming as a PV generating unit, active power and voltage control unit, we can see that the trajectories are different. However, with these trajectories, we can reach to nominal power unless reference is too high, which is not the case. We usually don't do that. Now let's go for verification. We started from a MATLAB Simulink. We implemented a battery system, grid forming, inverter system in both grid following and grid forming mode in simulation. And also we have verified our results in our lab with real inverters. I'm gonna show 6 cases for the verification. First of all, simulation results. The simulation results are for a 1 megawatt battery system. In the first case, it's a grid following inverter connected to a strong grid, SDR more than 3, and the PLL is well tuned. You can see that we can increase active power to the nominal value. We don't have issues. However, when it's the worst case scenario, meaning that the grid is weak and the PLL is minimally tuned, we can see that we cannot even reach to 0.6 per unit, which is not desirable at all. However, when the blue line in these curves showing the maximum Pmax static, we calculated based on our equations, and you can see in case 1 we never touched that limit, so everything is fine. In case 2, we are not touching that limit, but still the system is unstable. It's because of the PLL impact. In the third case, since the PLL is well tuned, we can go to higher values. Again, the static limit is the constraint here, and we cannot go to 0.8 anymore. Now, if we use our proposed controller, it improves the situation. But the point is, since our proposed controller considers the thermal limit, because of that, the reactive current injection is not the value that can stabilize the system for 1 PU because of the IBR thermal limit. So we can go to the maximum available value, which is similar for grid forming case, because for the grid forming case, while the system is stable for 1 PU, however, the reactive current, the needed reactive current is too high, too much, which means the thermal limit is violated. We also, in the 6th case, we showed that the system is still stable for lower voltage reference because we talked about the impact of voltage reference on the stability. And still we have the thermal limit violation. We also, as I said, verified our results, our equations, and our findings with experiments. We tested a 2.2 kilowatt battery system in our lab. The results are similar to the simulation results. So for the first case, the system is fine. For the second case, because of the PLL, we cannot reach even to 0.6 PU. But when we tune the PLL, while we can go to higher values, still because of the static limit, we cannot reach to the desired value. Here, I just showed some results from our scope, experimental results for the same cases. And for case 4, when our proposed controller is used, we can go to a better level. Still, because of the thermal limit, we cannot reach to 1 per unit. For case 5 and case 6, the same things happens. We can go to 1 PU. However, the amount of reactive current required are more than the thermal limit of the system. So we have violated the thermal limit. Now, what are the outputs and impacts of this study? There are some, as I explained, there are some constraints for reaching to 100% renewable in a grid. And in this study, we considered synchronization issues. we categorized them in two categories. One, issues, limitations comes from the network side, and some constraints come from the IBR side. Grid strength for the network side and control system for the IBR side. For the IBR control system, mainly issues come from PLL, which we showed you can use several methods to compensate for it, retuning the PLL, also switching to PLL-less controls, and PLL passivation. For the network constraints, since it mainly comes from the grid strength limitation, you can use our proposed auxiliary controller, or you can use grid forming. Grid forming has two benefits here. First of all, as I showed in this presentation, we already have higher maximum transferable power capability. And the other thing is grid forming itself improves the grid strength, meaning that it is beneficial for the system in terms of the limits. And that's it. Thank you very much for your attention. I'm more than happy to answer any questions.
Yeah, thank you so much, Mohammed, for this very interesting presentation outlining different limits that we've got in IBRs. I guess hopefully this study will be available online on IEEE very, very soon. Very interesting and insightful study, I would call it. And yeah, so questions from the audience and online. Yes, Phil.
Does that switch it on?
Yes.
Thank you very much for your presentation. I can't follow all of the theory, but that's okay. However, by the way, my name is Phil Cravell. I beg your pardon. I'm an energy writer. It tells me we are ripe for a new industry in this country, building inverters for world markets. I wonder if that's under discussion, because we are leaders in Australia. We are faster adopters than anybody else. And when I listen to all this research, I'm thinking, why aren't we building this stuff here?
Very valid point.
It's a very good question. Very good question. Yeah, I mean, we sure can, and we probably should. We probably should. I mean, the thing is that we have been relying quite a lot on international OEMs, obviously, well, there are very capable international OEMs operating in the Australian market, but unfortunately, we haven't developed or we don't have yet any OEM operating in this space in transmission networks. We do have some for distribution networks, and they're doing a good job. But for large inverters, unfortunately, yeah, we don't have any OEM in Australia, and that's something that we probably need. I don't know where we should start or how we can start or what can be done, but it's probably something that we need, because as you rightly mentioned, we are leading this in Australia. We've got all sorts of problems in Australia, and we are leading the way. So why don't we build them here?
May I make a final comment? It's rather impassioned. Building inverters is mainly brains and assembly work from established components, unlike building synchronous generators and turbines. So we really we have it in our grasp to do this.
That's right. No, I agree with you. Well, to add to this, in our lab, we also build inverters. So we also have actually capability of building inverters, but the applications that we are working on are for electric vehicles, and we build inverters for electric vehicles or lower power, but nothing stops us from going to the larger power. It's only like higher current, higher voltage, higher rated switches. So yeah, I mean, it's all possible. Ariel.
So I had a question, but I'll just comment that I think that's a great point. And we do have at least one really quite successful inverter manufacturer, not on the large scale, in Victoria. which we work with Electronics. So
Oh, yeah,
maybe we should
absolutely, yeah.
talk to them and say, what do you need to scale up and get this stuff going, which is in fact something that we are in some kind of conversation with them already, but not on this point. My question is around the interaction between system strength and frequency, fast frequency response or other services that or other capabilities that the virtual synchronous generators can provide. Can you comment on that at a high level? Is there trade-offs? Is there do we need more research to develop algorithms that can do both at the same time, etc.?
That's a good point, but just I want to mention that in this specific presentation, since the timeline I was looking is a little bit different, that's why you don't see any studies about frequency stability here. We have some presentations in the afternoon. I believe Dayan himself, one part of his presentation will cover this with more details. I can refer you to that presentation. I believe it's better to let him explain about this because this study is not relevant to that. Sorry for that.
Do you have any online questions?
No.
No online questions. So, yeah, our online attendees, please go to the Q&A part on the webinar. And if you have any questions, please do ask questions there. If you don't have any other questions here in the room, we probably can break here for a very short break. We are a little bit behind. Instead of a 10-minute break, we can probably make it a 5-minute break just to stretch your legs, and we come back for the next presentation before lunch. Okay, so in 5 minutes, we'll be back. Okay, I guess we are back in the room and we can start with our next presentation, which is on modeling, analysis, stability enhancement, and impedance measurement of PLL-based grids following inverters. So the next speaker is Dr. Weihua Zhou. Dr. Zhou received the Bachelor of Engineering degree in Electrical Engineering from the Honors College Northwestern Polytechnical University, Jian, China in 2014, the Master degree in Electrical Engineering from Northwestern Polytechnical University in 2017, and the PhD degree in Power Electronics from the Department of Energy Technology, Aalborg University, Aalborg in Denmark in 2020. From August 2020 to November 2020, he was a visiting scholar at the Department of Marine Technology, Norwegian University of Science and Technology. In 2021, he was a postdoc fellow at the Department of Electrical Engineering, KU Leuven in Belgium. He is currently a postdoctoral research fellow with the Department of Electrical and Computer System Engineering at Monash University, Melbourne, Australia. His research interests include modeling and control of power electronic converters, energy storage systems, and stability analysis of power electronic and underground cable-based modern power systems. Weihua, the floor is yours.
Hi, good morning. Today, my presentation is the modeling, analysis, stability enhancement, and impedance measurement of the PL-based grid-fault inverters. My presentation focuses on the PL-based grid-fault inverters instead of the grid-forming inverters. My presentation includes the following maybe 5 parts. As you can see, in the first part, I will introduce the background, and then I will introduce the comprehensive modeling of the grid-fault inverters, including the impedance models and the status space models. And then after we have the models, we will perform the stability analysis and further the stability enhancement of the grid-fault inverters. Finally, I will show how to perform the impedance measurement of the inverter-based power systems from the single inverter to the multi-parallel inverter systems, and further to the large-scale power system. Okay, firstly, I will introduce the background. As you can see in the previous presentations, my colleagues already show a lot of this. I will quickly go through this. As you can see in the right picture, currently, the conventional synchronous generators have been gradually replaced by the power electronic devices. So in this case, we have many power electronic devices. And in this case, the power system is dominated by the power electronic. So this is called power electronized power systems. So different from the conventional synchronous generators, for the grid fault inverters, we have many control loops. For example, as you can see from this figure, we have the PL is the very basic part which is used to track the phase angle of the PCC voltage to inject the desired power. And we should also have the inner current control loop. Optionally, maybe we can have the outer, for example, volt control. Specifically, as you can see, we can use the DC link volt control to control the DC link voltage. We can have the PCC voltage control loop to make the PCC voltage constant. And of course, we can also use the power control loop, for example, the active power control and the reactive power control. So, but you know, because these control loops have different bandwidths. So as you can see in this figure, for the outer power control and volt control, the bandwidth it can be very low. For the PL, it can be maybe 100 Hertz. But for the current control loop, maybe it can be 1 kilohertz. So it means that the control is maybe separated over the very wide frequency ranges. So in this case, when the grid fault inverters are interacting with the weaker grid, maybe wide band instability phenomenon can happen. For example, as you can see here, low frequency instability phenomenon can happen if the outer power or volt control loop interact with the weak grid. And high frequency harmonic instability phenomenon can happen if the inner current control loop interacts with the weak grid. Here, I would like to introduce some practical low frequency instability phenomena in the real world. As you can see here, the first accident is that the AEMO observed 7 Hz RBR related oscillation in 2015 with 5% peak-to-peak volume. In addition, in 2020, 9 Hz RBR related oscillation happened, as you can see in this figure. In addition, as you can see here, in China, there is a low frequency 30 Hz oscillation event happening. And this one is the Hydro 1 20 Hz oscillation event. And this one is the Texas 4 Hz oscillation event. And this one is a new accident. This is the Dominion Energy 22 Hz oscillation event. Actually, there are also many other low frequency instability phenomena. If you are interested, you can read this reference. This is early access. Okay, so in conclusion, to guarantee the power system small signal stability, we should firstly try to develop some stability analysis method and small signal models to review the instability phenomenon. And based on this, we should develop the stability enhancement strategies. So firstly, we should adopt some stability analysis methods. Up to now, we have 2 popular stability analysis methods, as you can see. One is the status space method, and the other one is the impedance method. For the status space method, firstly, we should theoretically derive the full order status space model. And after we have the status space model, we can calculate the eigenvalues. And based on the eigenvalues, we can say if the system is stable or unstable. And this model is, this method is mainly popular in the power system community. When the power system is dominated by the synchronous generator, we derived the model for synchronous generator's power system. As you can see in this figure, I provided one demo of the status model. As you can see, when we decrease the ICR, the dominant eigenvalue moves to the right half plane. As you can see, when the ICR equal to 0.8, it's unstable. And as you can see from figure B, from 4 seconds to 6 seconds is indeed unstable. Specifically, when we perform the FFT from 4 seconds to 6 seconds, we can see it oscillates at 4 Hertz. And if we calculate the oscillation frequency from figure A, it's indeed 4 Hertz. It means that the eigenvalue analysis method can accurately predict the instability behavior. The advantage of this method is that it can easily locate the instability source based on the participation factor analysis. For example, if we calculate the participation factor for this unstable eigenvalue, we can find which part contributes to this instability phenomenon. After that, we can obtain the whole system stability picture, and then we can maybe retune the critical controller parameters to make the system stable. However, as we can see, for example, for the practical larger scale power system dominated by the inverter-based resources, maybe there are millions of inverters. It means that if we derive the whole system status space model, the order can be very high. So it is very difficult to calculate the eigenvalues. The other one is that sometimes we even cannot do this because of the unknown IBR internal topologies and the parameters. So if we don't know what's inside the inverter-based resources, we cannot derive the status space models. I think it's very common in the industry because most of the IBRs are black boxes. So on the other hand, maybe we can use the impedance-based stability analysis method. So different from the status-based method, for the impedance method, we can, on the one hand, we can theoretically derive the impedance model based on the white boxes. On the other hand, maybe we can measure the impedance of the black box IBR. For example, we can inject the perturbation at the terminal and observe the response. So after we have the terminal impedance frequency responses, we can use the we can plot the Bode diagram to assess the stability. It's mainly popular for the power electronic community. Here is the one demo. As you can see in figure A, we have the impedance for grid fault inverter and the grid. The blue line is the grid, and the black line is the inverter. As you can see, they interact at 14 Hertz, and the phase angle difference is larger than 180 degrees. That means that it should be unstable at 14 Hertz in DQ domain. So in other words, in ABC domain, maybe it should oscillate at maybe 64 Hertz. So here is the time domain simulation. As you can see, it oscillates at 66 Hertz and 83 Hertz. So here is the demo. And as you can see, the impedance method does not need the internal information. And the stability margin can be easy to observe. As you can see, we just observe the phase angle difference at the magnitude interaction point. However, we cannot provide more insights into the instability source location because the grid fault inverters are regarded as the black boxes. So it means that we don't know which part contributes to the instability. And because if we use the impedance method for the larger scale power system, we divide the whole system into 2 parts. It means that maybe many inverter dynamics are aggregated. So we can only assess the assessment node stability. In other words, we cannot draw the whole system stability picture. So after the background, I would like to show my work for this project. As I say, firstly, to review the instability phenomenon, firstly, we should have the model. So here I comprehensively derived the grid following inverter small signal models considering 11 control strategies. As you can see, in this work, I focused on the effect of different out control loops. As you can see in the left figure, we have the basic circuit and inner current control and the PLL. And the current control loop and the PL are shown in figure A and figure B. But alternatively, for figure C, D, E, F, G, they are the different out control loops. So in this project, we focused on the effect of these out control loops on the low frequency stability. Here we performed a comprehensive literature review for the grid following inverter topologies study. As you can see in this table, we summarized the control strategies into 11 kinds. And I think several of them are popular control strategies. For example, control mode 2 and control mode 7 and control mode 9. But anyway, we comprehensively summarize the control strategies and derive all of them to provide some insights. So here is the summary of the studied 11 control strategies. For example, in control mode 1, we only consider the effect of current control loop. It means that we even ignore the effect of PLL. In the control mode 2, we simultaneously consider effect of current control and PLL. And in control mode 3, we consider the effect of current control, PL, and open loop power control. And similarly, we have 11 control strategies. So I will not introduce how to derive the status space model and the impedance model. I just provide the verification of these models. As you can see in this figure, in figure A is the time domain simulation verification of the derived status space model. For example, at 10 seconds, we change the current reference, and we can see the theoretical waveform obtained by our model agree with the simulation results. Similarly, we also change the Q-axis current reference at 20 seconds. You can see the derived model is very accurate. And in figure B, we can see the solid line are the derived theoretical models. And the dotted lines, for example, the YVSC1, MEA1 is a frequency scanning results. So you can see for 3 cases, all of the frequency scanning results agree with our derived model. And we can also provide some insights. As you can see here, if we increase the current control bandwidth, we can see for DD and QQ axis admittance, the magnitude is decreased and the phase angle is increased. So this is the effect of the current control parameters on the admittance. And as you can see here, this is for the control mode 2. You can see in this control mode, we simultaneously consider the effect of inner current control and the PLL. So we can easily compare the 2 figures. We can find that if we further consider the PLL, we can say for QQ axis, the phase angle starts from 180 degree. But if we don't consider the PLL, you can see here in the left figure, it starts from 90 degree. So it means that because of the phase angle is above 90 degree, so when the when the grid is weak enough, the instability may be happening. So you can see, for example, in this figure, maybe up to 9 Hertz, the phase angle is above 90 degree. But But if we, you can see, if we increase the PL bandwidth, you can see the phase angle is increased. It means that the instability will be degraded. I think this is the insight about the effect of the PL bandwidth on the low frequency stability. And we also, so you can see we also decrease the current reference. You can see it can also reshape the low frequency admittance of the grid following inverter. So it means that the operating point can affect the stability. Here is the summary. And as you can see, we also compare the admittance feature of the control mode 3 and control mode 6. For these two control modes, the difference is that for control mode 3, we consider the outer open loop power control, but for control mode 6, we consider the closed loop power control. So as you can see, the admittance feature is different. You can see for open loop power control, the YDD phase angle is 0 degree. You can see here, it starts from 0 degree. And it can be constant. It means that the DD axis behaves as a positive resistor. However, for the closed loop power control, as you can see, the YDD phase angle starts from maybe -90 degree. Minus 90 degree, as you can see for YDD. So it means that the closed loop power control makes the grid following inverter behave as inductor. So I think this is the effect of different outer power control on the low frequency admittance feature. Okay. In addition, we also provide the admittance of control mode 7 and control mode 8. As you can see, the difference is that for control mode 7, is controlled by outer DC link volt control, but for control mode 8, it's controlled by outer PCC volt control. So it can be seen for control mode 7, you can see for YDD, the phase angle is 0 degree, and the magnitude is constant. So it means that YDD is a positive resistor. However, for PCC volt control, as you can see, this doesn't affect the admittance feature. It means that the admittance feature is the same as that we didn't consider the outer PCC volt control. Okay, here is a summary for the 11 control modes, as you can see here in this table, and some highlights are here. One is that the PL enforces the QQ axis admittance to behave like a negative resistor at the near zero low frequency point. So this is why the grid following inverter is unstable under the weak grid condition. In addition, the admittance feature is not affected by the outer control loop, which provide the reactive current reference. For example, the PCC volt control and the reactive power control. But the outer active power control makes the DD axis admittance at the near zero frequency point behave like an inductor. And both the open loop power control and the outer DC link volt control make the DD axis admittance at the near zero frequency point behave like a positive behavior. It means that because a positive resistor helps to damp the low frequency instability. So it means that maybe the open loop power control and outer DC link volt control is good for the low frequency stability. Okay, here we performed some experiments for the different grid following inverter control strategies. Here is the scaled down experimental setup. And you can see for the 4 figures, here we use different ACC, this is the current control bandwidth. We have four current control bandwidths, and we didn't consider any outer power or volt control loop. As you can see, for each configuration, one pure power cannot be injected because of the PLL. But you can see the effect of the inner current control bandwidth. When we increase the inner control bandwidth, you can see maybe if we increase from 355.2 to 532.8, you can see the maximum power is increased. You can say it's increased from 0.2 pu to 1 pu. It means that maybe a larger current control bandwidth is good for the maximum power transfer capability. So next we consider the effect of the outer closed loop power control. As you can see here, if we use different closed loop power control bandwidth, the stability feature is different. For example, if we use the larger power control bandwidth, the maximum power transfer capability is increased. For example, if we use this bandwidth, the 236.8, the 1 pu can be injected. I think now I think the performance is satisfying. And here we also provide another test. The difference is that for the right picture, we use a larger current control bandwidth. But similarly, as you can see here, if we use larger power control bandwidth, the maximum power transfer capability is increased. Okay. So up to here is the modeling and the stability analysis of the effect of different out control loops, including the volt control and power control. So next, because we already have the verified status spread model and impedance model, we can propose some stability enhancement strategies. As you can see, here is the single line control structure of the peer-based scaffolding model. In this project, we only focus on the effect of the PLL, and we didn't consider the out power control and volt control. So here is the configuration of the studied topology. And because as I introduced, because the PLL makes the phase angle above 90 degrees. So our motivation is that if we propose this PL passivation module and insert this module into the figure, maybe we can make the grid impedance, grid fault inverter impedance to be passive. It means that maybe we can limit the phase angle within minus 90 degree and 90 degree. So if the phase angle is not above 90 degree, so no matter how weak the grid is, the stability can be always guaranteed. So this is our motivation. I will not show how to design this PL passivation module because we should use maybe very long equations, but here I just show the reshaped impedance. As you can see here, the black line is the admittance without using our PL passivation module, and the red line is the impedance using our developed PL passivation module. As you can see, for YDD and YQD, the two axes is unchanged because PL doesn't affect the two components. But if you can see YQQ, previously the phase angle starts from 180 degree. But if we use our proposed PL passivation module, it's not more than 90 degree. So it means that the stability can be improved. And as you can see, we have two case studies. For figure A, this is for low active power, but for figure B, we have increased the active power. So it means that even we increase the active power reference, we can still make the phase angle lower than 90 degree. So it means that it can work on the different power injection. Similarly, as you can see, we also change the current control bandwidth to test our performance of the proposed PL pacification module. As you can see, for different current control bandwidth, even with double the PL current control bandwidth, the performance is good. You can see from the red line for the two figures. For YQQ, it's always below 90 degrees. The last test is that you can see, I think this one is the one more important test because we change the PL bandwidth. You can see if we increase the PL bandwidth, the phase angle can be always below 90 degrees. But if we don't use the PL pacification module, as you can see in figure B, I think the instability phenomenon can happen up to 10 Hertz because up to 10 Hertz, the phase angle is above 90 degrees. But if we use the PL pacification module, you can see the admittance, I think is very good. So here, after we test our proposed PL pacification module from the perspective of impedance, we can show the performance using the eigenvalue and the time domain simulation. As you can see from figure A, if we don't use the proposed PL pacification, you can see from the black line, when the SCR is decreased to 3.6, it's unstable, and maybe the stability can oscillate at about 2 Hertz. But if we use the proposed PL pacification module, as you can see, the blue line, you can see it's stable. From figure B and figure C, you can see for figure B, it's the simulation without the proposed PL pacification module. You can see indeed it's unstable from 30 seconds if we decrease the SCR to 3.6. But you can see from figure C, if we use our proposed PL pacification module, it can be always stable, even on the SCR equal to 3. Of course, I think it can also be stable on the weaker grid, for example, SCR equal to 2 or 1. Here is another test. Here is another test. As you can see, we change the PL bandwidth. If we don't use the proposed PL pacification module, you can see from the maybe black line, you can see it's unstable. But if we use the proposed PL pacification module, it's always stable, no matter how large the PL bandwidth is. And the time domain simulation in figure B and figure C verify this. You can see for figure B, it's without the PL pacification module, it's unstable, and 1 Hertz oscillation can happen. But if we use the proposed module, it can be always stable, you can see. And I think the performance is satisfying. Finally, we also test the performance on the different active power reference. As you can see from figure A, if we don't use the proposed PL pacification module, it can be unstable if we inject 0.5 PU. But if we use the proposed method, you can see the eigenvalue is the most not changed if we increase the power. And the simulation results in figure B and figure C verify this. You can see in figure B, it's unstable from 30 seconds. If we increase the active power reference from 0.4 PU to 0.5 PU. But if we use the proposed method, you can see we can even inject 1 PU power. Here is the experimental verification, as you can see. This is the result without using the full PL pacification module. You can see maybe only for figure A, only 0.35 pu can be injected. But if we use the proposed module, you can see from figure A, figure B, figure C, 1 pu can be injected. Okay, so after we introduce the stability enhancement of the PL-based grid-fault inverters, in the last part, I would like to introduce some impedance measurement of the inverter-based power systems. Firstly, I would like to introduce the problem statement. As you can see, this is the typical power electronic based power system. It includes many power electronic devices. So if we want to use the impedance method, we should know the impedance feature at different nodes. But you know, maybe there are many nodes in the power system. It means that we should measure the impedance at different nodes, maybe one by one. So for example, you can see here, there are many nodes, maybe P nodes, and maybe we should perform the frequency scanning or to measure the impedance. It's very time consuming. So for example, if we want to know the impedance feature at nodes M and N, maybe we should inject, for example, in figure A, we should inject the current perturbation 2 times. Or we should inject the voltage perturbation 2 times at nodes M and N. So it's time consuming. So our motivation is that since the grid forming inverter can flexibly adjust its terminal voltage and frequency, so it can be used as a perturbation generation and injection device. So what we need to do is to adjust the output frequency. And meanwhile, as we know, for grid forming inverter, because it doesn't have the PLL, so maybe it can help to improve the small signal stability. So this is why we use the grid forming inverter to inject the perturbation and measure the impedance. As you can see from the figure, this is the principle of the single node based current perturbation injection using the grid forming inverter. So our motivation is that if we design the algorithm, maybe the impedance frequency responses at node N can be measured by injecting current perturbations at node M only. So in other words, if we are interested in the impedance feature at other nodes, we can similarly use the proposed method. Here is the simulation verification of the proposed method. I will not show how the details of the proposed method. If you are interested, you can refer to this reference. So you can see we start from the simple RLC circuit because it's very easy to show our proposed method, because you can see there are 2 nodes. It's very easy. You can see if we inject the current perturbation at node M, and our motivation is that we should measure the impedance at node N. Indeed, you can see from figure B, this ZNN1 is the theoretical impedance, because we can easily calculate the theoretical impedance model because it's just a RLC circuit. And for ZNN3 is the measurement using our proposed method. You can see up to 2.5 kilohertz, the measurement result is accurate. This is the 2 tests. And we move to the multi-parallel inverter-based power system. As you can see here, we have four inverters connected to the grid. We inject the current perturbation at node 1 using the grid forming inverter, and our motivation is that can we measure the impedance at node 4? Here is a simplification of figure A. As you can see, finally, it can be simplified as a single pi circuit model. You can see here, Z441 is the theoretical impedance at node 4. And the Z443 is the measurement result. You can see up to 2.5 kilohertz, the measurement result is accurate. So it means that indeed our proposed method works. But this is still for small scale power electronic based power system. So next we show the verification on the real world large scale power system. As you can see here, this is the practical power system built in the PCAD. You can see from figure A, this is the measurement result using the proposed method. This is the plant side impedance. It means that this is the terminal impedance of one wind power plant. You can say from YQQ, it starts from minus 180 degree. So I think if the grid is weak enough, maybe the instability can happen at the terminal of this wind power plant. And as you can see from figure B, this is the grid impedance seen from this power plant. As you can see for YDD and YQQ, the phase angle starts from 0 degree. So it means that it behaves as maybe positive resistor. So anyway, you can say up to maybe 10 hertz, maybe 50 hertz. The measurement is clean and accurate. So after we have this measurement result, we can perform the impedance-based stability criteria to assess the stability margin. Okay, finally, I would like to provide the summary. Firstly, we comprehensively derived the small signal models, including the status space models and the impedance models of 11 commonly adopted grid fault inverters. And after that, we compared the effects of inner current control, out power control, and voltage control on the maximum power transfer capability. And we pointed out that maybe we can increase the inner current control and power control bandwidth to improve the stability margin. In addition, after our theoretical analysis, we further developed the PL passivation module. It's very easy and it's very easy to plug in when the instability happens. We just insert the, as you can see, maybe it's a 2x2 matrix into the control loop. And this proposed PL passivation module can help the grid fault inverter to be stable on the maybe very weak grid, or maybe on the very high power injection, on the very high PL bandwidth. So in other words, the module is robust. Finally, we proposed the single node based multiple node impedance measurement method, which can release the computational burden and is cost effective because we only need to inject the perturbation at one single node. And in this case, maybe we can measure the impedance at all of the nodes of interest. Okay, thank you very much.
Thank you so much, Weihua. If you go back to the previous slide, I want to make a few notes on this slide. Yep. So, well, a lot of theory, a lot of concepts here in this particular presentation. This is the outcome of more than a year of very hard work that Weihua has put into this. So what Weihua has done in the last 18 months almost is, well, it starts with that small signal model. So what we have at the moment, which has been published in a paper available online, so a very comprehensive list of all these grid following inverters, small signal models that can be used for so many different studies. And Weihua showed a few of them. But when you've got access to the small signal model of a grid following inverter, the full model, you can do almost anything you want, any sort of analysis that you want by changing any parameters in the system. So depending on what model you've used in your grid following inverter. And then using these models, Weihua developed that PLL passivation technique. So essentially what he has done, it can help you to operate your PLL in any weak grid condition. So the impedance of your PLL will be passive. Now, what I would like to mention here, Weihua talked quite a lot about impedance-based analysis and frequency domain analysis. And this is the beginning of a journey for us over the next couple of years. Hopefully, we are embarking on a new project on this exact area of impedance-based or frequency-based stability analysis. And this is a new way of looking at stability. We're hoping that we can shed some light on this and particularly develop tools in years to come, hopefully with the knowledge that we've generated so far in this project. Over the next 2-3 years, we're hoping to develop many more tools that can be plugged into the current PSCAD models, for example, that AEMO has, or any other TNSP that might have a PSCAD model, an EMT analysis model, to help them augment that EMT or time domain as simulation platform to look into frequency domain as well, because frequency domain will give you a certain insight that you will not see in time domain, and that's our goal. Although it's a little bit more difficult, a little bit more challenging, a little bit more sophisticated, but this is something that we need. I mean, relying only on EMT analysis is not enough. And with the work that Weihua has done and with all the knowledge that we have at the moment in this area, we're confident that over the next couple of years, we can develop many interesting tools in this area to support grid connection and operation and planning and understand how IBRs will operate in different conditions. So with that short explanation about this work, we can open the floor for questions and monitor questions online. Okay. Bill, so if you again start your mic.
Is it on?
It is.
Okay. Thank you for your presentation. But following on your comment, Behrooz, do you see an opportunity for dynamic phasor measurement if you're looking at state-based equations or state-based descriptions of circuits and EMT? Are dynamic phasors a possibility in terms of control of power grids?
Look, you know, what we need to enable all these things, first of all, one thing here is that whether we want to look at things from a practical power system point of view, like the exact power system, or simulation. From simulation point of view, obviously what we need here to develop these tools are, well, you can sense the signals in your PSCAD or any EMT analysis, any platform, and do all of these analysis. Now, when you go to the real power system, you need all those measurements. You need all those measurements, and you need all those measurements synchronized with each other. At the moment, what we've got in the power system, we do have PMUs, we do have phasor measurement units, but not many of them. And then their report rate is pretty low. What we need for all these analyses are, if we wanted to do these on a real practical power system, we need PMUs with very high report rate, synchronized with each other, to be able to do all of these analyses on a real power system. Well, yet we don't have them. We are hoping that in the future years, we will have such a platform in the NEM, and we are hoping to have very high frequency sensors, synchronized sensors. Well, I don't want to say PMU, because PMU, the current standard PMUs, they report at 50 hertz. I would call them a high frequency PMU. So if we can have a high frequency set of PMUs in the network that we can extract all this information from, then we can do a lot of interesting studies in the frequency domain to see what happens. Having said that, doing these analyses on a simulation case study as well is, of course, very, very useful. And doing these analyses on the PSCAD, for example, model that AEMO has developed will be fantastic. That can help us quite a lot. But to take it to the practical level, we do need some more capable sensors in the NEM. Other questions? But you will hear much more about these frequency domain tools in future years, because like relying on RMS or EMT analysis and time domain analysis is not sufficient. we are having IBRs in the system which have so many different behaviors that we saw in some of these slides, that just relying on some isolated time domain tests wouldn't cut it, wouldn't actually be sufficient to understand all the interactions and problems that will occur in the system. We do need more tools, and hopefully frequency analysis will be a very good step towards equipping ourselves with the tools that are required for stability analysis. Nabil, any questions online? Any other questions on the floor? Okay, I guess a very good time to break. We are pretty much on time. Very good. So we've got a 45-minute break, and we will go for lunch. Lunch will be served just outside the room, and our online attendees, please be back at 1:10. So in 45 minutes from now, we will continue with our presentations. Okay, welcome back. I guess everybody is back in the room, and we probably can start the afternoon sessions. In the afternoon, the sessions that we've got are focused mainly around grid forming and grid following inverter control. We will be seeing a few presentations now in this session on this concept of power synchronous grid following inverters. And then after that, we'll move to grid forming control, and we'll see a few presentations around grid forming inverters and how we can use grid forming inverters to provide better performance in weak areas of the grid. I will first pretty briefly introduce this topic of power synchronous grid following inverters, and then Milad and Nabil will go into more details. And I probably can safely skip the first subsection here, because I think we've seen this now many times, so we don't want to see it anymore. And we know that typical grid following inverters have quite a lot of problems. I mean, control interaction and stability, failure to ride through disturbance and faults, islanding issues, subsynchronous oscillations, and inability to inject maximum power. Most of them are because of the PLL that we use. But we've seen some techniques today in the morning. Milad presented a technique on nonlinear control of PLL, phase lock loops, in order to shape their performance and make them stable in weak grids. Weihua talked about PLL passivation and showing us, he showed us that how we can have a PLL which acts as a passive component in weak grids and maintain its stability in the grid. So we already know that there are certain techniques that you can apply to PLL-based systems to make them stable. But the idea of this particular presentation here is to show another way of getting synchronized with the grid in a grid following system, that we call it power synchronous grid following inverter. So this is essentially, you can look at it as something in between a typical grid following inverter and a grid forming inverter. A grid forming inverter doesn't use a PLL. It actually gets synchronized to the grid using a power loop, but at the same time, it controls the voltage at the point of connection. So we can say that it forms the grid. A grid following inverter doesn't form the grid, it follows the voltage. But what we are actually explaining here is something in between. It doesn't require a PLL, but at the same time, it doesn't also control the voltage at the point of connection. And it can essentially, you can use it in, let's say, a farm to inject maximum power maximum power to the grid. Now, to explain this, well, imagine that you've got this very simple inverter connected to the grid. You've got a pulses modulator, and you've got an inverter current controller. So the inverter current controller is typically there to ensure that you're injecting a particular reference current to the grid, which is translated into real and reactive power. In this particular way of control that we are presenting here, you still have that inverter current control, but instead of having a PLL to follow the grid voltage and to obtain the grid frequency to get synchronized with the grid and inject that current, we're using a power controller. And that power controller, its output are two things. One, is the reference for the input for the current actually controlled, and the other one is the phase angle or the frequency of the grid that you require to get synchronized. So there is no PLL in this. And for those of you who already know what a grid forming inverter is, in a grid forming inverter, I can bring my mouse here. In a grid forming inverter here, in between your power control and current control, here you have another loop which controls the voltage, and also the power control here in a typical grid forming inverter is a VSG, virtual synchronous generator. We don't have that here. Instead, we've got, well, the current control, which is identical in all of these controllers, but this power control essentially synchronizes with the grid and also gives the set point for the inverter current controller. Now, one thing here is that IQ ref here is set to 0. When we set IQ ref to 0, this means that the DQ reference frame, for those of you who understand DQ reference frame will be actually aligned with current, not voltage anymore. And that's the big difference between this way of control and the typical controllers that we've got for grid following and grid forming inverters. Because in other types of control, you typically align with the Q component, with the voltage, and you force the Q component of the voltage to 0. And that's the difference here. Now, the controller that we've got for the power control in this one is essentially something like this. Is a 2x2 controller that receives the error in real and reactive power and gives these errors to a 2x2 controller and creates the frequency and the set point for the inner current controller. Now, one big difference here is the way we are controlling the power. We're controlling the power at the terminal. Typically, in a grid following or grid forming inverter, you control the power at the point of connection. This is the biggest difference between this and a normal grid following inverter. We actually are controlling the power at the terminal. And you might ask, okay, what is good about it? Well, if you control the power at the terminal, you can assume that the rest of it, the filter, you don't require that VABC here, right? You don't need to know the grid voltage. Without dependence on the grid voltage or without dependence on the point of connection voltage, essentially, you can assume that you are connecting your grid following inverter to an infinite bus because you don't need that grid voltage, because then you can assume that all of these LG and LF, they're all parts of the filter, harmonic filter for your inverter. And in a nutshell, it means that you are connected to an infinite bus. In a nutshell, it means that, again, I don't want to go to the details of the implementation, but I want to give this a message that using this approach and controlling the voltage at the terminal and not needing any other voltage in the grid, which can be sensitive to current injection, to power injection, means that you have a very strong grid at your disposal rather than having it connected to or controlling the power at the point of connection. Now, going actually well, this is the way we control power. Going to the modeling, so we can actually model this system. If you look at the power at the terminal, VT and ID, with VT and I, the terminal voltage of the inverter, and the current of the inverter, I can calculate the power at the terminal. And this is it. And with making the reference frame align with the inverter current, remember I told you that IQ is 0, this will be the simple model that you can develop. Very, very simple model that you can develop. And based on that simple model, so the error in the real and reactive power can be transferred into omega and IQ ref. And based on that simple model, with different control techniques, you can define a 2x2 controller that will give the reference for the D component of the current, and also it can get you synchronized with the grid. Or in other words, it can give you the frequency of the grid. Now, the way we have designed this, so this is one way of designing this 4PI control system with a pretty sophisticated optimization-based control design that I won't actually talk too much about the details of this. But the only thing I want you to take away from this slide is that if you want to design this, the 4PIs here, when you know the model, and you know how would be the performance, what performance you would like, and with performance, the open loop transfer function, you can come up with the coefficients of this by solving that optimization problem. The details are in this paper, but just what I want you to get from this slide is that to come up with a good design for those 4 PIs, you just need to solve that optimization problem, and by changing the coefficients of that LD, you can change the dynamic performance. Now, by taking this approach, we have done some tests. We have designed a controller and done some tests here for 2 separate grids. One is a very, very strong grid, so SCR16, and then this one a very, very, very weak grid, SCR 0.8. What we noticed was that almost identical performance. Doesn't really matter what grid you're connected to. Almost identical performance. Again, the main reason is that we are not dependent on any measurement of any voltage in this approach. We are controlling the power at the terminal of the inverter. We are not controlling the power at the point of connection. And by doing so, it's as if I'm combining the grid strength and the filter of the inverter together, and as if I've got a super strong grid, an inverter, and its filter in between, and I just control the current there, eliminating any PLL there, eliminating any source of instability that might occur in a weak grid. And as you can see, the performance in both very strong grid and very weak grid using this approach is identical. Going back to here, just maybe here is good. Just one more time to explain what the structure. So I've got an inverter current controller that's identical to any grid forming, grid following system. In order to synchronize, I need that theta or frequency of the grid. That frequency of the grid is coming from this power control. So this power control is the main source of difference between this methodology or any typical grid forming or grid following inverter. And it is giving me directly an omega and also ID ref. And remember, we are aligning with the reference, with the current of the inverter. All the reference frames are aligned with the current, meaning that IQ is 0. When IQ is 0, remember, when IQ is 0, our P is dependent on ID VT cosine delta. So there's no IQ there. My real power is dependent on the D component of voltage, and my Q is dependent on the Q component of the voltage. So it's the dual of a normal grid following inverter, which actually requires forcing Q component of the voltage to 0. So again, because we don't need that VABC at all, it's as if I'm combining these 2 impedances in one filter, and it's as if I've got a system, an inverter connected to a super strong grid. We don't require that VABC. We don't have any PLL, which are the forces of instability in normal, typical grid following inverters. So the only difficult point, I mean, it works very well, but the only difficult part about this is this optimization, and I need to design these controllers using an optimization and lots of difficult optimization constraints here, and not very easy to design. That's why Milad actually worked on a variation of this and came up with a way to design this controller in a very simple way, rather than designing this controller with an optimization approach. And Milad will be talking about that and tell us how he designed this controller and made the design very, very simple. So, Milad.
Okay, thank you very much, Behrooz, for the background. So this presentation is about a variation, actually, a modification of what Behrooz just explained. So let me just, it's not working. Okay, still not. It's on, I guess. Okay. Okay. Thank you. Okay, so in the first part, I'm really going to very briefly touch power synchronous grid following inverter because Behrooz already mentioned everything about it. And then I will introduce LPV PSGFLI. Then its transient stability and its small signal stability are going to be discussed in the next parts. And also finally, we're going to talk about outcomes and highlight what is the benefit of using LPV PSGFLI that I'm going to talk about shortly. So we know that grid following inverters use a PLL in order to get synchronized to the grid, and that PLL is the main source of instability. However, without a synchronization unit, it's not really able to synchronize any inverter to the grid. So if you want to get rid of PLL, we are supposed to replace it with another method, which in here, as Behrooz explained, a power synchronization method has been used for replacing the PLL and generating the data that we need for our control. So this is how PSGFLI, or the inverter that Behrooz just mentioned, has been born. So this is, again, the SMIP model of PSGFLI, and also this is the power controller, which is responsible for creating the angular frequency, which then it's going to be integrated and create theta for us. And ID ref, as Behrooz mentioned, IQ ref is set to 0. So it's really just necessary for us to generate ID ref and definitely the theta. So in Behrooz's presentation and the very initial design in PSGFLI, we use some identification. Behrooz used some optimization. Yes, thank you for some optimization methods in order to design the controller. However, there are some issues with that method. So first of all, as Behrooz mentioned, it's not really straightforward to use that optimization method. And there are some other things. So once you design the controller, you are just designing for one specific operating point. So, and definitely we are not going to change our controller, I don't know, every couple of days when it's installed in a power system. So what happens is that the design constraint and design criteria are only valid and are only taken care for the points, operating point that we have designed the controller for. So if we change the operating points, that dynamics of the responses are going to be different. For example, the rise times are going to be different. We might have some oscillations in the system that order of the system might increase and cause some undershoots or overshoots. And also, if the way that we initially designed this controller, if we want to design it, it's not that straightforward to change the direction of power. It means that if we have, for example, battery, if we want to inject or absorb power, then we need to change the controller completely. Otherwise, the system becomes unstable. So the idea here is to design a controller that always has, for any operating point, it has a constant, it provides a constant dynamics to us. Let's say, for example, the rise time is a constant value for any operating point, or we don't have any undershoots or overshoot. And so overall, we just want to have similar dynamics for any operating point that you are working at. And also we want to be able to change the power direction, and we want it to be as simple as possible instead of just using some optimization methods in order to design the controller. So the goal here is to have active and reactive power open loop transfer functions, something like this. So in this transfer function, we are going to, if we apply a change in active or reactive power reference, first of all, they are going to be decoupled because the non-diagonal entries of this transfer matrix are 0. And apart from that, both of them are going to have a first order Kp over S open loop transfer function. Means that we are going to have a first order response with the rise time equal to 1 over Kp. So the goal is that we always have this transfer function, and we are supposed to design the controller such that it guarantees for any operating point, the system is going to show this response to us. And if you remember from Behrooz's presentation, in that transfer function that he showed us, that transfer function is relying also on the operating points and also the grid voltage and impedance. So we have used a nonlinear control method named linear parameter varying method, or LPV controller. So if we apply this controller to the system, it guarantees that the open loop transfer function is similar to the equation above, or LD. So as you can see here in this LPV controller, we have, for example, delta 0, S0, ID0, and KP. So KP is similar to what we have in LD, and those delta 0, ID0, and S0 are about the operating point of the system. So if we change the operating point of the system, delta 0 is going to change. So for example, the first entry of this matrix and second entry, whatever, so all delta zeros in this matrix are going to be changed. If the amount of the RMS value of the injected current changes, then ID0 in this controller is going to be. So it's a kind of adapting itself to the new operating point of the system. It's a kind of changing its coefficients in any single operating point that we are working, including during the transients, because we can assume that the change is pretty faster than how P and Q are being changed. So these are simulation results of when our LPV PSGFLI is connected to a strong system with SCR equal to 16. So in the left, we can see the simulation results when we are changing P and Q for multiple times, for the P and Q are being changed from 1 megawatts to 5 megawatts, and even the active power is being reversed to -2 megawatts. And in the right, we can see that how this LPV PSGFLI is acting while we apply a fault at its POC, and how it's acting when we apply a 20 degrees phase jump at its POC. So we can see that in both disturbances, the LPV PSGFLI can read through them. The same tests have been done for when the similar LPV PSGFLI has been connected to SCR 1.2 without changing anything in our model. So we can see that again, similar dynamics have been observed in P and Q. Generally we are observing that the rise times are similar to each other. There are small undershoots here, which are for non-model dynamics. Definitely, we will have some on-model dynamics in particular in the current controller. Also in the right, we can see the response of the inverter when a fault applies, similar fault basically applies at this POC, and also similar phase jump has happened. So we can see that regardless of the SCR and the system strength, LPV PSGFLI can deal with any type of active or reactive power reference changes, or faults, phase jumps, whatever that you want to apply at its POC. So now that we have designed this LPV PSGFLI, it's also worth to go through its transient stability. So in transient stability, what we are going to do is we want to assess how the inverter basically reacts when we apply large disturbances, like for example, a grid fault at its terminal, or at its POC. So similar to what we did previously, first we need to find the nonlinear model of the system. And then after finding the nonlinear model of the system, we need to see if there exists an equilibrium point. So this equation here actually shows the condition of having an equilibrium point in the system. If this equation is not valid, then it means that we don't have any equilibrium point, and obviously the system cannot be stable. In the second stage, we need to assess whether the equilibrium point is stable or not. we can find the condition, the stability condition, which is a necessary and sufficient condition, as the constraint that you can see here. And finally, again, because it's a nonlinear system, we must find the domain of attraction. And again, Lyapunov's direct method is going to be used. So here we have two interesting figures, actually. So the thing is, when we use Lyapunov's direct method, or when we basically suggest a Lyapunov function for a system, for a large signal stability system, the DOA, which is given to us by that function, is conservative in general. What does it mean? It means that the DOA that we are acquiring from that energy function is most of the times smaller than the real domain of attraction of the system. So it's worth to assess the amount that is conservative. So here we are trying to do that. So the blue area shows the area that our function suggests the system is going to, that it's inside of the domain of attraction of the system. Or in other words, if we start from any point inside of this blue area, any initial condition inside of this blue area, we are going to end up at 0 and 0, which is our equilibrium point. And also these lines here that you can see are the results of numerical solution of the differential equations of the system, or the state spaces of the system. So interestingly, we can see that the Lyapunov function that we proposed here is giving the exact domain of attraction of the system, meaning that whatever is outside of this blue region is ending up in other equilibrium points of the system. So at least in these two examples for SCR16 and XCR 1.2, we can see that the energy function is not giving us a conservative result. Also, these are some experimental results. So in the left side, we can see that we change SCR from 22 to 1.4. And based on the initial condition about the presence of equilibrium point, we can see that we expect there should not be any equilibrium points in the system. So we expect the system to be unstable. And we can see that when we change the SCR at this time around 0.08, the system becomes unstable and it's not able to maintain its active and reactive power. In the right-hand side, we are changing KP from 100 to 1000. So what does it mean? We are forcing our inverter to have a rise time instead of 100 milliseconds. We are forcing it to have a 1 millisecond rise time. So we are forcing it, we are pushing it to be much faster. So it's not possible for it. It really cannot do it. And it shows itself in the eigenvalue here, or the pole of the linearized system. So it's being changed from -75 to 1200. So we expect that the system must become unstable after changing that KP. So it has equilibrium point, but the equilibrium point is unstable. So as we can see in the experimental results, the system becomes unstable as soon as we change KP from 100 to 1000. So this was about the transient stability or large signal stability of LPV PSGFLI. In the next part, I'm going to talk about small signal stability of LPV PSGFLI. And in order to do it, we are going to use impedance-based stability analysis. So impedance-based stability analysis, Weihua and I guess Sajjad, they both talked about it. So it's one method in order to assess a small signal stability analysis, and we are going to use it here. So another method for small signal stability analysis would be an eigenvalue analysis, but that is a very different method, and it's not really straightforward to do it. So impedance-based stability analysis is for small signal stability. It's a very powerful tool, in particular when we don't have information about what is happening inside of each. So typically what is happening is that some black boxes are given to us by, for example, OEMs and developers, and we really do not have access to the internal controls of those inverters. So this impedance-based stability analysis collectively with identification methods can be used in order to assess the small signal stability of the system. There are many system identification methods like PRBS injection, pulse injection, etc. that it's out of scope of this presentation, but that system identification with impedance-based stability analysis is a very strong tool for us, even in practical and real world issues, basically. So the aim here is to find the output impedance of our inverter in DQ domain. So it's going to be a 2x2 matrix like this. It will have ZDD, ZDQ, ZQD, and ZQQ. And we are going to find these entries analytically for our LPV PSGFLI. And I will explain why it's really valuable to have it analytically and why we just don't use system identification shortly. So we did that in this research, and this is the comparison of ZDD and ZQQ while we use a system identification method in red stars here. This is the red stars are the results of system identification, and the blue solid line shows the analytical method that we have used method. So we can see that they overlay each other perfectly. So if it's possible to that we identify the model why we just tried so hard in order to find the output impedance. So the reason is if any single thing changes in an inverter or in the grid or in the operating point, etc., then the identified model is not going to be valid anymore. So you need to repeat the identification over and over if you want to change anything or if you want to assess any sensitivity to any changes. But once you have the analytical model, it's just a matter of changing one number in a matrix or in, I don't know, in, for example, a Nyquist figure or whatever in order to assess its sensitivity, for instance, or if the operating point changes, you can just simply change the operating point in the corresponding variable in your equations in order to find what is the impact. So these are some Nyquist results. So in impedance-based stability analysis, typically the way that we use, as my colleagues mentioned previously, is using Nyquist criteria. So in Nyquist criteria, so in the left, we can see the Nyquist criterion for ZDD and ZQQ of a conventional grid following inverter. And in the right, you can see ZDD and ZQQ for LPV PSGFLI. For in identical situation, and these two controllers are designed to basically be similar, to show similar inverters in terms of rating, current control, etc. So the only thing which is different is the synchronization method that we are using. Instead of PLL, we are using power synchronized. So the green lines here show the results of the Nyquist when SCR is 16.8. The blue lines here show the Nyquist diagram when SCR is 1.21. So we can see that for LPV PSGFLI, we don't have any encirclement around -1. So it means that based on Nyquist, the system must be stable. However, in the left-hand side, we can see that ZQQ for conventional grid following inverter has an encirclement around -1 when SCR is 1.21. And also one other thing that we can understand is that because so what happens in the PLL is that it regulates the VQ. So the PLL impact usually shows itself in ZQQ, and we can see ZQQ is showing that encirclement around -1, and this gives us a kind of clue that possibly, and it's more likely that the PLL is the cause of instability in the left-hand side system. So these are the currents for this for the previous slide. So the phase A currents of in the left the conventional grid following inverter when the SCR is 1.2, and in the right the same test for when we are using LPV PSGFLI. So the active power is being changed from 2 megawatt to 4 megawatts at T equal 2.5. It's worth mentioning that also these figures are for when active power is equal to 4 megawatts. So for 2 megawatt, there is no encirclement around -1 even for grid following inverter, conventional grid following inverter. So as we expected, the small signal stability is lost when we increase the active power in the conventional grid following inverter, and that encirclement around -1 also confirms that. However, LPV PSGFLI does not show that instability, and neither in the Nyquist figures, Nyquist plots, nor in the current measurements. Also, these are some experimental results. We have changed active and reactive powers for when SCR is 31 and SCR is 1.9, and we have depicted the Nyquist of each operating point here. We can see that the Nyquists are not really impacted by the operating points, and regardless of the operating points, there is no encirclement around -1. And also we can see that there is no instability in our inverters. So the outcomes of these research are the PLL is removed, first of all, from the grid following inverter. That is a good thing because that was the main issue when we were connected to a weak grid. There is no need for voltage feedback, as Behrooz mentioned. I'm not going through that. And so there is no impact from POC voltage distortion. It's a very straightforward design because so you have the equation. So the only thing that you need to do is you get those variables from your measurements and put them in your equation in a real-time manner. And as we can see, there is no impact from very weak or very strong grids. So regardless of the system strength, is able to work. And also one other small thing about, no, I just already mentioned it. So the references for the LPV PSGFLI design has been published in this paper in IEEE and accessible on IEEE's website and also on our websites here. The second part, which is the transient stability, is not published yet. We are hoping that we can publish it soon. But the impedance-based stability analysis has been recently published again in IEEE and is accessible in IEEE Explore and in our website again. Thank you very much. I don't know if you are we taking questions now, or
I guess we can finish with Nabil's presentation first, and then we can take questions because they're all around the same topic. Yeah. Okay.
Thank you very much.
Thank you so much. So Nabil will be presenting the third part of this session, which is again on the similar topic of power synchronized grid following inverters. And then after that, we will have a Q&A session for this. Okay, Nabil, you've got around 20 minutes. So hopefully you can finish within 20 minutes.
Hi, everyone. Good afternoon, and thanks for coming, and thanks for those who are online. I'll be not working. It is on. Okay, so just okay. I'll be talking about grid following inverter. Like broadly, we can like divide them to two groups. The first one PLL based, and then the second group is PLL less. So just to give like a very like brief background. The most like well-known is the vector current control. These have been employed in the industry and the solar farms and so. So it is a simple structure. It is well-established control method. However, as my colleague mentioned before, they do have poor dynamic performance in weak grid, and they do have small signal instability issues due to the PLL. So researchers moved from PLL based to PLL-less, one of the most earlier method called direct power control. It was proposed in 2018 when they removed the PLL. And however, this method have different issues. They had bandpass filter that affects on the stability of the stability and the dynamic performance of the inverter. As well, it have unstable operation and grid and weak grid, especially under large frequency deviations. And then here is a summary of Behrooz work on power synchronized inverters. It is a very powerful control strategy. It is a PLL-less. It can perform well in strong grid and then in weak grid. But as we mentioned, that the shortcomings is the offline optimization method. And as well, the controller bandwidth is depending on the operating points. Then to summarize Milad work, he tried to solve the shortcoming in the previous version of the controller by proposing an adaptive tuning of the power controller. So it is a PLL-less. It has good performance in strong and weak grid. And as well, it is a real-time tuning of the power controller. However, we still have shortcomings related to the frequency deviations and unbalanced grid voltage. And in those 2 points, I mainly would like to thank Cyril from AusNet. In our of the stakeholder meetings, he said, guys, you are proposing new controllers. What about investigating the controllers under realistic scenarios of the grid? So thank you so much. He is with us here. So now I was talking about PLL based and PLL-less. So can we come up with a comprehensive study to test those controllers, the one I mentioned, in a one single study? This is what I firstly did when I joined Monash Uni. I consider the conventional VCC and then 2 PLL based, the direct power control and LPV. And we published this work on IEEE. First, we do a comprehensive comparison in frequency domain. Why frequency domain? Because we can look to the body plot and then we can compare the gain and phase margin of each controller. And as well, we can go to the generalized Nyquist criteria to judge on the stability of the system. And then we perform as well a very comprehensive time domain comparison in both strong grid and weak grid when we listed 5 different scenarios, including the step change in the active and reactive power, frequency jump, phase jump, and then imbalance in the grid voltage and the PCC fall. I'll not go to this study, but you can access it whether in the IEEE it is open access or on our website. So I'll go to the what I'm trying to solve in this presentation. I'll be talking about proposing new controllers, 2 controllers, one to tackle the frequency deviation, another one with to tackle the unbalanced system. We know that in real operation of power system, we do have frequency deviations that can occur for different reasons in the system. So how this will affect our controller, the proposed LPV? We will have steady state errors in the inverter output power. And then we might drive the large frequency deviation can drive the inverter to instability. The another challenge is unbalanced grid voltage. We know many reasons can be behind the imbalance in the grid, and they will affect as well the power synchronized control in terms of unbalanced output current that could be a one phase supply more current than the another one. And as well, it will lead to oscillations in the control loop. So the objective of the study is to propose new control strategies to handle the frequency deviation and then the unbalanced grid voltage, as well to preserve the advantages that we gained from the power synchronized control, like they are PLL-less, they can operate very well in strong grid, weak grid, and as well regardless of the XR ratio. So I'll be talking now about the first controller to handle the frequency deviations. Here is just only a very brief summary, like technical slide. I'll not go too much details, but as Behrooz mentioned, that we are aligning with the current at Q axis, and this is the inverter output waveforms. And the first thing we did, we remodeled the plant considering additional dynamics, especially in the Q component of the voltage. This is the final results. And what the aim is, based on the new model, how we can design for new parameters for the outer power controller. So we set up the desired output transfer function to have it second order, so that we can eliminate any deviations in the frequency. And after like going throughout the mathematics and so on, we come up with this new controller, the matrix of the new controller for M11 to M22. And this is the paper for the design and all of this technical. So to summarize, the controller that we come up with, it is a second order for the power controller. It have many advantages, like it is a PLL less, it is robust against frequency changes, it's operating in strong and weak grids, and it have fixed controller bandwidth. So then we propose a new control. We have to test it to see like its stability, and we moved here. We adopted the impedance-based stability analysis. As my colleague said about it, it is very powerful in frequency domain. We can utilize body plot and as well Nyquist to test the system before we put it in the real world. Just to make it very simple, like if we do have electric system, and then we would like to test the stability, just we set the system to two subsystems, and then we find like the ratio of the impedance of both systems, and then we see the Nyquist. So if the root locus is circulating -1, then it is unstable. So I'm testing the conventional vector current control in the left-hand side and the proposed control in the right-hand side for 3 different SR ratio, 10, 2, and 1.2. This is the body plot, but let us have a look to the Nyquist. So now this is the impedance at D-axis. We know that even the conventional controller will not face any issue at the D-axis because the effects of the PLL is at Q-axis. So at D-axis, both the conventional control and the proposed control is stable for 3 different SCR ratio. If we move to the Q-axis, we can see here now we have our proposed control is still stable. All curves are not in circulating -1, which is the critical point in the control theory. However, if we look to the vector current control in weak grid, which is represented by blue line, it is in circulating -1. So the controller will be unstable, and it will be marginally stable at SCR equal to 2. However, in strong grid, which is 10, it is completely stable. This is what we are expecting in strong grid. To verify the simulation, we verified the proposed control in simulation using AMT modeling in MATLAB Simulink, in Plex, and then in PS-SCAD. We tested different scenarios of the proposed control in strong grid and weak grid, and also we compare it with the direct power control, LPV, and conventional VCC. We did almost the same thing in the lab. So I'll skip this one very fast. So this is the proposed control in strong grid with SCR equal to 10. And this is when with SCR equal to 2, we can see that the proposed control is stable current at ABC, at DQ and voltage. We are aligning with IQ axis, as we can see. And we are controlling the VQ component in order to inject and absorb reactive power. And here is a continuation of the curves. We do have the active reactive power, and then we can see here we are applying a frequency deviation, which is even a realistic 5 Hertz to test extreme condition of the proposed controller. We can see that the proposed control is able to recover, to inject the reference after the jump in the frequency. Here we are comparing the proposed control with the other controllers. We do have one frequency deviation, the DPC. Here it have it takes longer settling time. The LPV, which was proposed earlier by our group, have steady state errors after the frequency deviation. So this is the case of 1 Hertz deviation. If it is 5 Hertz deviation, the only one will be stable is our new controller. The other conventional controller and LPV will be driven to instability. For experimental result, we had a scaled down 1 kilowatt system to test this controller. And I started by showing the problem with the conventional LPV. After we had a 1 Hertz frequency deviation, we can see that we do have error in the active and reactive power at T3, with just only with a frequency deviation of 1. However, we do have, this is the proposed control in weak grid with 1.3. We do, there is a frequency deviation equal to 5 Hertz, and then the controller is able to maintain the references. This is in weak grid. This is the performance in strong grid with SCR equal to 7, and the proposed control is still able to track the frequency deviations. So now, what about unbalanced system? We know that we are controlling inverters at DQ axis after we apply ABC to DQ with 50 Hertz. And then if we do have unbalance, then we will have oscillation at double of fundamental frequency at 10 Hertz. So the whole control at DQ need to be restructured again. Without going to the details, this is the control. This is the block diagram of the proposed control. So what we had a while loop to control the negative sequence, another control to control another inner current control for the positive sequence, and then the outer power control of our proposed power synchronized controller will just only give the references to the positive sequence. And with this controller as well, you do have the option either to regulate the terminal power or at the PCC after the filter. This is another advantage. Let me go here. So we had simulation test. We have experimental test, but here I'll show just only the experimental tests. With the conventional power synchronized controller, we are applying unbalanced system with 50% at phase B. This is the power synchronized controller. We can see the current is unbalanced. The injected current by the inverter is unbalanced anymore. If we look to the active reactive power, they are oscillating at 100 Hertz, double of the fundamental frequency. And we can see that the estimated frequency by the inverter itself is oscillating as well. So this is the conventional control at SCR equal to 1. Now with the proposed control, this is experimental results. We are able to get rid of all oscillations and then to inject a balance system to the grid. So we apply the third test with SCR equal to 5.3 to emulate strong grid. We can see that the proposed control is able to inject the balance system as we want. So the research output, in this study, we further accurately model the plant when we are aligning with the Q axis of the current. we proposed 2 new controllers to emulate real scenarios, frequency deviations, and unbalanced grid voltage. And we preserve the advantages of power synchronized controllers in terms of PLL-less, good performance in strong and weak grid, and adaptive tuning. And we consider realistic scenarios like weak and strong and different XR ratios. Potential application, now we do have like, this is the final version of the controller. It can handle frequency deviation, it can handle unbalanced system, it can go with strong and weak grid. So it can be adapted to weak parts of the grid or of the NEM. So here's the end of my presentation.
Thank you so much, Nabil. So we're right on time, which is very good. So we've got probably 10 minutes before we go for a break to answer any questions. Do we have any questions online?
No question.
I guess there was one question in the morning we forgot to talk about, was about how operators or TNSPs can estimate inertia, which was a little bit not very relevant to what we were talking about, but just wanted to let you know that there are different, of course, ways of estimating inertia. There are quite a rich literature on inertia estimation, and there are even some, if I'm not mistaken, there's this company called Reactive Technologies, right? Reactive Technologies, they do have even products that they can estimate inertia. There's a pretty rich literature around that. By looking at different measurements in the network, you can come up with inertia estimation. Just remember that. I wanted to have a quick note on that. Also, before taking questions, can we show the website for the project? Yeah, if you can share a screen and show the website, how to find the website, and to know where we can actually see all the presentations, that would be great. If you search for Monash Grid Innovation Hub, and if you go to the website for Monash Grid Innovation Hub, you can see that, but I guess Mohammed Hasan will be showing that, Monash Grid Innovation Hub. If you go to the website and projects, if you click on projects, then this one is stability enhancing. If you click on this one, find more. So you will see all of, oh, we didn't have it shared on, but yeah. So this is the website. So if you search for Monash Grid Innovation Hub and go to the projects and then select our project, you can come to the website, the webpage for the project, and particularly knowledge sharing. If you go to knowledge sharing, you will see all of the papers that we have published, and anything that has been accepted is here, and we will progressively update this website as soon as any paper or publication are accepted in the next couple of months. But Mohammed Hasan, correct me if I'm wrong, we have also uploaded the papers that we put on archive here, or yeah, okay, so papers that we have submitted are also available here. So some of the works that we haven't, they're not published in public domain, you can still find them here, the submitted version. To, I guess most of them are IEEE papers. So this is where you can find all the publications. Also, we will upload the presentations that you're seeing here today onto this website, and also the recording of the session. We will be uploading them here. Okay. Questions about the last three presentations that we saw? Any questions? Yes, please.
Yes. Do you know any inverter manufacturer that has this PLL-less control strategy?
Well, the problem is that they don't tell you what they have, right? It's always like, there might be some of them, they might have actually PLL-less strategies, but none of them will tell you what's inside. They always give you a black box. So there might be some of them that are either using a PLL-less or a variation of the typical PLL base, because the conventional PLL base, it is very well known that it has a limitation in weak grids. And I know for a fact that over the last 5 years, the performance of inverters in weak areas in practical products, it's been improving, which suggests that they are using alternatives compared to conventional PLL. But yeah, the answer is I don't know. Anybody in the audience knows whether any of them uses anything? Because they just don't tell you. That's the problem. They don't tell you what they're about.
Yeah. Behrooz, just yes, to put a bit of context here, a 5 megawatt wind turbine costs about $5 million to buy and about another $5 million to install. That includes the collection network and the connection point terminal stations. So you've got about $10 million per turbine. The cost of retrofitting a controller on an inverter on a type 3 turbine, because the inverter in a type 3 turbine is a low rated inverter. It's not the full turbine output. It's about usually 20%, something like that. Would be at most, I would think, $100,000. And probably 80% of that would be testing and proving and meeting AEMO's requirements and proving that it meets AEMO's requirements. The business case, I would think, for Australia to look at retrofit on the 90% of wind farms which are currently on the grid, currently connected to the grid, must be pretty strong. The number of type 4 manufacturers, OEMs who are offering type 4 product, it's about 50% of the OEMs who are now offering type 4 product. But in terms of turbines being installed, it's much, much lower than that. So we're going to have that original 90% legacy of type 3 turbines, and we're going to have more installations over the next 5 to 10 years of large, like multiple gigawatts of type 3 turbines connected. So I can see this work as having a pretty major impact on Australia's transition. And what I'm not entirely clear on is how the financing and risk sharing and motivation and enforcement and so on should be put in place to make sure it happens. And that's, I think, it's not a question for the research team here, but it's a question for the wider industry and for the regulators as to, okay, you've got, I don't know how many gigawatts of wind turbines are on the system today, but it's a lot. They're not going away. They're not going to become type 4 anytime soon. And we're going to have probably as many again, type 3, over the next 10 years. So this work would seem to offer an opportunity which hasn't been identified up to date for Australia to take a major step forward in utilising the areas of the grid. And I know we talk about weak grid, and in fact, I had to point out to someone the other day that to say the grid is becoming weaker is not true. The grid is what it always has been. It's just, it was designed to do a different job. It was moving bulk power from coalfields to cities. And the new generation is not where the coalfields are. So we're now using what were rural transmission grids to distribute power to provincial cities. We're using them to collect power into major cities. And yeah, they're weaker. So that's just the nature of them. So I just see enormous potential in some of the work that's been done by this team over the last 3 years.
Thank you, Tony.
Hi, Behrooz.
Yes.
We have one online question.
Yes, please ask.
How to determine if we use the PS grid following inverter or the grid forming inverter when a new inverter is to be installed?
Yeah, well, that's a very good question. Well, this PSGFLI, it can easily, without any problem, operate at the maximum power point. I mean, in terms of operating at maximum power point, there's no difference between this one and a grid forming inverter. Sorry, a grid following inverter. So the only difference is that the PLL has been replaced by another loop. But grid forming inverters, although depending on where you want to use them, how you want to use them, they need to control the voltage. So there's a difference there. They need to control the voltage at the point of connection as well. So meaning that first you need to have access to that point of connection voltage. Also, you need to definitely have a capacitor at the point of connection as a state to be able to control that, which is most of the time it is there anyway. So these are the differences. So here you do not need that capacitor, and you do not need to have access to the point of connection voltage. Having said that, when you use a grid forming inverter, you can provide services such as grid strength, such as inertia, depending how you control. So depending on what you want to do, if you want to, for example, have a battery and control a battery in a grid forming mode, definitely you have to go for grid forming. But if you want to, for example, have a solar farm that you want to only operate at the maximum power point without any other thing around that, without having access to any system strength provision or things like that, you probably can go for PSGFLI. But if you want to have services such as inertia, such as system strength, then grid forming would be the way to go. But both of them, in terms of stability issues, are free from PLL problems because they don't have PLL. So I think depends on the application, depends on what you want to do. One thing that we haven't done is a comparison actually between PSGFLI and grid forming inverters, which is probably something that Nabil, you should be doing. We probably should do the comparison that in terms of stability, what's the difference between a grid forming inverter and a PSGFLI, and what you can gain in terms of stability, in terms of different services that you can get out of these, and whether under more serious conditions, one of them might be stable or the other one won't be. Having said that, one thing that I should also mention is that if you're operating in a very strong grid, if your STR is very, very high, grid forming control can be problematic because you are essentially having a voltage source, right? A grid forming inverter, you can look at it as a voltage source. And then if you put it next to a synchronous generator, the two voltage sources kind of competing against each other. So you'll have difficulties maintaining stability when your system is extremely strong using grid forming inverters. So that's one case. Probably PSGFLI would be a better choice for you compared to a grid forming inverter. But good idea for Nabil to do more studies. Yeah, we need more funding. Yes. Any other questions? Yes, please. If you please turn on the mic as well.
So is there any particular limitation of the proposed Neo controller, or you want to try to add more features on that controller?
Well, limitations, so far we have identified different limitations and we have tried to resolve them. So if you notice from the very first version of it that I presented, going to what Milad presented, and then finally what Nabil presented, we have identified different issues and then we have solved them one by one. The one we've got at the moment looks good. I mean, I don't know if there is any particular limitation that Nabil you're aware of that we should still rectify, but it is working pretty well at the moment. So it is actually ticking all the boxes, but the more you dig, the more you find issues. But so far, this ticks all the boxes, and we couldn't actually find a scenario that we are unable to operate or we are unstable. So far, it's been actually working pretty well, both in all different practical scenarios. One thing that we probably should be doing here, doing a little bit more studies on transient stability of this. We probably, small signal stability, we've done a pretty solid job, but transient stability, we need to do more work to see whether it becomes unstable and whether we can make it stable by adding different features. But yeah, so far I can't tell you any problem. So far so good. We'll see. Yes.
Do you think it's a good idea to test these control strategies with the DMAT, for example, the dynamic model assessment?
Actually, that's a pretty, yes, I guess that's something that we can do. We can actually go through all the tests and do that. We can do that. But most of the tests are anyway similar to the tests that we do, regardless. I mean, although we don't call them DMATs or any particular name, but yeah, we do almost all of them. But it's good to actually have a look at the DMAT list of tests and make sure that the tests that we are doing cover those actually scenarios as well.
And maybe also provide some feedback to the regulators if that's their
correct. We can do that, and then probably we can publish the report to that on our website. Thank you for that. Yeah, thank you. Okay, any other questions online? No questions? No, we're good. Okay, I guess we're right on time. We go for a 15-minute break, and we guess we have most people back in the room. I guess we can start our afternoon sessions. So in the next couple of presentations, we'll be focusing on grid forming inverters. So we've done a pretty large amount of work on grid forming inverters in the last 3 years, last 30 months. And a few of our researchers have been focused on this concept. This is one of the biggest parts of our research groups, and we will continue development in the area. But today we'll be sharing some of the concepts that we have developed over the last 30 months, and Dayan will be presenting the first one. Dayan Rathnayake received a bachelor and master degree in electrical and electronic engineering from the University of Pradenia, Sri Lanka in 2014 and 2017. He is currently working toward the PhD degree in Monash University, and I believe he has just submitted his thesis as well. His PhD is on design and control strategies for battery energy storage-based inverter-based resources. His PhD work is primarily focused on designing controllers for grid forming and grid following inverters in inverter-based resources dominant power networks. During his PhD, he was also involved with developing Australia's Global Power System Transformation Research Roadmap, which was published by CSIRO through engagement with the Global Power System Transformation Consortium in March 2022. His research interests include control and stability analysis of inverter-based resources, grid integration of renewable energy resources, and battery energy storage systems and their application in large power systems. He is currently working at AEMO as an engineer within which team? Grid Performance and Integration. Grid Performance and Integration. So Dayan, the floor is yours, and yeah, thank you.
Thank you, Behrooz. So I'll be putting on my Monash hat today and be talking about what I did on the grid forming inverters. Right. So I'll be presenting 3 projects that we did under the ARENA project. The first one is the generalized virtual synchronous generator control for renewable power systems. Okay, probably skip this one. We all know that the renewable energy generators are here, and yeah, they're here to stay, right? And a lot of power systems in the world, they're integrating more and more renewable energy into their systems, right? And that comes with its challenges. So reduction of synchronous inertia, reduction of system strength, reduced fault current, and increased control interactions and oscillations. There are several solutions to address these concerns, and grid forming inverters is one of them. And if you do a quick Google trend analysis, you can see the grid forming inverters has been trending for the past decade. And there are several good reasons for that, actually. They have superior performance in weak grids over grid following inverters. And they're capable of providing system strength and inertia to the system. And also they are capable of operating in grid connected and standalone modes. Okay. The virtual synchronous generator control is probably the most prevalent control type used in grid forming inverters. It is based on synchronous machines. It's based on the swing equation of the synchronous machine. So it has similar properties that you would find in synchronous machines. For example, the droop coefficient and also the inertia coefficient or the virtual inertia coefficient. Now, you can mathematically prove that unlike in synchronous machines, these parameters are more flexible in grid forming inverters. So it's up to the designer to choose these parameters. It can be shown that we have to carefully choose these parameters because they are sort of interdependent, or not interdependent, but they have a certain trade-off. So if you choose to have a large virtual inertia provision, you can end up with a deteriorated step response. So if you look at the second graph, that would tell you how the frequency would change if you subject the grid forming inverter to a load change. If you choose to have the rock-off or the rate of change of frequency to be low, or if you want to have a high virtual inertia provision, that can cause high overshoots and longer settling times in the step response. So it can actually deteriorate the step response of the grid forming inverter if you use the virtual synchronous generator control. And if you choose to have low overshoots, that can compromise the virtual inertia provision capability. Now, in this work, what we did was we introduced more damping to have low overshoots and low settling times without compromising the virtual inertia provision capability. And we call this controller the generalized virtual synchronous generator control. We call it generalized virtual synchronous generator control because it is flexible enough to achieve different controllers from the frame control structure. So if you choose the controller gains carefully, you can achieve either a droop controller or you can achieve a more sophisticated second order controller. So it's up to the designer. But the control structure facilitates the design of the droop control or VSG control or the generalized virtual synchronous generator control. Okay, now that we have, I have to tell you that it's also based on power synchronization. So we take the power inputs and then it will output the frequency, and then from that we can get the angle to synchronize to the grid. Now that we have defined the controller structure, we have shown that if we choose the controller gains according to these equations, we can guarantee that the grid forming inverter would comply with a rate of change of frequency that we would specify in the design stage. So therein, we can guarantee that it would comply with the virtual inertia provision capability that we would specify in the design stage. That actually directly correlates with the high frequency gain of the controller. Okay, now that we have solved the issue with the virtual synchronous inertia provision, now we have to figure out how do we solve the issue with the overshoot and the settling time. So in this work, we showed that if we choose the controller gains based on these equations, we can maximize the phase margin of the open loop transfer function. So the phase margin would obviously translate to the damping, and also it would achieve sufficient bandwidth such that it would have reasonable enough settling time. So I'm not going to go into too much details, You can find more details about this controller design and the controller in this paper. So we wanted to go a step further. We wanted to have more damping. So what we did was we looked at the closed loop transfer function, and you can see that there's a 0 there. So when you have a 0, usually it results in overshoots. So what we did was we took that 0 and put that in the feedback path so that it acts as a compensator. So that would not affect the virtual synchronous inertia provision capability, but it would get rid of the 0 in the closed loop transfer function. And then we rearranged the controller such that it is implementable in a digital controller, because this type of a controller is not implementable. So we changed the configuration without affecting the open loop transfer function or the rock-off relay compliance. And then we tested the controller in a wide variety of grid conditions. So we tested the controller in a strong grid as well as in a very weak grid. Now you can see that the proposed controller, or the two proposed controllers, actually results in low overshoot and a low settling time in both strong and weak grids. And then the performance of the two proposed controllers is fairly consistent when you're going from a strong grid to a weak grid, or when you're going from a weak grid to a strong grid. So let's say you have a lot of outages in the system, and your system and the system strength is different to what you designed the controller for. And if you have a VSG, you would expect your performance to be a bit different, but with the proposed controllers, the performance will be fairly consistent, or we call it's fairly robust against the grid strength changes. And then we tested this controller in a standalone case to show that it can provide more virtual inertia than a conventional virtual synchronous generator. Now you can see that the rock-off, the initial rock-off, is much less than a conventional virtual synchronous generator, as well as over the time, the rate of change of frequency is much less with the proposed controllers. Obviously, the controller can support the grid during grid disturbances. So if there's a frequency disturbance in the grid, it can inject more power and it can support the grid to recover from that frequency disturbance. And one of the important things about this controller is that we designed seamless transition strategies for this type of grid forming controllers. So it can transit between grid connected mode as well as standalone mode without causing a disturbance to the grid or without causing a high frequency change when it is transiting from grid connected to standalone mode. And if you look at the other graph, you can see that when it's connected to the grid, it causes minimal disturbance. It causes no disturbance at all. Okay, let's revisit what we found out. So we proposed two new controllers that results in low overshoot, which means it has enhanced damping, and also it has more virtual inertia than a conventional virtual synchronous generator. And the control design is quite straightforward. It is based on the frequency response of the system. So it provides more learning into how the grid forming inverters are into their dynamic response, basically. The control design is basically two equations. So you just have to plug in the values and it spits out the controller gains. So it's that easy. You don't have to remember the control theory that you have learned. You just have to plug in the values and get the control gains. The control structure is quite flexible. You can achieve group controllers, VSGs, or the more sophisticated second order controllers. And then we have developed seamless transition strategies to switch between standalone and grid connected modes. Okay. In this piece of work, what we did was we saw that the generalized virtual synchronous generator control has few shortcomings. So we thought how we can address those. The challenges that we encountered when we are designing the generalized virtual synchronous generator control was, it was difficult to specify the performance specifications such as overshoot and rise time in the control design stage. It was more about maximizing the damping. So we left it to the control design to give us the best damping possible. So if we wanted to define a range for the overshoot and the rise time, it would be a bit difficult. And only simplified parametric models could be used in the control design. And the last one would be if you wanted to design multiple controllers for multiple grid forming inverters simultaneously, that's a bit difficult with the previous approach. So in this piece of work, we proposed a second order discrete controller. And then we used an optimization based technique to design that controller. Now, the good thing about this controller is it can work with non-parametric models. So what I mean by non-parametric models is you don't need to model the system using first principles, using the physics. So you don't have to write equations. This is especially advantageous if you have a more complex system to deal with. If you're dealing with a lot of elements, if you have difficult to model dynamics, it's easy to identify a system than try to model it using first principles. So this model, this control design can work with identified models. And then we run a mixed sensitivity optimization problem to get the control gains. If you want to read more about this control design approach, you can visit this paper. It's also available in the project website. Again, we tested this controller in a wide variety of different conditions. It achieves low overshoot as well as low settling time compared to the conventional VSG approach or the virtual synchronous generator. And also it provides more virtual inertia than the conventional approaches. And it can design controllers for parallel inverters. If you want to design multiple controllers for simultaneously, this control design can also handle that. So we proposed a controller with improved damping and improved virtual inertia. But the good thing about this is you can design the performance specifications in the control design stage based on the sensitivity functions. How do you want to shape them? So if you can specify the output sensitivity to be shaped in such way that you can achieve a certain response time or maximum overshoot. It can work with both parametric and experimentally identified models. So you don't have to model them. You don't have to write them by hand, or you don't have to use MATLAB to do that. You can just identify the system. Oops. Yeah, you can simultaneously design multiple controllers as well if you would like that. In the last piece of work, I'll be talking about multiple or multivariable control design for grid forming inverters to decouple the active and reactive power loops. So in the simplest form, you can think of the grid forming inverters as a controllable voltage source. So what you are doing at the end, I mean, if you forget about the complex control loops. Okay. Yeah, sorry about that. So yeah. So if you forget about the complex internal control loops, in the simplest form, you can think of the grid forming inverter as a controllable voltage source. So at the end, what you're doing is you are changing the voltage magnitude and the angle at the point of connection, right? And if you remember a bit of basics, you can change the active power transfer by changing the angle, and you can change the reactive power transfer by changing the voltage. But that will only work if you have an inductive grid or the line is more inductive, right? But if the line is not inductive, or if the X to R ratio is comparable, if they are like similar, you'd find that if you try to change active power, that would result in a change in reactive power as well. So they will be more coupled. So if you look at the system model, you will have off-diagonal elements, non-zero off-diagonal elements. So we wanted to get rid of that. So we wanted to have decoupled active and reactive power loops. There are already existing decoupling methods, but they're not effective. They have limited decoupling capability. So we wanted to have we wanted to completely decouple the active and reactive power loops. So what we did was we proposed a multivariable controller where you have 4 controllers or a 2x2 controller. And the good thing about this controller structure is you can define, it can be based on prevalent control structures. It can be based on VSG control, or you can have different control structures to reactive control loop. So it can be based on a fixed error reactive power controller, or it can be based on a 0 steady state error reactive power controller. So you can define different control structures that you'd like, and then based on that, you can go ahead with the control design. Now, once you have decided on what type of a controller you want, we went with defining a desired open loop gain, where we would decide where we would specify the desired performance characteristics, such as the rise time or the bandwidth of the controller, and the damping that we would like to see in the step response. So once you have decided that, you can define the desired open loop gain based on the desired dynamics. Once you decide that, we used an H-infinity based optimization algorithm, which spits out the controller gains that would tell you, that would completely decouple the P and Q loops. So if you wanted to read more about the control design, it will be available in this paper. Okay, now we tested this controller to see whether it can actually decouple the active and reactive power loops. And also we tested its performance against the more conventional approaches, or more widely known approaches, such as the virtual impedance method. So in the virtual impedance method, what it's doing is it's tricking the inverter to think that the line is inductive, although it's not. But the problem with the virtual impedance method is its inductive capability is limited because of the voltage drop that it introduces. So you can see that the proposed controller completely decoupled the active and reactive power loop, even during the step change time. When you change the time, when you change the active power, and also when you change the reactive power, it dynamically decouples the active and reactive power loops.
Maybe you should talk about that VID. What is VID? I guess I don't know if you define VID, what it is.
Yeah, it's the virtual impedance decoupling method. And VSG is without any decoupling, and OMPC is the proposed approach. Yeah, thanks for pointing that out, Behrooz. So you can see that the proposed approach is actually better than the VID. It results in, so if you look at here, there's no change in active power when you change the reactive power. But in other cases, when you use virtual inductor, decoupling, and also when there's no decoupling at all, you can see there's a change. Okay. And we tested the controller during different disturbances, during frequency disturbances and voltage disturbances. And they ride through them completely fine. They don't have any issues with riding through those disturbances. We actually designed 2 different controllers for reactive power, fixed steady state error controller and also a zero steady state error controller. That's one of the advantages of this method. You can design different control structures that you want. It can operate in standalone mode as well. Okay, now coming to the key takeaways, we proposed a multivariable controller to completely decouple the active and reactive power loops. And the performance and the control design stage allows us to define the control specifications in terms of frequency domain quantities. And then the proposed controller can be based on a variety of different P and Q controllers for grid-forming inverters. Yep, and this control design method is also, it can also work with parametric and experimentally identified non-parametric models. Okay, thank you very much. That's the end of my presentation.
Thank you so much. I'm not sure whether this microphone is working. Yeah. Working, right? Okay, cool. Thank you so much, Dayan, for this presentation. Actually, the controllers that Dayan presented will pave the way for some other interesting application, and Mohammad Hasan will be talking about that, namely grid forming control for wind farms. We'll show you some results on that, but very interesting approaches for controlling grid forming inverters, enhanced performance, and hopefully we can get more out of our grid forming inverters in the grid. Next presenter, I believe it's Nabil, and I forgot to introduce you, Nabil, previously in your previous presentation. I don't know, for some reason I thought that we have already introduced you. Dr. Nabil Mohammed received the bachelor's degree in electrical power engineering from Tashrin University in 2013, the MEng degree in electrical engineering from University of Technology Malaysia in 2017, and his PhD degree in power electronics from Macquarie University in 2021. During the summer of 2019, he was a visiting researcher at the Department of Energy Technology, Aalborg University in Denmark. He is currently a postdoctoral fellow with Monash University, Australia. His research interests include power electronic converters, renewable energy generation and integration in power systems, microgrids, energy storage and energy management systems, modeling and control of electric systems. So the floor is yours, and Nabil will be talking about another controller that we have come up with for virtual synchronous generators.
Thank you. Welcome back. So apart from my previous work on grid following, this piece of work, it is on grid forming, and I'm proposing a new controller for the VSG in order to mitigate all effects in grid connected mode, whether in strong or weak grid. So we will see here how we achieved that goal. In this presentation, I'll give like a brief introduction about grid forming, then about the control structure of the conventional VSG, and then what is the challenge and our motivation for this research, and the proposed adaptive VSG, and the evaluation of this controller in frequency domain as well in time domain, and then the research output. As we are mentioning from the morning here, that grid forming are paving the way to integrating more renewable energy resources into the grid, and they are mimicking the synchro generator, and they can increase the system strength as well the frequency stability throughout inertia. To say that the grid forming, they can control by different methods. The most like 3 well known is the droop and VSG and virtual oscillators. In this presentation, I'm focusing on the second one, VSG. to give like an idea about what is the main issue, the grid forming is operating as a voltage source, and then we do have our grid is as a voltage source, and in between is the equivalent impedance of the grid. And here is the main issue of the whole story about grid forming. So when this impedance have a smaller value, then we say our grid is strong, and it will face, it will pose a lot of challenges to control the grid forming. And when this impedance is large, it will like, we can say that the grid is weak and the grid forming can perform well. So this is exactly like opposite of the grid following inverters. So to summarize this slide, our main issue with the operating of VSG is the impedance itself. And in this presentation, I'll show how we can utilize this information to enhance the grid forming inverters. Let us go ahead. I'm showing in this slide the conventional control strategy of VSG. We do have inner current loops, inner current and voltage loops, and then we do have the outer power loops for the active power and for reactive power. In the active power, we are determining the damping, DP, and the inertia, J, and in the reactive power, we do have PI controller. So this is the conventional one. So for grid forming, they can operate in islanded mode and grid connected mode. In grid connected mode, we are expecting them to provide us with voltage support, frequency support, inertia, and as well, the most important is power reference tracking, which is the step response. If we look to again to the block diagram, we can see that the supplied active and reactive power from the inverter itself will be can be like determined by the power flow at the PCC between the grid and the inverter, and we can see that the grid parameter, the R and X, they are appearing in these nonlinear equations. So this is make it difficult for us to predict the behavior of the grid forming. Here is I'm showing how the supplied active and reactive power by the VSG will be like as a function to the grid strength. We are in the first figure, we are like testing for different SCR, 15, 3, and 1. We can see in weak grid, the blue line, the VSG have less overshoot. And when we increase the grid strength, the red curve, it have more oscillation, and it is the worst case with the third value. So the first figure with XR ratio fixed to 3. Now, if we change even the XR ratio while keeping the SCR is fixed, we are getting different response. This gives us like a one impression that we are in front of a lot of operation conditions. We're in front of a lot of uncertainties in the VSG, how it will behave in the system. What is the main cause is the X and R. Can we get rid of this one? Can we have a fixed response? So this is what we will explore in next slides. So the main challenge, we say that the performance of the VSG is strongly related to the SCR. It is strongly related to the XR ratio. And in strong grid, VSG have very poor dynamic response, such as significant oscillations, long settling time, as well large overshoot. Current solution, we can find like different solutions in the literature. Some of them, they propose new complex control techniques that they go to nonlinear and whatever. Or they assume the grid impedance is mainly inductive, and then they design the controller. Or they assume the grid is inductive resistive, but they assume the grid impedance is well known during the design, which is not the case. Because if you connect your VSG to low voltage network or to medium voltage, so the equivalent impedance will be like different. Then we cannot assume it as it is invariant parameter. It is the opposite variant parameter based on the location you install your VSG. The motivation of this work was, can we design a fully controllable VSG with a fixed dynamic performance, have the same settling time, the same overshoot, the same damping ratio, regardless of the grid that we are integrating to? And the second most important question, can we keep the control structure of the VSG as it is? What I mean is this one. Can we keep it as it is while we are designing a new one, just we change some parameter, instead going to nonlinear controllers and new control structures? So to answer this, to answer to these questions, the answer is yes, and this is what we are proposing here. We propose the new control called adaptive VSG. In this control, mainly like we do have four parameters in the active channel, the damping and inertia, and in the reactive power. So we are controlling those four parameters in the VSG adaptively to cope with the impedance value. How we did that? We started from the issue, the nonlinear equations of the power flow, and then we linearize the equations. Then we plot the block diagram of the small signal model of the VSG, considering the grid resistive and inductive. And then we determine the desired transfer function of the VSG in terms of like you want the settling time to be 1 second or 2 seconds, the damping ratio to be 0.7. So the desired transfer function for the active and reactive power. And after like the mathematical and manipulation of relations, whatever, we came up with these new values at the outer power control loop. More details, you can find it in the paper itself, which is on archive as well and on the website. It's still like, if we can see these parameters, they still related to the grid impedance. So we can't design any VSG without knowing the grid impedance. So we are in front of two scenarios where either we assume it will known, it is not realistic, or we enable the VSG to get information of the impedance in real time. So that is the most accurate solution. If we choose the second one, because of the importance of the grid impedance, as it determines the SCR, the XR ratio, and it is involving in the design, we came up with a very good idea that we implemented a software inside the VSG that estimate the grid impedance in real time. So now our VSG is working in two rules. The first one, what it means to be injecting active and reactive power. The second rule is its work as network analyzer to estimate the impedance. So we are using the VSG itself, no extra hardware. It is cost effective, no communication links because it is embedded algorithm inside the VSG itself. It is real-time estimation. We're getting the most accurate results, and it is automated. So the most important question, is this VSG will always keep estimating the impedance? The answer is no, because it is a computational burden as well, could disturb the system and power quality. So it is automated. For when it is needed, it will estimate again. And there are like different grid impedance estimation techniques. After like studying different methods, we choose the one which is based on the harmonic injection. We inject 75 hertz, very close to the fundamental impedance. And then we extracted from the response, the current and voltage response from the grid. And then we estimated the equivalent grid impedance to be approximated at 50 hertz, which is very, very acceptable results. This is the proposed algorithm like for the whole adaptive control. So simply like if we are in islanded mode, we are not facing any issue. So once the algorithm starts, if you are in islanded mode, so you will use just only the fixed parameters of the VSG. And then if we are in grid connected mode, the operator have the choice either to enable the adaptive terms or to keep it fixed. So if you want not to enable the adaptive terms, so it will use the fixed or design parameters. Alternatively, it will execute the algorithm will be applied to find the adaptive terms. So this is the final control structure of our new controllers. We are like keeping everything is as it is, similar to the conventional. However, we are changing the DP, J, Ki, and K and KP for the active and reactive power controller. And then we are injecting the additional small signal at 75 hertz to the inner current control in order to estimate the impedance RG and LG. So we propose a new control. Can we verify it? Yes, we verify it in using time domain simulation and then frequency domain. In frequency domain, we use the eigenvalues. Here we can see the conventional control. The poles are very closer to the imaginary axis, and this is indicating to oscillations in the grid, while our controller the poles are far from the imaginary axis, indicating to stable operation. As well, we cancel the third pole because we know the impedance, so that we only have a second order system that we can exactly control the settling time and overshoot of the system. So here is the analysis in the active power channel. Here are the analysis in the reactive power channel. We can see that we moved the poles from the imaginary to far in the proposed control, indicating to stable controller. We perform a lot of case studies and simulation, as well, like in the to tested in strong grid and weak grid, and then we compare it with the conventional VSG, and we had test the proposed control in the lab, and we tested for the same scenarios. In this presentation, I'll present just only the results in the lab. Okay, let us start with the simulation as I have them here. So this is the test at in a weak grid 1.5. We expect that the conventional VSG will still have like few oscillations, but it will be stable. This is the conventional controller, have small oscillation, and then it damp in a weak grid with SCR equal to 1. However, our proposed control is having a settling time equal to 0.8. This is what I did, what we perform here. We set the settling time of the controller to be 0.8. We can see that we do have a step response in the active power, two-step response, and then in the reactive power, while the conventional control have oscillations, the proposed control is free of oscillations. And we had the additional disturbance that to be injected to estimate the grid impedance. If we zoom here, we can see that we do have less than 5 ampere, just an oscillation for a period of time. And based on the response of this injected disturbance, the VSG can get like information in real time of the grid impedance for the adaptive control. Here is just only a zoom in on this additional disturbance, which is less than 5 ampere in the I'm showing as well here how the VSG is accurately estimating the impedance. I do the grid resistance and inductance. The green line is the reference, while the red one is the estimated. We can see very accurate results. Strong grid. The conventional VSG have more oscillations when we applied step response in the active power, reactive power, and we can see that our control keep exactly like the desired step response requirement as we are expecting. We test this concept in the lab based on a grid connected setup. We started with the conventional control in weak grid with SCR equal to 2.5. We can see that after applying a step response at T2, in the active power, we do have, there is oscillation in the controller. This is our proposed control. It is free of oscillation, and then we are like obtaining the step response within 1 second. Here is the injected active and reactive power by the controllers. Let's go ahead, and we are testing the system, the conventional of the proposed control in strong grid with SCR equal to 6.7. This is the conventional control, more oscillation compared to the previous case as expected. And this is the new controller. It is just very similar to the weak grid and the desired step response. And here the active and reactive power. The proposed control is free of oscillation 100%. So let us go to the research outcome. The negative impact of the grid parameter on the VSG have been revealed initially because we do have like a part of the paper for comprehensive review. When we compare how the effects of SCR and XR ratio will affect the step response. Then we proposed an online grid impedance estimation based VSG. So it have like good performance regardless of the grid parameters, and then it achieved desired dynamic performance in terms of no oscillation, specified time duration of the step response, and minimal overshoot. So this control is definitely have enhanced stability margin, and as well it can enable like reliable and safe integration of more renewable energy as well energy storage systems. I want to, as our new method is based on the online estimation, I want to have this conclusion. The advantages of the online estimation of the impedance by the VSG. First of all, the VSG is estimating by itself, so it is added function to the inverter. There is no additional hardware. There is no requirement for additional sensors or like network analyzer. So it is cost effective. There is no communication requirements. The algorithm is within the controller band, within the controller loop. So it is reliable and secure. And it is local impedance measurement. So it can be used for many different applications. If you can estimate the impedance, then you can use it for the adaptive control as well. We can use it for different applications like stability analysis, or it's super like it paved the way for many applications. So this is just the last 2 slides. As a part of this project, we are editing a book on grid forming power inverters here at Monash. This book is expected to be online in February 2023. It is the first, will be the first book in the world dedicated to grid forming. And key features of this book will be comparison between grid following, grid forming, and then the requirements and grid codes around the globe for the grid forming inverters. And then it will talk about modeling of VSG, control strategies, practical applications like battery energy storage systems and wind turbines, and then different applications like dynamic stability under faults and damping in power system, damping the oscillations in power system. So thank you so much.
Okay, thank you so much, Nabil, for this very interesting presentation. So as you saw, the last 2 presentations, well, we were focusing on control or new controls for grid forming inverters to enhance the performance of conventional virtual synchronous generators. What Dayan presented was essentially changing a little bit the control blocks of a VSG to provide better performance. And what Nabil presented was to conserve the structure, but add certain features to tune the parameters of a typical conventional grid forming inverter in VSG structure to behave better. and to get rid of all the oscillations that you might get because of the system strength and because of the change in your grid impedance. So both of them can be used to enhance the performance of conventional grid forming inverters. And in the presentation to come, when Mohammad Hasan will be talking about grid forming wind farms, we will be using Dayan's approach to actually to demonstrate how you can use grid forming capability in wind farms. Now I've got time for some questions before we break, and then we'll come back for next few presentations. Sorel.
Thanks very much. This is just a general one because I've been out of the know for about 10 years in this space, but how accurate do the transducers need to be? You mentioned that there's no need for additional hardware for the grid impedance estimation. How good are transducers nowadays? Are they like, what kind of tolerance are we talking about here to be able to accurately determine the grid impedance?
Okay, thank you so much for this question. We do have like the most important limitation is the as we are implementing this algorithm inside the control loop of the inverter. So one of the limitation is the sampling frequency of the inverter itself, which is much higher than the switching. The another limitation is the switching frequency of the inverter, because according to Shannon theorem, we cannot like exceed half of it. But here is the beauty that we are estimating at 75 hertz. We didn't have this limitation, but I work on different methods that when we like estimating the wideband impedance. In that case, we can't like go more than half of the switching.
But I guess the question was more about the accuracy of the sensors, current sensors, how accurate the current sensor should be, not the bandwidth, right? The accuracy of the measurement for your sensors, voltage and current sensors, so that your impedance estimation is accurate. That was the question. Rather than
So that is one limitation. And there, for the current measurement, I'm using the one of the inverter itself, the embedded inside the inverter itself.
So essentially what we used was a LEM sensor. LEM is one of the better manufacturers. The sensor that we used was nothing special. It was the sensor which was there for current control, and is pretty good, pretty capable. So we didn't have any issues with that. But just wanted to mention this, that LEM is currently actually manufacturing certain sensors with accuracy of 0.01%. Extremely accurate. Of course, expensive, but extremely accurate. So the current sensing technology is actually pretty advanced. So absolutely no limitation from that point of view.
So no need to like degauss or anything like that.
No, it's just fantastic. I mean, the sensors, they're again a little bit expensive, but they've just released it, and we actually use them for some other applications for inverters for motor drives. Extremely accurate, extremely accurate.
Okay, to add to that, like we're injecting 75. So it is in time domain will be like require like almost 50 milliseconds. But what I was injecting is 200 milliseconds. So this means like make the estimation is more accurate, because we're expanding the window of the FFT. Yeah, and as well like it is according to the standard from IEEE to have 5 hertz frequency resolution to capture the interharmonics. Yeah, this is why alternatively I can even like I got a good simulation results with just only injecting a one period of 75 hertz. But to be more realistic, I extended to 200 milliseconds. Yeah. No worries. Thanks.
Any questions online?
Sorry, Behrooz.
Yes.
Can I provide some comments here?
Yes, please.
Thank you. So just a question from my end, Nabil. When I saw your structure for the virtual synchronous machine, I haven't seen any synthetic impedance or inductance to be modeled for that VSG. Is that correct, that there is none considered?
Maybe go back to your block diagram and explain on your block diagrams.
Actually, I do have like the impedance inside.
Go to the next slide, I guess, number 15, maybe.
I think the minus not all.
It is this one. So like we start in. Yeah. So was the first step in the design, we started with the nonlinear power equations, and then we linearized them. After that, if we look to the small signal model of the VSG itself, and then we do have the active power channel and then the reactive power channel, the K11 till like K22, they are included in the linearized model, the grid parameters. And if we go to slide 16, I know that you can't see like the grid parameters there, but they are embedded inside the coefficient of K22, and we do have sigma and sigma. So I'm not showing the sigma and as well like especially like the sigma, but it included both of them, the grid impedance, the resistance, and the inductance.
So the answer is that your grid impedance is kind of embedded in your JD here. So if you go back to the block diagrams, if you go to the,
What I mean, Behrooz and Nabil, is about the conventional VSG that you're talking about, and you showed us the results. Is there any synthetic impedance for the VSG? Or basically for the synchronous machine, considered for the VSG, for the conventional VSG, or it was just pure active and reactive power?
Yeah, no, I think you didn't have any virtual impedance in the conventional, right? You just
no.
Yeah, no, there hasn't been. No, that's yes.
Because of because those oscillations or oscillatory responses that I see that is dampening. One of the reasons that you saw there, those oscillations or those behaviors is you don't have any dampening component in your VSG. So basically the result that you show, when we're talking about VSG, there are multiple components that needs to be included. Among them is that synthetic impedance that you have to consider. Otherwise, what you are referring to could not be the most advanced or sophisticated form of VSG. Of course, it's a broad range when we're talking about grid forming inverters, starting from voltage and frequency regulatory behavior or mechanisms up to the most advanced and sophisticated forms of VSGs with all the components being modeled in there. So that's one thing. The second thing is, again, you can, well, that's commenting on Dayan's work, your work, and what Behrooz mentioned initially about the issue that grid forming inverters might face when they're connecting to the stiff grids. Yes, think of the two voltage sources that they're going to connect together and control a voltage. They're definitely gonna fight together to control that voltage. What's the solution? Solution is putting in the impedance there in between, so you can control the power flow, and the voltage can be maintained, control at both ends. So the same thing can be considered for a virtual synchronous machine. You have to ensure that you have of course, you have the transformer. It's a form of inductance that you're connecting one asset to the other one, the two generations, a synchronous machine to a grid forming, a virtual synchronous machine. Then you have the filters, they have inductances as well. So their form of sharing, you do have droop, they're also sharing, and make the voltage sources to be less stiff. And also on top of these mechanisms, you also have this virtual synthetic impedance that can be modeled in your system that helps you with smoothing out the responses and letting the voltage source mechanisms to operate together. It's similar to other synchronous machines that are connecting in parallel. You can connect like 10 diesel gens or gas turbines at the same time, and they can operate happily together. So that's my comment. And that's it. Thank you.
Yeah, no, absolutely spot on. You're absolutely right. All of the comments. One thing that we wanted here to show, we wanted actually to emphasize or exaggerate a little bit that, okay, this is the way that VSG works. And if you tune the parameters based on the knowledge of the grid impedance, you can make a better VSG. But absolutely right. Using the virtual impedance will help and will actually dampen a little bit the what we are seeing here. But I guess still, even if we have that virtual impedance, these oscillations won't go away completely. But of course, it will help a lot. That's absolutely right. I guess.
Yeah, there is no issue with coming up with new ideas, and I really appreciate that. I do like those ideas and control methodologies that's been introduced throughout this presentations. Really, thank you. Just one more comment that just came to my mind is the even the dampening method that used for the inertia could be designed in a better way to give us a better performance. Dayan, of course, suggested very good ways, but there are other also mechanisms or other options that can be considered. So when we're talking about VSGs, it's good to highlight that again, it's a broad range.
Of course,
you can go from a very primitive kind of design and response to a very advanced and sophisticated one. Thank you so much.
Absolutely. Larissa, yes.
Question?
Yes.
David Q on the screen and so ask a question.
Oh, David.
Hi, can you hear me, Behrooz?
We can hear you, yes.
Great. I'm finally allowed
yes.
into. Sorry, I've been a bit locked out here. Well, first of all, I want to follow Tony Markson's comment with my own general comment about the work, which I think I can do because I'm a newcomer to Monash University. So I can see all this work as, as something that I'm not yet connected with. And then secondly, I have a question. So the general comment is quite simply to praise the work, not only for its importance to the energy transition, but also I've not seen a program of work in the whole world that combines this knowledge of power electronics and control design. They're separate areas, power systems, power electronics, control design. So as someone who's lived his career with, Lyapunov and robust control and adaptive control, I'm just really impressed with the results that I'm seeing here today. Secondly, just a question. You really got me excited when you started talking, and Hasan has followed up on that, so I won't say too much. This idea of how the different types of inverters can coexist. I mean, we're not going to have 100% for a long time, if ever, because we'll probably still keep hydro, and who knows, maybe CSP will have a role one day. But high inverter systems with different modes can have the potential to fight with each other. So it begs a planning, once we finish with all this stability and control, there seems to be a major project just planning how these different devices coexist, unless you can invent an inverter with a switch on it to go from, grid forming to grid following, and you just switch according to the situation. I don't know if that's a very fantastic idea or not. It seems to me there's a big planning question here for the Australian grid about, obviously one guideline is to put grid forming, out on the ends where the grid is weak, but that's probably too simplistic. So yeah, I see a lot of work here to follow up on what you've begun. As impressive as it is, there's a lot of things to do here.
True. Thank you so much, David. Very much appreciate your kind words. And yeah, I believe there's still a huge amount of work in front of us to be done in the coming years. And the more IBRs, I guess, we integrate into the grid, more challenges will be there. And as I always say, there's so many unknowns in this area that, you know, who knows what's going to happen in 2 years from now. So yeah, interesting times ahead of us, interesting time ahead of the Australian power industry, and hopefully we can assist with this transition as much as we can at Monash. So if we don't have any other questions,
Still two online questions.
Oh, online questions. Yes, can you please read them?
Yeah, the first one was, in a weak grid condition, does the real-time grid impedance measurement cause any power issues? The simple answer, it causes minimal issues because of two things. The first one, it is automated, so it is not all the time injecting harmonics. I would call it inter-harmonic 75. And it is like the injected is 5% of the inverter nominal power. And then you can even control it till like 1 or 2. So we are like affecting the power quality, but it is in a minimal, as minimal as we can. Yeah. And the second question was, why measuring the impedance at 75, not 50 hertz? That is very good, because our interested is 50. Because the power system fundamental frequency is 50, we can't measure the impedance at 50 directly. So if it was like 60 hertz, then we can inject 50 hertz and estimate the impedance. So it is because the 50 is the fundamental of the grid, and it is the fundamental of the VSG itself.
Yeah.
Yeah.
Okay. Yes, Bruce.
Okay, just a quick question then. At the moment, when you register a new generator, you've got to model the inverters and go through all Schedule 5 requirements. Now, with this approach, we probably have to model how the model adapts to the grid. So have you given any thought to how that would work in practice?
Was the answer to get like the real-time grid impedance estimation in order to mimic how it will be in the practice in the real grid, and we tested in the lab as well on experimental result on experiment setup when the inverter is connecting to the grid itself, so it is not isolated from the low voltage distribution network. But was the idea is when we put it in practice, is it will work or not? So this was one of our motivation to get real-time estimation.
So I'm not sure. Thank you for the answer, but I'm not sure whether I got the question exactly. So can you maybe paraphrase it for me?
Yeah. To register a generator or to register an inverter-connected plant at the moment, we model it, do a number of simulations to work out its responses, etc. Now, in this approach, you're not just modeling how the inverter behaves with certain parameters, but you also have to model how the measurement of the grid will set the parameters in the inverter equipment to give you the response. So I suppose it comes down to how do we model the accuracy of that process in a practical grid circumstance.
Yes, yeah. I mean, it is essentially adding, I would say, another kind of, fair to say, complexity to the connection process, because again, you're adding another thing to the controller. But at the same time, it is helping the IBR to provide better performance for you. But I hear you. I mean, when it comes to connection studies and things like that, I mean, of course, this is something different. It adds, as Nabil said, a little bit of power quality issues, but that's minimal. Now, when you look at it as, I mean, if you look at it as a black box IBR, right? If you don't know what is inside this one, so you probably can treat it similarly compared to a normal IBR without this, a normal VSG or normal grid forming inverter without this approach. So from connection point of view, because you don't know what's inside, this is part of the control, right? It does something, and then, so you can do all those tests, right? And see whether it ticks the boxes. And probably this ticks the boxes better than a normal grid forming inverter, because helping to improve the performance and the response. And again, because you don't know, as the let's say consultant doing this study, you don't know what's inside this. It's just helping, right? So I think it shouldn't be a problem from connection point of view, because simply, you know, it's yet another control layer which is helping your performance, and you don't have access to it, right?
Yeah, I totally agree. Can you get AEMO to agree?
Yeah. Tony.
Behrooz, if I can just add a comment in response to Bruce, that it is clear that this work poses challenges for OEMs, but it also poses challenges for AEMO and for the rule makers. It's the existing processes may need to be adapted to take account, as they don't do at the moment, to take account of variations in wide area grid conditions as the ISP gets implemented. It is clear that many areas of the grid that we currently describe as weak, in 20 years' time are probably not going to be weak. And so how do you do the connection studies at the moment? You do them on the existing circumstances, and you're going to have countervailing factors. You're going to have large generators dropping off the grid, which is going to tend to weaken it. And you're going to have new transmission commissioned, which is going to tend to strengthen it. And it's the idea of doing a connection study which has to span the entire life of a wind farm and say, okay, it's okay to connect now, but we want to know this thing is going to work in 20 years' time. That question is not really being asked at the moment. So yeah, there's challenges for the regulators and for AEMO and for the rule makers, as well as the OEMs at the moment.
Tony, so I guess it's a good time to break, and we will come back maybe at 4:10 for our last two presentations. We will be having two very interesting presentations, one by Si Phu, who will be talking about fault recovery of grid forming inverters, and also a very interesting presentation from Mohammad Hasan talking about grid forming capability for wind farms. So we'll be coming back at 4:10. I think we can start our last session of the day. I guess everybody's back in the room. So I guess I have already introduced Mohammad Hasan. There's no need to introduce Mohammad Hasan. So in the last two presentations that we've got, we'll be talking about two interesting concepts on grid forming inverters. One of them will be grid forming capabilities for wind turbines. So this is a very interesting concept that we are hoping to see deployed in practical power system in practical wind farms. And Mohammad Hasan will be talking about this. And finally, Si Phu will be talking about fault recovery of grid forming inverters. So the floor is yours, Mohammad Hasan. And yeah.
Hello again. In this presentation, I'm going to talk about grid forming capabilities for wind turbine generators, as Behrooz explained. Again, I have similar slide like several presentations we had, but I'm going to look at it from another point of view. This is the map of weak points on our grid. But the point here is that if we have a better look at a specific area like the Victorian grid, my intention here is to say that there's a good overlay between the points with weak points of the grid and also the point we have solar farms and our wind farms. So why is that? The reason is most of the current grid wind farms and solar farms are in grid following mode. So, and we want to install more. So it means we are deteriorating the situation. To get rid of this, grid formings emerged. As we talked about this difference several times in the previous presentations, the main difference is that a grid forming can work similar to a voltage source, while a grid following inverter is mainly a current source. So for grid forming, we technically can form voltage and frequency at the point of connection of the farm. Currently, the existing grid forming, we have all our battery-based, battery energy storage system based. I mean, if we look into the energy source, this energy source is connected to a battery. And when it's connected to a battery, the DC link voltage we had in the previous slide as the energy source in the DC side, the voltage is constant and is fixed by the battery system. So the parameters we need to take care of them are frequency and also active and reactive power, voltage, PCC voltage, point of connection, point of common coupling voltage, and also the grid side current. We also have some real examples for BESS-based, BESS GFMIs around the world. I have brought 3 examples here. A GE BESS in Imperial Irrigation District, one in Eustatius Island, and one in Australia, Hitachi ABB Dalrymple BESS. Now, let's think from an overview point. What services BESS GFMIs potentially can provide? We can divide them in 3 different categories. Services relating to stability, services relating to operational services, and power quality services. When we say stability services, we mainly mean inertial and frequency control, system strengths, having power system stabilizers, and also the robustness and disturbance rejection. And when we talk about operational services, we mainly talking about the restoration and the capability to operate in the island. Now, the question is, currently, we need to install battery system to have grid forming capability for the system. Batteries are expensive. What about using non-BESS GFMIs, providing grid forming capabilities with other devices, other components in the grid? To answer this, we should find between different features I showed you in the previous slide, what are the key features of a grid forming inverter? Based on what we found in the literature, we can say that there are 3 key aspects that if we have them in a inverter-based system, then we can say that this device, this component is a grid-forming inverter. First of all, a grid-forming inverter must, I can say, form frequency, also form voltage. And the other thing is, which is related to the previous 2 items, is to containing an energy buffer for that. I will talk about it more later. So technically, each inverter-based component in our grid, which can have these features, 3 main features, can potentially be retrofitted to be a grid-forming inverter. Now, in this slide, I've provided several options we can have for a grid-forming component in the system. Most of them right now aren't available in the real world, but they are under study, and at least for one of them, we had a try in the real world. The first option is wind farms, type 4 wind farms. For type 4 wind farms, I have provided a table with 5 columns, 5 main columns, talking about the energy buffer, the control complexity, and also the type of services I mentioned in the previous slides. I'm not going to go through all these details, it takes time, but my main point here is that if we look into this table, we can see that based on the features I mentioned as the key feature of a grid forming inverter, wind farm type 4 and also wind farm type 3 are the best options to be our best GFMIs. The difference is in the control complexity, which I can say for type 3, it's more complicated. Anyway, still, it's a valid option. And this is something we're going to work on it later in our team. Now, keeping this in mind, also it's better to just mention the other options. We can have grid forming with PV solar farms. We can have grid forming capabilities with HVDC systems and also STATCOMs, even as STATCOMs. This is something we are looking into it as our extension of our works. And one thing important to think about as a difference between these options is looking into the energy buffer, because providing grid forming capability means you need some sort of energy, having a reserve energy to use it, similar to a synchronous generator. A synchronous generator had kinetic energy. It was released when it was needed after a fault or a specific situation in the grid. We need to provide such energy buffer when we want to have a non-BESS GFMI. For wind farm, we basically can have 3 different energy buffers. It's not necessary to have all of them at the same time, but we can use each of them as per the requirement of the system. We may implement, we use our DC link as the energy buffer. I will talk about it later. Or we can use the rotating mass of wind turbine generators, or just the loading from the maximum power point, because we usually use our renewables using a MPPT, maximum power point tracking controller, to make sure that we are harvesting the maximum energy from the grid. We can distance from this feature, but having a reserve to provide grid forming capability. Okay. Now, so I said we are more interested in grid forming for wind turbine type 4, and I explained why. But the most important advantage of having grid forming with wind turbine is that if we can equip our existing wind farm with grid forming capability, it is we can say that the best cost-effective way for addressing the issues we have, because we don't need to install any new hardware. All things are just control things. However, we may have some limitations we should consider. First of all, unlike the battery BESS-based GFMIs, the DC side is not constant anymore. So we need to use a control system to make sure that the DC link voltage is also in the permitted range. Also, when we implement grid forming for wind turbines, our energy side is not decoupled from the grid side anymore. And it may result in some issues, some difficulties for the system. Also, in addition to DC link voltage, we need to make sure that we are regulating the wind turbine rotary speed and also machine side converter control. And the other thing is, important thing about grid forming for devices like wind turbine is that we may need to provide a black starting feature, and providing black starting feature is more challenging for wind farms. Finally, in the presence of an event, the energy and the rate of change of energy we can provide is limited compared to a BESS GFMI. Now, and I also mentioned that we had one example, real-world project, which was used in the grid forming mode for a limited time. A farm in Scotland was used in the grid forming mode for 6 weeks. And they reported that they have applied some tests and the response was satisfactory. However, they also mentioned that they had some limitations, which are obvious. First of all, the operation is a function of the operating point. If we don't have wind, so we cannot provide anything for the system. So wind speed, when the wind speed is declining or it's very low, we would have issues for providing grid forming capabilities. Now let's have a deeper look into the details of implementing grid forming for wind turbines. This is a schematic of a simple SMIP model of a wind turbine generator, type 4 wind turbine generator connected to an idle grid through a transmission line model. And we have a control system all things are happening in this control system, the differences between grid forming and grid following. To have a better look, I provided a schematic of what happens inside the control system for wind farm. For wind farm, we have a PPC, power plant controller, which provides dispatching references for the units, active and reactive power, using an AVR, automatic voltage regulator, and also governor. We may have a machine side master controller, which is responsible for providing references for the torque, for pitch angle of the wind turbine, and the functions relating to power curtailment. I mentioned about when I was talking about the energy buffer. And also, we know that wind turbines, their mode of operation is a function of the wind speed. If the wind speed is higher than a limit or lower than a limit, then we should stall the wind turbine. Otherwise, we may have some mechanical issues. All of these things are implemented in the MSMC. Also, we need a PAC, pitch angle controller, which is responsible for, we can say, rotary speed protection by curtailing power for higher wind speeds. We always have a chopper to protect our DC link, and the most important blocks, which are where the differences between grid forming and grid following are shown. MSC, machine side converter, and GSC, grid side converter. For a grid following inverter, the machine side converter is responsible for regulating the active power and also taking care of reactive power at the machine side. And the grid side converter is responsible for grid synchronization using PLL, controlling the VDC, the thing which we were assuming that is constant for a battery system, and also the reactive power or voltage at the grid side. This is the grid following system. If I want to show more details of machine side and grid side, for providing active power controller, we use a relation between torque and current. For machine side and also for the reactive power control at the machine side, we need a Q or V controller. I've shown them here in these slides. And also for the grid side converter, we need the PLL, similar to what we shown in our previous presentations. We need to regulate VDC link, and also we may regulate the reactive current, reactive power at the grid side, or the voltage at the grid side. Now, I'm gonna upgrade my grid following inverter, grid following wind turbine from GFLI to GFMI. Functionalities needed to be added are, first of all, we need to provide frequency formation. In the previous schematic, we didn't see anything about frequency formation. We had a PLL, which just let us track the frequency and angle of the grid, the voltage grid. But we need to form the frequency with a grid forming wind turbine. Also, we need to have the capability of forming voltage. Since we are departing from a current source to a voltage source, to make sure that the system is safe during and after a fault, we need some sort of current limitation techniques. For grid following, it's important, but for grid forming, it's more important because grid following is some sort of a current source. And a current source, it's we can say safe when we have some faults in the system. Also, as Hasan mentioned in the Q&A session of the previous presentation, we also usually implement virtual impedance to make sure that we can improve the performance of the grid forming inverter in case we have lack of damping in the system. To implement these features, we can have two different approaches. The first approach is forming the frequency on active power, the well-known one, and the other way is forming the frequency on the DC link voltage. Here, I just comparing them, and I just want to mention that the method one, implementing grid forming on frequency on active power, is more desirable because of the features it has. And we select this one. We have selected this one for our implementation. First of all, the capability, grid forming capability you can provide is higher with the first method. While with the second method, it's limited. The energy buffer for the first one is the rotating parts, or if the reserved power. But for the second method, we use the DC link as our energy buffer. For the first method, we need to upgrade both machine side and grid side converters. However, for the second one, we only need to take care of the machine side converter. And the other thing is, when we use the first method, the grid side controller would be completely similar to a grid forming base, which was emulating a synchronous generator. So technically, we are emulating a synchronous generator. However, with the second method, we are not doing like that. In fact, the second method is useful when we have limited amount of energy resource, which can be adapted for specific structures like a STATCOM. Now, for the first method, method 1, PPC, MSMC, chopper controller, and PAC are similar. We don't need to change them. But for the grid side converter, first of all, we need to implement that grid formation and synchronization. And also, we need to implement the active power controller. These are the differences with the grid following one. In the grid following one, the output power was controlled through MSC. But here, we want to control it with our GSC to make sure that our GSC is completely similar to a battery system. And since we have used all the degrees of freedom we had, control degrees of freedom we had in GSC, we have no choice but using MSC to regulating DC link voltage. And the differences in GSC and MSC of a grid forming with the grid following, you can see them with these blue boxes in this presentation slide. It's good to mention that in our team, we had several studies about this primary controller. Dayan presentation and also Nabil presentation were both focusing on these boxes, this primary control loop. Also, the presentation Si Phu is gonna present after me relates to this virtual impedance. And also, I myself had a paper on voltage control about the impact of feed-forwards on the stability of the grid forming. I'm not going to talk about it anymore, but you can find it. It's not published yet. It is also at the end stages of publication. It would be published very soon. I can say maybe in the next 2 or 3 weeks. And after that, we will put it on our website and you can find it there. And also, I had some other studies on the primary controller. What about the second method? The second method, again, PPC, MSMC, CHC, and PAC are similar. In this method, the MSC is completely similar to what we had for grid following, but in the grid side converter, the grid formation and synchronization, VDC link control, and also reactive power at the output reactive power of the farm, all are controlled in the grid side controller in the using these blue boxes here. Since it's not our focus, I'm not gonna explain this one anymore. So right now, I've explained what we needed for a grid forming wind turbine generator. I'm not gonna go through the details of design. It's not in the scope of this presentation. Now I'm gonna show what we've done in terms of implementation. First of all, we started from MATLAB Simulink. We tried to have the most detailed EMT model we can think about to include all the requirements which can work in both grid following and grid forming mode. And we included a detailed model of back-to-back converters, the rectifier and inverter, or I can say machine side and grid side converters. Also, we considered the model of wind turbine model itself, a 2-mass drivetrain model, all the controller block I talked about. For also a very important feature we considered when we were designing and implementing is that we designed filters and also control systems all in per unit. It means that you can easily change the rating of the system as you want because everything is designed, controllers, filters in per unit. You just need to determine the rating of the system, the power rating and voltage rating, and everything is designed automatically. Also, we considered different types of active power controller, reactive power controller. My colleagues talked about. We also implemented CGVSG Dayan talked about. Also, we implemented different reactive power controller here, droop method, a well-known method as rotor flux model. We implemented all of them. User can easily select between them with some options on the GUI, the model. And also, we tested the system with as a SMIP case connected to an idle grid, a tunable SCR and XR ratio. We tested the system for IEEE standard to area for machine system. They usually mention it as condor case, and also IEEE standard 39 bus system. These are all what we did in simulating environment. Also, we implemented all of these things in PSCAD. We implemented all those blocks again with the per unit format in PSCAD, so a user can easily select the parameters at the GUI of the model and change the form as the user wants. And also for this case, we tested two different cases. First of all, a case where the farm is connected to an idle grid with tunable SCR and XR ratio, meaning the SMIP case, and also a larger scale, a real world network. Here, I'm just gonna show some results because I believe we don't have more time. For the SMIP case, a wind farm, including 104 megawatt wind turbines, are connected as a farm to a weak grid with SCR2 and XR ratio 2. Here are the simulation results. First of all, I wanna say that you can see at the first seconds of the simulation, the system is working fine. This is one fine. This is one output we wanna talk about. Then at T6 second, we have a 3-phase fault to ground near to the farm. After 200 millisecond, the fault is cleared without any tripping. And as you can see, the farm can perfectly withstand this fault. For the second scenario, we applied another type of fault, another severe fault, phase jump, 20 degrees at T6 second, and minus 20 degrees at 8 seconds. And as you can see, again, the system can perfectly withstand this fault. Also, we tested our farm with a real world case, as I said. Here, at T30 seconds, we had a 2-phase to ground fault on a 220 kilovolt line. One side is tripped after 120 millisecond, and the other side after 220 millisecond, and the fault duration is 220 millisecond. The bolded brown curve shows the response of the system when it's in the grid following mode without our inverter. And as you can see, it's almost reluctant regarding the fault because it's in grid following mode. However, when we use the design controller, the grid forming wind turbine, we use the grid forming mode, you can see that the wind farm reacts to the fault similar to a synchronous generator. And I can say that the system response is improved. It's not easy to show it here because we had a small, I can say, a wind farm comparing to the overall generation of the whole system. But still, if you just compare the overshoots of synchronous generators, the black traces in these figures, compare them, you can see that since the wind farm now contributing to providing after fault services, during and after fault services, inertial responses, and also inertial services and other things, you can see that the responses of the required actions of other generating systems reduces, which is exactly what we need. Also, as I said, it's not really clear how much improvement we had because of the grid forming. The better way to do so is to use a method of impedance identification technique. Already Weihua and Nabil talked about identification methods in their presentations. For this specific case, we also developed a specific PSCAD toolbox, which can identify the impedance or admittance of a farm and also the grid connected. The interesting feature of this thing is that all things are all happening in PSCAD, meaning that you don't need to do any post-processing out of PSCAD. The method we use for this identification is PRBS because, as my colleague said, we have several types of identification method. Currently, we just implemented PRBS. Sajjad explained more about the details of PRBS technique. I'm not going to go through that. We are still working on this step because for this step, we need a very fast simulation file. The real case we had was slow. We are still waiting to get the faster one to finalize this step as well. As a recap, if we equip our existing wind farms with grid forming capability, we can say that this is one of the best cost-effective way of addressing the issues relating to weak grids we have in our network. The benefits are GFM, grid forming wind farms, can operate in very weak spots of the grid. The other thing is they themselves improve the grid strengths because they are voltage sources, and also they can provide some services we cannot have them from grid following inverters, like inertial support. However, providing grid forming capabilities by wind farms has some limitations. First of all, we are relying on the energy source, which is wind, which is intermittent. And also, we don't have a stiff DC link like a BESS, which limits our capability. In our study, first of all, we implemented a type after exploring the requirements and also designing the system. We implemented our wind turbine, grid forming wind turbine in Simulink MATLAB with different cases, SMIP case, Condor case, 39 bytes case. Then we switched to PSCAD simulations, and also we implemented a PRBS-based identification method to enable us studying the system with more details. And that's it, what I prepared for this presentation. Thank you very much for your attention.
Thank you so much, Mohammed Hasan, for this interesting presentation. This technology, grid forming wind turbines, we're hoping and expecting to become the norm in coming years. Well, this was mainly focused on type 4, but nothing will stop you from applying similar concept to type 3. And actually, type 3 could be even more interesting. The main reason is that type 3 has a machine connected to the grid directly, and that potentially can provide some fault current, which is a big limitation of type 4, because it's a full converter, and then you've got current limitations there. But yeah, so I think it can be a very interesting technology for future grids. Any questions for Mohammed Hasan before we go to our last presentation? Any questions online? Oh, Sorel, please. Oh. So are they like... They all run out of battery at the same time. No, it should be good now. Yep.
Okay, thanks. Is there any scope to look at how could it affect the mechanical side of the turbines? Are there any lifetime limitations as a result of it being in grid forming mode or anything like that?
That's a very good and valid point. The point is, when we are in a grid following mode, the mechanical side, we can say, at least for type 4, is completely decoupled from the grid events. So it's not contributing to the to provide services. However, in the grid forming mode, if we use the method 1 I discussed, we are trying to use mechanical energy, inertial response, intrinsic inertial response of the wind turbine to provide some of these capabilities. It definitely has some impacts, but still we haven't studied that part. But because we had a chat with some of our industry partners, they were also saying that we have some limitations for providing grid forming capabilities for our farms, but these are the things still under study. We also had another study regarding some torque limitations. Since we didn't have enough time to go through that, I haven't provided anything for that. But these are the things we are working on. We provided a solution for that torque limitation. In a nutshell, yes, we have some limitations, but we can come up with ideas to address them.
Okay, maybe in the interest of time, we can go to the last presentation of the day. Mr. Si Phu Me received the bachelor's degree in electrical and computer system engineering from Monash University, Victoria, Australia in 2019. He's currently pursuing the PhD degree in power electronic engineering at Monash University. His research interests include control and stability analysis of power electronic inverters. And Si Phu today will be talking about post-fault oscillation damping in grid forming inverters. Well, he's also working on in another project that we have on grid forming inverters and transient stability of grid forming inverters. Hopefully that study will be presented elsewhere, but today we are focusing on post-fault oscillation damping in grid forming inverters, which has been done within the context of our ARENA project. So Si Phu, floor is yours.
So thanks, Behrooz, for the introduction. So hello, everyone. I'm Si Phu. And yeah, today I would like to introduce to you the work that we have done on post-fault oscillation damping for grid forming inverters using virtual resistance. Sorry. There's a trick here? Yeah. Yeah, thanks, Mohammed Hasan. Yep. So in the presentation today, I will first give you a brief introduction on the problem, which is the post-fault oscillation of inverter-based resources, or IBR. And then two models of virtual resistance will be discussed. So the first one, which is the fixed value virtual resistors used for damping post-fault oscillation. This fixed value model is proposal existing in the literature. However, we found that there's some limitations when we use this model, especially when dealing with a steep grid. Therefore, we propose another adaptive model of virtual resistor to damp post-fault oscillation, as well as being robust to changes in the grid topology. And then at the end of the presentation, a few evaluation on the performance of the two models will be given. So let's start by having a look at the problem, which is post-fault oscillation of grid forming inverters. So we may know that inverters or grid forming inverters are very vulnerable during fault and fault recovery. So yep, show here on the left-hand side of the screen, which is an example of a post-fault response of a grid forming inverter. So you can see that the fault occurs at 0.1 second, and this is clear at 0.3 second, and followed by the fault clearance are oscillatory responses in both voltage, power, and current of the inverters, grid forming inverters, I mean. And those oscillations can be resulted by non-ideally tuned control loops in the control of the converters, and that can lead to the interaction. It can be a result of the interaction between different loops in the converter, and that can also be the undesired interaction between different IBRs in a local network. And apart from that reason, the wind-up of the current limiter in the grid forming inverter can also lead to that kind of oscillation. So for your information, in a grid forming inverter, as Mohammad Hasan mentioned, it is constructed from semiconductor material. Therefore, it is very vulnerable and very sensitive to overcurrent, especially during fault and severe voltage sags. Therefore, grid forming inverter need a current limiter to protect its internal semiconductor switches from overcurrent, and that the activation of the current limiter can put the inverter in a saturation mode. And when exiting a saturation mode, the wind-up phenomenon can occurs and lead to those oscillation. And yeah, anti-wind up methods can be used here to mitigate the effect of the wind up phenomenon. And in addition to that, you can see from the plot I showed here, the severity of the oscillation depends on the connecting condition of the grid, of the converter. So basically you can see here when the SCR reduces, the oscillation magnitude increases. It's a bit confusing here compared to previous presentation, but you might notice that as I mentioned before, grid forming inverter in this case require current limiter during the fault from 0.1 to 0.3 second, and that the activation of the current limiter put the converter in a current control mode, not really a voltage control mode during the fault. And by that reason, during and right after a fault, the grid forming inverter I've shown here is not really a grid forming one due to the current limiter. So that's why we have a lot of oscillation in low SCR level. So those oscillation can trigger the protection in the network unnecessarily, even the fault is clear. And also those oscillations can resonate with some existing oscillation mode in the system, and that can lead to the instability of the nearby IBRs, for example. So due to the negative impact of those oscillation, we need to equip grid forming inverter with a damping mechanism to suppress all the oscillation. And virtual resistance can be a candidate for this job. But because the grid topology is not static, it's kind of dynamic and it changes before, during, and after a fault. Therefore, the virtual resistance model is expected to be adaptive. And by getting rid of all the oscillation, we can avoid triggering protection and unnecessarily, and also we can prevent the interference between different IBRs in a local network. So by now you know what I mean by post-fault oscillation for grid forming inverter, but what is virtual resistance or virtual resistor? So we'll get to that point later, but now let's have a look at the model that I employed in this study. So it is similar to what my college has presented before. So a grid forming inverter is connected to the grid via some filter and grid impedance there. And in this project, I use cascaded loop here to regulate the voltage and the frequency of the grid forming inverter here. So for the primary controller, I use a droop, and the dual inner controllers are PI-based vector controllers. And those cascaded loops generate the control signal to PWM, and the PWM module I have there translate the control signal to gating signal and drive the switches, the semiconductor switches inside the converter to get the behavior that we want. So now I just replaced that single line diagram of grid forming inverter by this simple circuit. So you can see we have the grid forming inverter on the right of the model. We have the grid on the left. We have the filter between them and also a line impedance. So virtual resistor or virtual resistance, which is basically just a component in the control software of the converter, and it tried to mimic the effect of a real resistant or a real resistor in the circuit. So in this project, I insert a virtual resistor in that position, the red component as you can see in the circuit, insert it in that position to damp the post-fault oscillation. So you can see I put it before the terminal, and it can be seen as a component in the filter of the converter. And in the software of the grid forming inverter, this is where I put the virtual resistor. So it is put right before the PWM of the converter. So actually there's two benefits of doing so. So the first thing is you can see because I added that virtual resistor right before PWM. So whenever I need it, it can be activated almost immediately, because it just need to pass the PWM layer and then go directly to the circuit, and it can become online almost immediately. And their effect doesn't need to be passed through the cascaded loop. And also, because I put the virtual resistor in that position, which is outside of the cascaded loop, so it's independent to the grid forming control. So we can apply this virtual resistor to different types of grid. This virtual resistor to different type of grid forming inverter. So we can see this virtual resistor as an add-on to the control of a grid forming inverter. And as stated by its name, the virtual resistor I use here is mainly for damping post-fault oscillation. So for that reason, I just add it to the circuit when a fault recovery is detected, as you can see, and it will be removed when the system returns to a stable operation. And in the literature, there has been a study on that type of dynamic virtual resistance, and I call it fixed value virtual resistance. And the operation of this model of virtual resistance is exactly the same as what I just showed you in the previous slide. So when a voltage recovery is detected, the virtual resistor is added immediately to the circuit, and then it will be removed. It will be held at a constant value for a predefined amount of time that you can see, and then it will ramp down and reach zero and will be completely removed from the circuit eventually when the voltage and power are completely fully recovered. The reason I call this model is fixed value virtual resistor is because you can see the constant value that show on the green curve there. It is fixed for all operating conditions, and this can lead to some issue. So in a weak grid where the oscillation is very severe, as I showed you before, a very small virtual resistance cannot be enough for damping all the oscillation. And then if we use too large virtual resistance, it will lead to a very high demand of active current, because in this case we need active current for resynchronizing with the grid, and also we need active current to compensating for the losses over that virtual resistance. And at the same time, in parallel with that, we need high reactive current to restore the voltage after a fault. And as you can see, because both active and reactive currents are in high demand in this case, so the current limiter I mentioned before can be reactivated even the fault is cleared. And that would put the converter in a saturation mode, and it would lengthen the recovery process of the converter, and it can even put the converter in an unstable operation. And yeah, the problem here can become even worse when it comes to a stiff grid where the grid impedance is smaller. So in that case, as you've seen before, the sensitivity between the current and the voltage change will be even larger. The two voltage, the V grid and the VBOC will be coupled even stronger. So it will be very easy to reactivate the current limitation in this case. So by now you can see that it is important to determine the right value for virtual resistance when the grid condition changes. So due to that motivation, we propose an adaptive model for this virtual resistance. So the model we propose is called adaptive virtual resistance, and you can find more details about it on the paper that I show on the screen, and it's also available on our website. So the idea of this AVR or adaptive virtual resistance is adding less virtual resistance when it comes to stiff grid, so that we can avoid reactivating the current limitation. And when it comes to a weak grid where the oscillations are more severe, we put more virtual resistance to damp all the oscillations. And to do so, that model monitor the oscillation in the power the magnitude of the oscillation in the power, and the amount of virtual resistance will be determined based on this power oscillation. And yeah, that can be implemented by using this filter network. So the actual power of the converter will be monitored, and it will be fed to this filter network. And the output of this filter network would be the amount of virtual resistance that we will add to the network. And yeah, the tuning and the design of this filter network can be found in the paper that I showed you in the previous slide. So at the start of the recovery process, more virtual resistance should be used to dam the severe oscillation at the start. And then when the power is about to settle down to a new stable point, the amount of virtual resistance would be reduced gradually, and it will be removed, will be removed smoothly from the circuit due to the operation of this filter network. And yeah, the operation of this AVR model and also the filter network is governed by a state machine, and more detail on this can be found in the paper. Let's come to a few performance comparison here. So this figure is exactly what I showed you before, which is the fault response without the virtual resistance model. So it's very oscillatory. And then the same fault and the same condition are applied to a grid forming inverter. But in this case, it's equipped with AVR model or an adaptive virtual resistance model. So you can see the responses here are almost oscillation free. The voltage and the power can converge to the pre-fault level pretty quickly. And the FVR, or the fixed value virtual resistance that I mentioned before, is also tested here. You can see it works pretty well at low SCR levels. So for example, 1.8 and 2.8 here. However, when SCR increased to 4.5, the current limitation it activates again, and that leads to the collapse in the power and then the instability of the whole system. But for the adaptive model, if you have a look at the very bottom plot where I show the virtual resistance amount, you can see when SCR increases, the amount of virtual resistance inserted to the network reduces, and thanks to that, the current limitation is not activated, and the system can remain stable without much oscillation after the fault clearance. And similar results are seen from our experimental results here as well. So on the left-hand side here, without the virtual resistance model, the post-fault response is very oscillatory. But then with the AVR model added to the system, activated, all those oscillations are suppressed. And similarly to the simulation result, the FVR model works pretty well at low SCR, but when it comes to high SCR, it caused the reactivation of current limiter, and then the system fails after that. But the AVR, or the adaptive model, it is very robust against the changes in the SCR. And then just a few points before concluding this presentation. So the virtual resistance can be used in grid forming inverter to enhance the post-fault recovery of the converter, and it can help to help the converter to smoothly recover to a new stable operation. And the AVR model we propose in this project is robust against changes in the grid topology, and also it can be applicable to different types of grid forming inverter control, just like an add-on. And that's it for the presentation. So thank you for your attention.
Thank you so much, Si Phu, for this brilliant presentation. So we are almost out of time, so we can take a few quick questions from the audience, either online or... Yes, please. There should be a button.
The bottom here.
Are we mute, Larissa? Or
All right.
Yeah.
Is it working? Yeah.
oh yes,
All right.
it works.
Yeah, just a
okay.
quick one. Since this thing is outside of the main control loop, can it also be applied to grid following inverters, or is it just for grid forming?
Yes, that can be a potential of this virtual resistant, but so far we haven't investigated the application of this virtual resistant on grid following. But I think it's possible to add it to grid following inverter as well.
All right. Yeah. Thanks.
Yeah.
Yes, please.
Quick question. Yeah, this is really exciting technology. Can you elaborate what you mean by robust topology changes? How much topology change are we talking about here?
So I mean the SCR, robust again the changes in the grid strength. Yep, that's what I mean. Not the whole. Yeah, because usually...
at the point of connection, if something changes, right? Okay. Do we have any online questions?
Yeah, can we have the presentation slides and
oh yeah, the presentations and the session recording will be available on our website. So we need to probably do some editing and cut, because I guess we've got one large file at the moment. Probably need to break it into several pieces, and then we'll upload everything in the coming days. But yes, they'll be available on our website. Any further questions online?
There is one like about using high sampling PMUs. Is a big one.
Right.
It is directed to Behrooz.
Right. Okay, with respect to our early comment on the need to install more high-frequency PMUs in power networks to facilitate the application of frequency-based stability technique, is this the case because the high-frequency behavior of power networks is not predictable from line lengths? Well, the reason that I was referring to high frequency, well, because if you want to do the likes of, for example, frequency-based techniques and impedance-based analysis, you need to get the impedance of the network. In order to get the impedance of the network, what do you need? You need, or the impedance of the inverter. You need voltage and voltage and current. You need voltage and current sensors to be able to treat them such that you can get the impedance of the network. Now, depending on what bandwidth you're looking at, you need to have high sampling rate for these measurements to be able to extract the impedance of the network, the impedance of the inverters. That's why I was saying that we do need to have these high bandwidth PMUs. At the moment, what we've got is around 50 hertz, meaning that it's not enough to measure the impedance of the network, the impedance of the inverters. So if we want to apply frequency domain techniques, we do need to have high frequency PMUs. The other part, could efforts be made on the part of the NSPs to predict high frequency impedance characteristics? Well, yes, NSPs would need to actually install such devices in the networks to be able to do these things, right? Because we need to remember the impedance of the network and inverters can and do change with operating points. So at any point in time, and also with the topology of the network, so at any point in time, if you want to know the impedance of the network, you do need to have access to these measurements to be able to extract the impedance of the network. So that's why we do need these high frequency PMUs, if you call them. Okay, so I guess this brings the technical parts to an end. I would like to, before I hand over to Professor Markson for some concluding remarks, I would like to again acknowledge the help and support of ARENA in the project. Of course, without the funding provided to us, this work wouldn't be possible. And also, I would like to acknowledge our partners, AEMO, Hitachi, and AusNet Services for their fantastic help and support during the project. Very much appreciated. Also, Monash Energy Institute, who helped us a lot, obviously we operate under Monash Energy Institute and Professor Ariel Liebman. The Grid Innovation Hub is operated under that. So thank you so much, Ariel and the team. And also Larissa for putting together everything. Very much appreciated. So you did a fantastic job, I guess, in the last couple of months to put together this session. Great job. And of course, our researchers, PhD students who did a super great job in the last 30 months. It was a pleasure working with you guys. You did an excellent work, every single of you. Thank you so much. Very much appreciated and looking forward to more contributions from you. And yes, I guess that's about it. So Tony, if you please say a few words to close the session.
Thanks, Behrooz. And I realise numbers have thinned down a little bit, but the hardcore enthusiasts are still here. So I just want to comment that I wasn't quite sure what I was going to get today when I signed up to come here. I've watched the project over the last 2.5 years and the proposal before that to thinking, yeah, this is what Australia needs. We need research in this area. And today has just hammered home the point as to the value of this research to the transition that Australia faces. There's no other country in the world that has the challenge of a grid. I once explained to a British engineer, I said, if you considered the English grid stretched out from London to Minsk in a straight line, right through Europe and halfway across Russia, you'd have the Australian grid. And the load on that grid would be less than the British load. But you've got to keep it secure and reliable, and you've got to have a diversity of sources on it. And the guy just shook his head, you know. We've got a challenge that no other country in the world faces. And the research that you've heard about in today's session is a really important step in meeting that challenge, not only in the results, but also in the fact that we now have a cadre of highly expert individuals who have been working with these issues for 2.5 years and are available. As you've seen in the write-ups of the various speakers, half of them already got jobs in the industry. So there is an injection of talent and expertise and thinking and so on into the Australian industry to help us all with the challenge we face. My final comment is that this is the first step. Now, as I mentioned in my opening remarks, our vision is to take this further and to actually try it out. Take some of the best ideas out of what you've seen today and find the research funds and the industry willingness to actually do it. So if we're successful, then we will have some working examples of this, and it will influence the future of the industry. It'll influence the regulators, the operator, the TNSPs, everyone into the future, and help all of us together meet the challenges we face, because we're not even at the ankle point on the curve that we've got to climb to have a successful transition to an IBR-dominated grid. I don't expect to be around when it's complete, because it's going to take decades. But it's a great time to be in this industry. It's one of the most exciting times. After decades of boredom, we finally get to see some action, some real action. And you've seen the cutting edge today. And I hope to perhaps see you again at the next presentation when the next project reaches its conclusion. So I'd like you to join me in thanking all the presenters, Behrooz as being the project director right through and the sponsor at the start, Arena and AusNet and ABB, Hitachi and AEMO for seeing this project through to its completion. So thank you very much and have a safe trip home. Thank you.
Thank you, everyone. Well done.
Thank you, Tony. Thank you, Bruce.
By the way, for those of you who are in the room, we've got a lot of food and refreshments left. So please help yourself, take home whatever